This video is normally an in-house training material for our students here at ThrustFlight, but we wanted to make this public, give back to the aviation community because our students say that this is a great tool, a great touch point for anyone who's entering their multi-engine course training. That being said, Alex Shoza does a great job at breaking this all down into ways that you guys can understand it, and I really hope you enjoy. Without further ado, let's go ahead and get into the first day of multi-engine course training.
All right, so that's kind of the list of core topics we're going to go through tomorrow. Today is going to be very formal, very structured, all about aerodynamics, VMC, minimum controlled airspeed. We'll go through systems, primarily constant speed propeller, the landing gear, genital combustion heater, electrical system, and fuel system. And then we'll also dive into some of the performance charts and calculations. That's, like I said, the bulk of the formal content in the ground. Tomorrow's focus is going to be more so things that are going to help you out training in the 141 program and flying the Seminole specifically. Make sense? But as far as you guys are concerned at a very basic level, kind of structure of how the course is going to go, we'll have ground class today for 4 hours, going over those topics that I told you about: aerodynamics, VMC, systems, and performance calculations, or 4 topics really. And then tomorrow we're going to go through more detailed information with respect to flying the plane and the course and some other nuances towards the stage check, the EOC. After these 2 ground courses that are each 4 hours, you guys will be booked for a sim and a cross country. The sim will likely be 2 hours. We'll be using all 2 hours of it, and it's going to be configured for the Piper Seminole. This way you guys can get configured, or rather introduced to flying the complex aircraft. 2 standout new systems are going to be the constant speed propellers. Has anybody flown constant speed? All right, so you have one guy who's familiar, but now you have a whole new set of levers. We also have landing gear, which we need to consider in various different phases in flight. So we're going to hop in the sim, get you guys familiar with that, and then also walk through all of the procedures with respect to all the maneuvers we do, all the criteria we practice, landings, takeoffs, instrument approaches, and single engine operations. Make sense? Hello. So really, it's in your guys' best interest that before you go into that simulator session, you have the maneuver guide studied and memorized to a T. Right? The multi-engine aircraft and complex aircraft, there's a lot going on. It's going to be moving a good bit faster than what you're familiar with. So if you're expecting to just get in the plane and learn it as you go, I'm telling you right now, you're going to be way too task saturated for that learning to occur. If you do the due diligence of studying the maneuver guide and having it not only memorized, but rehearsed via chair flying, I highly recommend you either get yourself a poster for the Seminole, or if you go on Google and just type in PA44 G1000, you can go on Piper's website, and under the avionics subpage, they have a beautiful, wide-angle lens picture of the entire cockpit, and it looks just like our chair flying posters that we all got in private. You can hook that up to your TV, and you can get familiar with where all the switches are and where all the throttle levers are and the cowl flaps, and this way you can sit at home in front of your TV and actually chair fly. The other thing, for those of you local here to Addison, our Seminoles aren't necessarily flying all day every day. So if you go into Flight Schedule Pro and you look under the plane and there's an open 2 or 3 hours, go sit in the plane, chair fly in the plane. But of course, don't move things out of reason, right? Like, we don't want to be moving prop controls and gear levers around when the plane's off, right? So within logical reason, go chair fly these planes. Make sense? So before that sim, all the maneuvers rehearsed. The engine outflow is probably one of the most important things in this entire rating when it comes flight-wise. It's important to know it so that you can do it calm, cool, and collected in the event that we're training it under simulation, or in the event that you actually have an emergency. But about 50%, if not more, of our training is just flying a single engine or a dual engine aircraft with one engine and managing those kind of engine failures. So I'll send you guys a video on YouTube that I really like that introduces this engine outflow and kind of digs into the importance of it. And one of the quotes that the instructor in that video says that I also agree with is that engine outflow, by the time we get into training, should be as deeply ingrained in your mind as the song "Mary Had a Little Lamb." What he's getting at is that When the engine failures occurs, it shouldn't be some kind of panic and you shouldn't be frazzled, you don't know what to do. You just have it rehearsed in your subconscious that you can patiently, calmly, and collectively go through that engine outflow. So 2 things, maneuver guide, memorized, rehearsed via chair flying, engine outflow, memorized, rehearsed via chair flying to the point where you don't even have to think about it, right? So from that first sim, as you can tell, it's important, 2 hours of sim. We really, really do use it, more so than the other ratings. You guys will be booked for a 4-hour cross country. The criteria on that one is that 2 hours of it are during the day and 2 hours are during the night, or the vice versa if you fly in the morning. And it needs to be to a destination of 100 nautical miles away from here. The best use of your guys' time, in my experience, is to choose a destination that's pretty close to 100 nautical miles, but slightly over. This way you can maneuver your way out there and practice all the maneuvers in the plane. You can practice some instrument approaches on the way back and have some time left over to maybe do some short field landings and introduce those things. So it's a cross-country flight by all intents and purposes, and you'll plan it like a cross-country flight to get that experience in the twin, but we'll be flying it much like a blend of cross-country and maneuvers so that we can be as productive as possible. Make sense? From there, you'll have 2, potentially 3 training flights if you need it and if you have the hours available before going into a stage check in an EOC. Those training flights are going to be with your buddies, so each of you will be paired, or I guess 2 of you will be paired together, and you're going to be backseating each other for everything with exception to that first sim and the first cross country. But everything is really only 2 or 3 flights. It'll be about a 6-hour block for 2 days. That'll be standard. And then the way I like to break it up, each MEI is different, is we'll do 4 flights within that 6 hours, each around 1.2, just so we can focus on something and then give you guys a little bit of a resting break and go in the back seat so you can see everything while you're not task saturated and then switch again. But point I'm getting at is that the course is very, very accelerated. The more preparation that you can do going into it and the more preparation that you can do outside of it, the more you're going to succeed. So kind of to review, at least the key points, going into that sim, maneuver guide, memorized, chair flown, engine outflow, rehearsed to the point that you know it, as well as Mary Had a Little Lamb. You'll have 2 maneuver flights after that, so we should be pretty well studied up on the ground, because after those 2 maneuver flights, potentially 3 if you need it, it'll be off to stage check in EOC. Make sense? So any questions on the structure of the course before we get into the material? And please ask questions all the time. It makes the class a lot more, productive for you guys because we get into topics that I don't have rehearsed, and it makes it a lot more fun for everybody, me included. I've taught this class probably once every other week for the last 5 weeks, and it's beginning to get a little repetitive. So the more you guys can ask questions and kind of throw me out of my routine, the more I appreciate it, and the more you're going to learn from it. Sound good? All right. So my background, I guess, my name is Alex, for those of you who don't know me. I think the majority of you do. I'm going to write my name and my phone number in case you need anything related to the course. Whatever you guys need, just shoot me a text message or a phone call. I'll give you the warning. If it's past 8 p.m., I'm probably not going to answer because I'm sleeping. If it's really early in the morning, don't hesitate because I'm usually up by 3:45. But my background, I've been here working with thrust since April, a year on the dot. Did all my training in the Archers, did my commercial add-on in the Seminole, commercial check ride with Joe Johnson, MEI checkout with Patrick. Probably at this point pretty evenly split between instructing in the Archer and the Seminole, but beyond that my flight experience is very, very green, as in I've only flown the Archer and the Seminole and a decathlon for spin training. So if anybody has any outside experience with different aircraft, especially different twins, I think it could bring a lot of value to the discussion that we have here. Maybe some Barons or Aztecs, Twin Comanches, that kind of thing. So that being said, beyond flying, I have a background in mechanics, so I have a decent understanding of all the systems that we're going over to and just physics in general. So if anybody wants to get in the weeds of those topics, don't hesitate to ask. Sound good? All right, so we're going to start with aerodynamics. Everybody have a good view of this slide? It's not too dim. So I'll ask you guys the question before we even get into this whole journey. What's the point of flying a twin engine aircraft? Why do you guys even want the rating, besides it being a stepping stone to go fly bigger equipment?
It's like safety.
Safety, how so?
If we have an engine loss, we can still continue to fly. I guess, yeah,
Yeah, I'd say that's spot on. And first time you guys ask a question, I know some of us are familiar, but can you please just remind me your names?
I'm Garrett.
Garrett, I remember we met in Denison quite a few times. But by the end of the class today, I'll have each of your names memorized. So Garrett, very good. I agree with you entirely. Anybody else have any other ideas of why you might want to fly a twin?
It's cool.
It's cool? Hell yeah. That's a good answer too. Bill, was that you? Oh.
More job options.
More job options?
Yeah.
All right.
When you're trying to get hours to get to an airline, you have more options.
All right, that's a good option as well.
Get places faster.
You can get places faster. I might agree but slightly disagree with you on that one, but we'll circle back to that. What else?
Carry more stuff.
You carry more stuff. Again, I might agree with you but slightly disagree with you on that one.
Well, with our multi, yeah, for sure. You're not carrying a lot of payload.
Yeah. So common misconceptions that people have is range. You can go farther because you can carry more fuel. Or payload, you can carry more because you have more thrust. Or performance, you can climb faster, fly faster because now you have two engines as opposed to one. But let me ask you guys this. If we had an Archer and we just slapped on a 360 horsepower engine, wouldn't it be faster?
Absolutely.
Yeah, wouldn't it carry more weight?
Absolutely.
Wouldn't it have better range if you can carry more fuel with that more weight? Yeah, so you get all these things, and tell me, which one's easier? Putting an entire other engine on an aircraft or just making the engine you already have bigger?
Bigger engine.
Yeah. If you have a single engine, you double the size. One, it's less extra weight. Two, it's less extra complexity. Three, less packaging. You could probably make your airframe a lot more aerodynamic. So all win, 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 win for just making your engine bigger. So yes, while these are true, inherently twins tend to have these things in greater capacities than the single. That's not the purpose of the twin. The overwhelming one is what Garrett just said, safety and redundancy, because you lose an engine, you can still fly around. So follow-up question on that, what kind of flight missions do you think the twin is tailored towards? Medevac, over water. Okay, so then what are we looking for here? Harsh terrain over water. I think you'd say the same for mountains or deserts or sparsely populated areas. Medevac, what's the case there?
Safety, ensuring that somebody's getting from point A to point B.
Yeah, insurance, right? High priority cargo, high profile missions that want to minimize risk. Very good. So environment, high profile missions that want to minimize risk. And a third one that I like to bring up that really doesn't relate to what we're doing here nor our time in history, but warfare, right? All those bombers, all those, not all the fighter planes, but a lot of the bombers that needed to fly multiple missions and carry payloads, they had two engines, if not three, four, six. Like, oh, we used to have, I think, a B-17 on the wall here, but it's gone. Anyways, if you're getting shot at, right, you lose one engine, you still got another one, right? Oops, going too far ahead. So one theme that I like to carry from topic to topic to topic as we go out through today and tomorrow is going to be a failure mode analysis, I call it. So what happens and kind of comparison between if a system fails, if an engine fails, etc. Make sense? So first one I'm going to throw at you guys is if you're flying a single engine, as you know, if you fail that engine, if the engine fails, what's the clear con of that situation?
There's a good chance you're not going to get a restart.
Good chance you're not going to get a restart.
And you're going to be forced to land at that point.
Forced to land, you cannot maintain altitude, right? Cool. Now, what's the clear benefit of that situation? And you guys coming into the course might not be entirely aware of it, but I guarantee you by the end of the course, you might see it pretty transparently.
Is your glide ratio better?
I mean, it depends from airframe to airframe.
You have less thing to worry about because all you're thinking about is like airspeed and then getting the engine restarted and work on that. But
Maybe you
when
start
your
to
engine dies, you have to worry about it yawing off, and now you're trying to fix or get the engine that's not working set up well, maintaining the one on the right or the one that's still working.
That's exactly right, Garrett. That's brilliant. So clear pro to the situation. I'd say there's really two. One is that it doesn't fly any different, whether you have an engine or if you don't. I mean, of course, climbing and descending is a little different, but turning, your controls, all of that's exactly the same. Landing the plane, whether you have an engine or not, it's fundamentally the same, right? You just don't have that extra energy from the engine. Two, what Garrett was alluding for, It's very straightforward in the single. It doesn't require specialized training. You run your troubleshoot checklist to try to get restarted. If that doesn't work, you run your emergency landing checklist, and then you fly it down just as you know and land it in a field or an airport, right? We train private pilots to do it all the time. Now, other side of the coin, multi-engine aircraft. If you lose a engine, what's the clear benefit of that situation? Or not benefit, but a pro.
You have another engine.
Yeah, exactly. You have another one. You can maintain altitude. And what's the con of that situation?
You gotta handle the dead end.
Yeah, you have to handle the dead engine. It's more workload, and it requires very specific pilot training because it's not easy. Now you're introducing asymmetrical thrust. The airplane does not fly the same. That operating engine is totally unbalanced relative to your center of gravity, and it just wants to yaw you and roll you into a condition that's not very good if you let it get a hold of everything. Make sense? And that's why we have the whole rating in general, the multi-engine add-on, is to teach you guys how to deal with that situation when an engine goes bad and how to deal with the one that goes bad and still fly the plane with the one that goes good. Make sense? So yeah, that's that slide that we just went over. I'm hesitant to give you guys the next slide because I like this conversation more and I tend to just give you the answers if I put it up. So we're gonna always be one slide behind where the conversation is, all right? So if you lose an engine in the twin, how much horsepower are you losing, at least in our Seminole?
I guess you
If you lose one engine, you lose 90% of horsepower?
50% of horsepower.
Yeah, 50% of the horsepower. Cool.
Talking about performance.
Performance. Is it total performance?
I would assume so.
Performance.
Climb performance. You lose 80 to 90% of your climb performance even though you only lost 50% of your horsepower or your power. Now, I'll ask you guys, have you think about it for a little bit. Where does that extra 30-40% loss come from? From 50% horsepower loss to 80-90% climb performance loss? What accounts for that extra 30-40% loss? Drag, that's one of them.
You're talking about the asymmetric thrust. That's still drag.
Yeah, drag in a different way, I agree. What else?
I can't remember what it's named or called. I know I should. But you know, like it's the same thing when you're going to take off versus you're already in there, like the motor's having to work harder because the air's not going over as fast. Does that make sense?
The effective blade angle of the propeller and the relative wind. But we have constant speed props, so we could change that. Good thinking though. So really there's main three. One, you have the dead engine, so you've lost that thrust, right? What do we climb with in an aircraft, generally? What kind of thrust? Like what allotment of energy do we use in order to climb?
Like max?
Excess thrust. Excess thrust, right? Because it requires a certain amount of thrust to maintain straight and level. However, we always have a little bit extra in the tank when we go full power, and we use that excess thrust to maintain that same airspeed that we're going straight and level and turn it into a climb, because now we're fighting gravity at that airspeed with all the other factors as well, right? So dead engine, there's less thrust available, so we have less excess thrust to climb. There's the dead engine, which is dead weight. It's no longer producing thrust and it's no longer carrying its own weight. In fact, it's creating a whole bunch of drag because that propeller, if you haven't feathered it properly, is just windmilling in the air, and that's effectively a massive dinner plate that's just catching all kinds of relative wind and slowing you down. Does that make sense? So really these three factors at the core are the result of that 30 to 40% loss. I like to go a little more into the physics of it, so I'm going to introduce this chart to you. This is a airspeed and power curve. So on the x-axis here is going to be any given airspeed that you're trying to maintain, right? On the y-axis is how much power you have available in your aircraft, right? And this chart is a general trend that all airplanes follow. It's not the exact chart that our Seminole follows. It's a general trend that all airplanes follow. Is that understood? This green line here is the power required to maintain straight and level at a certain airspeed. So as you can see, if you're really, really slow, think of slow flight, right? You need really high angle of attack because you don't have a lot of air going over your control surfaces. There's not that mass airflow and you're not producing a lot of force. So you have to increase your angle of attack to produce enough lift and really slug yourself around in slow flight. Make sense? That requires a lot of power because there's a lot of induced drag in that scenario. The faster you go, the more airflow you have over your surfaces, so you're producing more lift, you can start to reduce that angle of attack, right? And when we get to a point where it requires the minimum amount of power to maintain a certain airspeed, that's known as our best glide, VG. Make sense? As you keep accelerating faster and faster, you can keep decreasing that angle of attack because you now have so much airflow going over the wings, but then the air that you're moving through becomes a lot of mass itself. And you have to keep splitting that air that you're moving through. And that creates a lot of drag. This is our parasitic drag and increasing airspeed drag, right? The faster you go, the air becomes more like a cake that you're flying through rather than this gas. So that's why as you start increasing speed, the drag, parasitic drag increases and you need more power in order to plow through it. So you guys understand the relationship of this curve? This is what we call the back side of the power curve. This is what we call the front side of the power curve. Now, if you understand this relationship, we can jump to the red line. That's how much power we have available in the airplane. And kind of what Garrett was mentioning, the slower you are, the less effective relative wind you have on the propeller, so the engine can't operate as efficiently with what it's equipped with. The faster you go, the more efficient it is, so you start to get these kind of diminishing returns towards power available. So that explains the curve. The distance in between these two is your excess thrust, and that's what we use to climb. So if we maintain straight and level right here, that's how much energy it requires. You only need cruise power setting. But if you want to climb, you go full power, and you have all of this excess thrust available from max power in order to fight gravity and climb. And the area underneath these two curves is all your excess thrust that you have in a range of airspeeds. But specifically the point that these are farthest apart is how you determine your VY. Your best rate of climb is going to be the relationship where you have the most excess thrust based on your aerodynamic characteristics in order to climb with. Does that make sense? So now getting back to this multi-engine case, if we lose 50% of power, how is it that you lose 80 to 90% in climb performance? Well, this is power available, and we cut it by 50% on that y-axis. That line results here. And now what happens to the area in between the two curves? Yeah, I would argue this is like 80 to 90% of that area of excess thrust, and it's totally shot. Hence, 80 to 90% of performance loss. Make sense?
Yep.
Sweet. Way more detail than you guys need to know, but I kind of nerd out over stuff like that, so thank you for entertaining me.
Oh, thank you.
All right, performance with a single engine. We talked about asymmetric thrust. Garrett kind of leaned into how the aircraft wants to steer you out of control. This is kind of what it looks like in a force balance diagram. So left engine in this case is out, and this propeller is just windmilling, so it's creating a whole bunch of drag. The right engine is still producing thrust because it's operating. The center of gravity is here. That's a huge imbalance, and it wants to steer the plane over to the left, right? That ends up leaving you with a crab if you're just countering it with rudder, right? So naturally, if your plane wants to yaw over to the left, you're just going to mash the rudder to straighten it out, right? But the plane's not going to be flying in the same direction as the relative wind. So here's a good representation. If you were to put a yaw string on your front window, it would be going diagonally. Because when you're flying in that asymmetrical OEI condition, you're in a crab. Any questions on how that looks?
Are you going to remain in a crab?
No. No. We're going to introduce what you already know as zero side slip with up to a 5-degree bank to correct this and improve your aerodynamic efficiency, but we're going to get to that in a moment. Make sense? But this is just the scenario if you were to fly straight, wings level, and mash the rudder to correct it. Very inefficient aerodynamically.
A question about a practical sense.
Okay?
Let's say we're doing a simulated engine, right? Will it be a dramatic change, and will we have a normal human reaction to try to correct the airplane? Do you think that's going to occur? Okay.
You will. And that's a good point. Usually I talk about this tomorrow, but we'll dive into it now, and I'll just repeat it to you guys tomorrow. Let me preface it with I've probably put through close to 50 students in the 141 program now. Somewhere between 40 and 50, rough estimate. And one of the things that I'm seeing over and over and over again, especially doing stage checks and EOCs, is people get so caught up in the, what's the right word I'm looking for? Kind of in the verbiage of raise the dead engine and split the ball, zero side slip, that when they get the engine failure, that's the only thing they can think of. and they start making really aggressive aileron movements and really aggressive rudder pushes in order to raise the dead engine and split the ball, but they haven't even taken the time to feel what the airplane's doing and properly assess which aileron needs to be raised and which rudder needs to be stepped on. And what happens in that scenario is there's a panic, there's a stepping on the rudder, and 50-50 chance it's the wrong rudder, and then now you're 30 degrees banked, dropping the dead engine, and then panicking even more because you're so uncoordinated, right? So that's exactly what you do not want to do. So let me give you the good advice that when you get the engine failure, don't worry about anything for a second. The first thing you should do is just take a deep breath and let the plane fly for a second and just pay attention to where it's going, right? As long as you're not terribly slow, nothing catastrophic is going to happen. Just take a second, take a deep breath, and you'll see which way the plane's leaning, right? If you just look out at the horizon, the nose is going to go over to the right if that engine's dead, or to the left if that engine's dead. And you don't even need to make that connection. You'll just notice which way the nose is veering, and then you can start tilting your ailerons ever so slightly in the opposite direction, and then you'll know which rudder to step on to arrest that drift. And just naturally, by doing that and centering your ball, because that's just the cross reference, don't worry about zero side slip, just center your ball. You're going to be in the proper aileron and rudder coordination to then begin your engine outflow. And that's where you pitch for your 88. You've maintained directional control by doing that. Mixtures, props, throttles, gear, flaps, identify, verify, choose to feather, and once you've feathered or done any troubleshooting, that's where you can establish your zero side slip. Make sense? So kind of rule and thumb to top off your question, because I see it so many times. Engine failure comes by simulation or in real life. Do not immediately respond that instant. It is not a race. Take a second, feel out which way the plane's drifting, and make gradual control inputs to arrest that drift, and then continue with your engine outflow, right? It feels like it's a lot slower, but in reality, it happens in like 2 or 3 seconds max.
And one more question. We are not going to actually feather the prop in the air. We will?
You will.
Okay, cool.
Caveat though. We will feather the prop as a training exercise because it's useful for you guys to learn how to do it. Whenever we do engine failure simulated, if it's below 3,000 feet AGL, it's always going to be with a throttle pull. And you'll run your flow, and if you're at a right position to make the decision that, hey, I'm going to feather, you'll point to the prop that you want to feather, and then I will simulate, or the other MEI will simulate a zero drag condition per the POH's recommendation with throttle in order to produce a little bit of thrust that counteracts all that drag. We will not actually feather, and we will never land with a feathered propeller unless it's an actual emergency. If we're above 3,000 feet and we're practicing a full engine secure, yeah, we'll feather it. With a disclaimer, other MEIs might tell you to do other things. I always ask, if you're ever going to make a decision to feather the propeller, put your finger on it, look at me and ask me to verify it. I'll nod my head or I'll tell you no and then go ahead and pull it. Because the last thing you need is somebody to get all jumpy and panicky and pull the wrong one, and now you have one simulated dead engine with the mixture out and then one feathered engine that's stalled out, and now there's no checklist for that. The MEI has to be very on top of their game in order to get things, because you've got no thrust, you're a very heavy aircraft, you're going to start descending really fast.
The thing, what is it called? Like the online thing for this tip kit, it said we had to be above 4,000 AGL to do like a simulated, like actually kill the engine. Is that a thrust thing or is that a?
That's what he just talked about.
I said 3,000, and that's a very good point. This is where it comes from. In the POH, it requires us to do a VMC demonstration maneuver above 4,000 feet.
Okay.
To this day, I have not found anywhere in the POH that says we can't practice simulated engine failures above 4,000 or 3,000. If it's in there, please let me know, right? I've dug well enough, but I've not scoured the entire thing, so I could be missing something. So POH says 4,000 for VMC demos. The FARs, the regulations, say that you cannot do an engine failure with a mixture cut or anything but throttle below 3,000 AGL.
Okay.
Does that make sense? So if you want to simulate anything below 3,000 AGL, it needs to be with throttle. Above that, mixtures, fuel selectors are fair game. However, the POH says 4,000 for a VMC demo, so thrust has always had a bit of a gray area of, hey, do we follow the VMC demo recommendation and do all single engine work above 4,000, or just the VMC? There's not a definitive answer. A good question. All right, so back to this scenario. You lose an engine and you're just stepping on the rudder, and let's say you're a pilot that isn't properly trained on how to deal with all this asymmetrical thrust. What's the main concern? Like, what could happen out of this situation?
Get slow, mid-stall.
You get slow and you get stalled, and then what happens? You spin. Exactly. Now, do you guys know what happens in a multi-engine aircraft if you spin?
You don't get out.
You do not. Are there any multi-engine aircraft rated for spins?
Sure there are, maybe.
I don't know of any either. You think pair would work in a twin?
Yeah.
You think so?
In theory.
I'd make the argument that very, very early on, like before you get into the incipient phase even of a spin, pair could work. But if you have any kind of momentum in that spin, game over. So let me draw on the board. That's your single, right? There's the twin. Where is the majority of mass located on the single engine aircraft? Where?
The center.
Center, right? So CG, I mean, I'd make the argument that both of them have a CG roughly here, right? But outside of where the CG is, what are some things that are very, very dense in terms of their weight distribution? The engines, yeah. So we got this one screaming right here, right? But that is in line with the CG. And now you have these engines that are not in line with your CG. So if we start rotating,
More momentum.
the mass of those engines has a pretty significant moment arm from the center of gravity, as in that mass is displaced and located outwards. In physics, this is called mass moment of inertia. Essentially, how much mass do you have outside of your center of gravity, so that once you start rotating, you get a measurement of how much momentum in a rotational velocity you have. Does that make sense? Threw out a lot of big physicsy words there.
So basically what you're saying is that the weight, once we enter a spin, is going to want to continue to move away from that CG as we accelerate the spin.
I mean, that's by centripetal force,
Yeah.
yes, but what I'm saying is the weight as it begins rotating around the CG, by Newton's first law, every object in motion wants to stay in motion until disturbed by an external force. That weight is going to want to continue rotating.
Absolutely.
So you're going to have so much rotational momentum of however heavy those engines are, hundreds and hundreds of pounds spinning around, that no amount of rudder deflection and no amount of aileron neutrality and power idle and pitch the nose over is going to overcome the rotational force that those engines have once they get turning. Make sense?
Yeah.
So very, very early on, before that rotational momentum is big, yes, maybe pair will work. However, no multi-engine aircraft is rated for a spin, because once that baby gets spinning, you don't have enough rudder to stop it. Hence, reiterating the importance of this rating, right? Flying a two-engine aircraft is very much similar to flying a single. You just have to monitor a couple different things. Where it all goes different is how you handle that twin-engine aircraft when only one of your engines is operating, and how do you stay safe with it. And my favorite part is, how can you plan for the flight to minimize risk as much as possible in the event you get this engine failure. But we'll talk about a lot of that tomorrow. Any questions? So yeah, no multi-engine aircrafts rated for a spin. All right, so kind of trailing into what Nick was hinting at, one thing that we help, or that we practice, one thing that we fly in order to help with this single engine condition is called a zero side slip. This is an orientation of the aircraft, a technique in order to reduce drag and make you aerodynamically much more efficient. I'm going to grab this model airplane to help demonstrate to you guys. So we'll start off here, wings level with OEI. We've lost an engine. Maybe I have a pen to put here. All right, let's say the scissors are the operating engine, right? We've lost an engine here. The plane wants to steer off in this way. Does that make sense? So how do you counter it? With rudder deflection, right? If it wants to steer this way, you're going to go left rudder, but these forces are going to be unbalanced. You're going to be flying in a crab, much like this. All of this side of the fuselage is exposed to your relative wind. Flying in a crab is aerodynamically very inefficient. So this technique, zero side slip, encourages you to raise your dead engine with bank. So you bank your ailerons over, roughly 0 to 5 degrees. Every airframe is going to be different. And split the ball. Splitting the ball is what you see on your turn coordinator. But what that does for you, engine failure aside for a second, when you start to bank, the aircraft naturally wants to start rolling and turning in that direction, right? So with the engine failure here, if you're flying in a crab, you start to bank, it wants to turn the aircraft. However, the asymmetrical thrust is going to oppose and counteract that turning force. They're going to balance each other out. And now you're slightly diagonal with the dead engine raised, but aligned with the relative wind and using less rudder because you're not crabbed anymore and you can fly much more effectively. The way these forces all balance out is because if you're flying straight and level, your wings produce a vertical component of lift. If you bank over 5 degrees, some of that vertical component turns into horizontal component. And that horizontal component is helping fight the asymmetrical thrust from your operating engine. It balances each other out, once again reducing the load needed on the rudder and increasing your aerodynamic performance. Make sense? It's very, very, very beneficial, to a point which every 1 degree of bank can reduce your VMC speed, the speed where you'll lose directional control and that operating engine will roll and spin you if the critical engine was out, right? If you bank over 1 extra degree, you can raise your VMC speed, lower your VMC speed by 3 knots. 2 degrees bank, 6, 5, 15, 10, 30 knots, right? Huge. But we limit it to 5, and I'll get into why later. Make sense? One more thing just to reiterate. When we're flying this technique in the plane, this is what we're going to see on the G1000s. The picture's kind of small. Can you guys make it out? Everyone here is going to be in the Seminole, right? G1000. The triangle, your bank indicator, is primarily set by your aileron control. It should just be using ailerons to keep it somewhere in between the center diamond and the first tick mark of 5 degrees. That's what you use ailerons for, to move this somewhere in between there. Once you have it established, your aileron should be neutral, and the rest is rudder. Rudder for directional control and maintaining your heading, and roughly splitting it so that if you follow this edge of the triangle down, it meets up halfway through the brick. That's what we call splitting the ball, because in a traditional slip and skid indicator, it was the ball suspended in the Vaseline or water or oil, whatever it was, and you split it down the line. But we call it splitting the brick. So once more, to reiterate, your primary means of maintaining directional control in an OEI situation is your rudders. The ailerons are only used to get this triangle somewhere between 0 and 5 degrees of bank. Make sense? It's another thing that I see. People are like throwing the ailerons over, trying to steer the aircraft with bank. It's your feet. If any of you guys go to the gym or do some kind of leg workouts, the week that you're flying is a good time to take it easy because you're going to use them in the plane. Right. So if you lose an engine, back to this failure mode analysis, which one would you guys rather lose? Left or right?
Right.
Why?
I would say you're gonna have, if you lose the right, you'll still have more control authority on the left side.
In the Seminole?
Maybe for conventional, you'd want to lose your right engine instead of.
Yeah, now we're getting into the weeds. So we'll start introducing them. There is an engine that you would rather lose because not all the engines are made equal in all cases, right? A lot of it depends on the orientation of your engines on the airplane and how they're set up, right? Critical engine is the naming convention we use for the engine that if you lose it, it's going to hurt you the most, right? So if you lose your critical engine, it's going to most negatively impact your ability to maintain directional control and have any kind of climb performance. Make sense? So critical engine will have the most negative impact on your airplane's performance and directional control. That's the one we do not want to lose. Kind of as Nick was alluding to, there's 2 common types of orientation on engines in light twins. Conventional, which is both of your engines are rotating clockwise, or for your guys' view, clockwise, right? Then there's non-conventional, counter-rotating, as in both of them rotate inwards. Make sense? Which one's the Seminole?
Non-conventional.
Non-conventional. Why? Yeah, safety, because there's not a critical one, which we'll get into in a little bit. But of these 2, which one's more popular?
Probably
Conventional.
Why?
Cheaper.
Why?
Because you just have the exact same engines. You don't have to make an entire new engine for the right side.
Garrett, you're a freaking genius. Exactly. It's all from manufacturing, right? If you're Piper and you're making twin aircraft, wouldn't you rather, if you were making 1,000 of them, for example, wouldn't you rather have one assembly line that just pumps out 2,000 engines and one set of crew to assemble it and one set of packaging and one set of engineers to design all the parts, as opposed to having 2 whole assembly lines and 2 whole sets of engineers and 2 whole sets of packaging to make 2 whole different types of engines that need to be maintained in 2 different ways? Just a lot more affordable. So conventional is more common. Big misconception here too is people think, well, if non-conventional is way safer, then why doesn't the FAA mandate that a non-conventional is the way to go? Reality is that engine failures aren't, I guess, yeah, they could be common, but they're not something that you try to do, right? Like you don't go out flying saying, I'm going to have an engine failure today. It happens, it's circumstantial, it's relatively minor. So when it does happen, as long as the pilot's trained to withstand it, it's usually an okay situation. Non-conventional is more so trainer aircraft, where the flight mission demands that, hey, we're going to go shut off a bunch of engines, we're going to practice stuff single engine, and we want to prioritize the safety. Make sense? If you're just flying a passenger from A to B 100 times a year, probably going to fly one of these because the chance you get an engine failure, I don't know what the percentage is, but I bet you it's probably closer to 1 out of that 100. As opposed to the training flight, you're going to turn off an engine every single one of those 100 times. Right, so there's 4 elements of physics, 4 factors that we use to understand why the critical engine is the critical one. The first of those 4 is P factor. And this goes back very much so to our private understanding of P factor. Does anybody want to give me a simple definition in their own words of how P factor works on a single engine? Come on, don't be shy.
On a single engine,
Yeah, on a single engine.
essentially what we have is in a climb, the descending blade has a higher angle of attack, generating more thrust on the right, thus causing a left turning yaw tendency.
Yeah, I would slightly reword that rather than in a climb with any positive angle of attack. The descending blade of the propeller has a greater angle of attack to the relative wind or takes a bigger bite of air. Choose whether you follow the P-hack or the AFM in terms of wording. Right?
Does that depend on rotation?
Sorry?
Does that depend on which side we have rotation, clockwise or counterclockwise?
Indeed, because the descending blade, if you're counter-rotating, right, you're descending inside the airframe, the fuselage is here, it'll be on your left, versus conventional is always going to be on the right.
And so would you have a lower angle of attack on the...
On the rising blade? Yes, but that's the same as the single engine land, right?
Yeah.
Same thing, P factor, single engine land, if you have a positive angle of attack and you're climbing, your descending blade, the right side blade will have that greater angle of attack, and your ascending or your rising blade will have a lower angle of attack. That's always true, and it's going to be the same in the Seminole, whether you're conventional. Those rising blades are always going to have lower angles, and if it's non-conventional, then they're rising on the outside and they'll have lower angles, right? But here we get into a discretion. So we're going to draw this out nice and big for you. This is our multi-engine aircraft, and I have to space it out relatively similar. Otherwise, the math doesn't work out, or the geometry doesn't work out. Those are the 2 engines. Big enough? We make them a little bigger. So the descending blade has a greater angle of attack. It's producing more thrust, right? So let's draw that out. More thrust on the descending blades. The ascending blades are still producing thrust, but like we just discovered, less. So you can draw tiny arrows.
And this is for conventional, correct?
All of these examples that we're going to go over are for conventional, because a non-conventional, counter-rotating, doesn't have a true critical engine. So these are critical engine for conventional because a non-conventional does not have a true critical engine. If we were to take the average across the span of the propeller blade of where thrust is being produced, like you know how we do center of gravity? If we do a center of thrust, it's probably going to be out over here, right? Because we know where more thrust is being produced on the descending side. You guys agree with that? I'm going to try using the blue because the green is kind of shot. They're all shot. I'm going to go get more markers. We'll stick with green. So drawing the center of thrust, we'll just call it there. You guys following? So now if we wanted to draw the moment arm from this center of thrust on both sides, it is clearly much, much greater on the right. Because of this phenomenon, if we lose the left engine, our critical engine, the right one has more leverage to yaw us out of directional control. Make sense? Conversely, if we were to lose the right engine, the left one will still want to yaw us out of control to the right side, but it has less leverage than the opposite scenario. So both are bad, both result in asymmetrical thrust. However, the asymmetrical thrust produced by the right engine operating is greater because of the P factor. It has an extended moment arm and more leverage on the thrust that it's producing to yaw us out of control. Does that make sense?
I'm still a little confused.
Okay.
I don't know why or what happened, but whenever you started drawing the blue lines, it was just coming in one ear, not the other. So do you mind just repeating?
Yeah. So we'll erase this green because I think it's confusion. So we determined because of P factor on the propeller blades, we're producing more thrust on the right side of the engines, right? So if we were to just take an average of where thrust is being produced over the engines and center that thrust, it's towards the right side, right? So in this case, we can just erase these small arrows and call them negligible for this purpose. Now if we were to draw a line backwards, and I guess I made the mistake of not drawing the CG, right? The CG is right there. Because the aircraft rotates about the CG, right? If this thrust is acting to rotate about the CG, it has this moment arm right here to produce the leverage. It's going to be this force multiplied by this distance across the CG to turn you. The right side here, this distance, is greater than the left side.
Gotcha.
It's a shorter moment arm because that center of thrust is also inwards, but it's inwards towards the fuselage, towards the CG. So even though they're producing the same amount of thrust, the right side has way more leverage to yaw the aircraft than the left side does. Hence, it's way worse if you were to lose the left engine because the right one is going to turn you stronger. Good?
Yep.
Sweet. So kind of keywords, because you guys will need to explain this in your own words when it comes to stage check or EOC. So your descending blade is producing more thrust because it has a greater angle of attack when the aircraft has any kind of positive angle of attack. The center of thrust produced by each propeller is rightwards of the center of the propeller, right? And your center of gravity experiences a greater moment arm to the center of thrust on the right engine than the left. Hence, the right engine will want to yaw you more aggressively than the left. And this is all for a conventional, same rotating direction aircraft. Make sense? All right, on to the next one. Anybody know it off your top of your head? What's that?
Asymmetric thrust. Or
Ace.
That's accelerated slipstream.
Accelerated slipstream. And then before we go into this one, I'm going to see if I can find a blue marker in the other room. So that's driving me nuts. Hey, Romy.
Anybody want coffee?
Wow.
Alex, get your power here, you know, your sugar.
I'm going to take notes. Like, I didn't do this for my class. Yeah. A blue marker. Do you have any?
There was
in here?
some in the other room.
Yeah, they have all the tiny ones, but they don't have any of the good expert ones. Oh, excuse me. I think there might be some in class 2. You have anything, Romy?
Yeah.
Oh, you do? Yes. Thank you. All right, we have blue and brown. Is everyone still in here? No one escaped? Our friend from Denison escaped. Accelerated slipstream is the next one. Accelerated slipstream. So I'm going to draw out an aircraft from a different view. That's the fuselage. Here are the wings. And we're going to say the airplane is flying into the board. Make sense? So once again, we can put propeller, propeller. Now, based off of P factor, they're all related. Everything trickles down from P factor. The right side of the propeller is producing more thrust, correct? How is it producing more thrust? How does the propeller achieve that at a very fundamental level?
Creating more lift.
The propeller's producing more lift, okay. How's it manipulating air?
So the air will spiral in the same direction.
Even simpler picture than that. A propeller produces forward thrust by doing what to air?
Just displacing it.
Pushing it backwards, right? It's that easy. Propeller produces forward thrust by pushing air backwards. Much like a wing lifts an aircraft up by pushing air down. Like fundamentals of aviation. You don't need to complicate it with Bernoulli, because I guarantee you that nobody in this entire campus really understands it to the full extent, right? The propeller produces forward thrust by pushing air backwards. So based off of that principle, it's pushing a whole bunch of air back, right? Where is that engine mounted?
On the wings.
On the wings. So where is it pushing air back over?
Your wing.
over the wing. And if you have more mass flow over the wing, what does it produce? Lift. Oh, okay. So now we tie all these concepts together. The right side of the engine is producing more thrust. So it must be pushing back more air than the left side, right? So if it's pushing back more air, the wing is producing more lift in that section than right here. It might produce a little bit over here. And same thing on the right side. The wing is producing more lift to the right side of the engine and less over there. And then the rest of the wing is relatively minor, right? You can just say something like that. You guys understand what I'm trying to draw out? The blue is lift production, and because the engines are so effective at pushing extra air over the wings, these parts of the wings are extra effective at producing more lift. Make sense? And then we can do the very same force balance. If we were to take the moment arm from the center of lift on the right side and the moment arm to the center of lift on the left side, this is about 1 marker length. This one's almost 2. The right wing, where its center of lift is located, has a lot more leverage to roll the aircraft out of control in the event that you have the engine failure. Once again, if the right engine fails, the left one still wants to roll you over to the right, but it has less leverage. So the left one's critical because the right one will have more authority to roll you out of control. Make sense? So summary on this one. The propellers induce airflow over the wings. They push air back over the wings. More airflow over the wings results in more lift. However, due to P factor, the right side of the propeller is more effective at pushing air back over the wings. So if we were to take the center of lift, the average amount of lift produced over the wing, that vector exists towards the right because P factor influences it towards the right. And now the right wing in a single engine operation is going to have more leverage to roll the aircraft out of control than the left wing would. Does that make sense to everybody?
Yes.
Sweet. Now, there's a tangent I could go on here, but we'll save it for tomorrow. I think that's just too much information at once. Spiraling slipstream. So once again, this is a byproduct of P factor. Right side of the propeller is producing more thrust. If it's producing more thrust, it does that by pushing more air back. Well, let me ask you, if you're pushing more back on this side than this side, how does it get out of the way? It has to go faster, right? There's no other way for air to get out of its own way. So if the air is moving faster to the right side of the propeller behind it, what do you know about the pressure? Lower. Good friend, Mr. Bernoulli. So you have slightly low pressure behind the right side of the propeller, slightly high pressure on the left side of the propeller. High is going to push towards low, and the slipstream, the prop wash, will move backwards and to the right. Excuse me. All right, so backwards and to the right. Now, in the case that the left engine is operating, that prop wash will move backwards and to the right and interfere with your vertical stabilator, your rudder, and your stabilator, right? That's going to give you more control authority, more mass flow over your control surfaces, more control. On the right side, it's just prop washing out into oblivion. It doesn't help you, but it also doesn't hurt you. So here's kind of a little bit of a mental shift. The first 2 conditions are ones that are going to hurt you because one engine wants to roll or yaw you out of control more than the other. This third one with spiraling slipstream, neither one wants to hurt you, it's just one of them helps you and one of them doesn't do anything for you. Make sense? So the left engine is critical because its slipstream interferes with that tail surface and helps you counteract the asymmetrical thrust. It yaws you in the left direction, which is opposed to the right turning force of the asymmetrical thrust. However, the right engine, this one didn't help you to begin with, so if you lose it, you didn't lose any benefit. Make sense?
Question not related.
Yep.
So with the Seminole, because we have non-conventional, both of the slipstreams are going to basically go towards the tail. Correct?
Exactly. Yeah, they both converge back here.
But because this is conventional, right, that right engine is rotating to the right. So that's why the slipstream goes off to the right.
Exactly.
So I just thought that was pretty cool how on the Seminole they'll actually both go inwards.
Yep.
To create control.
Exactly. And same thing with all of these elements too. In the Seminole, because it's counter-rotating, this is going to be the descending blade. So the center of lift is actually shifted inwards and they become equal. And the P factor is shifted inwards and they become equal. Everything's symmetric in the Seminole. So when you introduce the conventional, everything becomes unsymmetrical, and that's why you have all these pass factors. It's all due to the lack of symmetry.
Hopefully that didn't confuse anybody. Don't get confused.
Yeah, you got it? Any questions? Sweet. All right, last one is torque. Same thing based off of a private level. I don't know how these got moved. Interesting. I'll have to go and fix that in my presentation. Oh, I know. So I went and I had thrust logos everywhere, and I shifted the pictures to make room for the thrust logo, but I didn't move my X's. Whoops. Anyway, so Newton's third law, every reaction has an equal and opposite reaction. Both engines are conventional. They're spinning to the right. They're going to have an equal and opposite reaction to roll the aircraft to the left. So back to this airplane, we could treat it as a single. If the prop is spinning clockwise, the plane wants to roll counterclockwise to the left, right? That doesn't change when you put two engines on the right. Both of them want to roll the aircraft to the right, and the plane, or sorry, both of them want to spin to the right, and the plane wants to roll to the left. Now, if you lose your dead engine right here, your right engine wants to steer you and yaw you to the left, right? Its torque roll also wants to yaw and roll you to the left. So both of those compound and make your situation a lot more aggressive. Versus if you lose the right engine, that left engine wants to steer you to the right. However, that left engine's torque roll is acting towards the left. So even though the asymmetrical thrust wants to take you to the right, its torque roll helps balance it out to the left. So this helps you by balancing out the asymmetrical thrust, losing your right engine. Oh, sorry, I'm getting confused with which finger. Losing your right engine, you're going to be better off because your left one's still operating, is going to want to counter the asymmetrical thrust. Using your left engine, you're going to be worse off because your right engine and its torque roll both want to roll you in the same direction. Make sense? One scenario raises your dead engine and one drops your dead engine, and dropping the dead engine is bad.
So when we lose the left engine on a conventional, you're going to have all four of these factors that we talked about fighting against you. So you're going to have more lift generated on the right. You're going to have more thrust generated on the right. You're going to have less spiraling slipstream.
You're going to have no spiraling slipstream.
Exactly, right? So you're going to have even more less.
And then you're going to have torque roll from your operating engine in the direction that you don't want it.
So everything we just talked about is going to cause a rolling and yawing tendency.
Exactly.
With a left critical engine
Exactly.
missing. Yeah, that's insane.
Yeah, so you're screwed.
That's insane.
That makes a huge difference between flying a conventional twin and a non-conventional twin. You experience all these things in the non-conventional, but they're very dampened. They're minimized because they're always the good part. The conventional, you have the more aggressive one. So overall, to summarize, 4 factors that you guys need to have learned and understood in terms of what they are and how they impact the aircraft. P factor. Right, P factor, descending blade is getting a higher angle of attack, so the center of thrust is shifted out to the right. The right engine has a greater moment arm to yaw you out of control. P factor is a yaw tendency. Accelerated slipstream, byproduct of that P factor. If you're producing more thrust to the right of the engine, you're pushing back more air to the right of the engine. So more airflow on the rightward side of the wing will shift the center of lift towards the right on both wings. Hence, the right wing will have more leverage to roll you to the left. Accelerated slipstream is a roll tendency. Spiraling slipstream. Both of those prop washes move backwards and to the right of the aircraft. The one coming from the left engine helps you. The one coming from the right engine doesn't do anything for you. So the left engine is critical because that one helps you out. It's going to help you yaw and fight that asymmetrical thrust. And then the torque roll is the last one. Both engines are rotating clockwise, so they have a counterclockwise or leftwards rolling tendency. If you lose the left engine, both the asymmetrical thrust and the torque roll want to take you left. If you lose the right engine, the torque roll helps you steer left while the asymmetrical thrust wants to go to the right. They counteract each other. So easy way to remember, yaw roll, yaw roll. P factor, accelerated slipstream, spiral slipstream, torque, yaw roll, yaw roll. Any questions on that? Sweet, so that's aerodynamics. We're about an hour into class. We're going to transition into the next topic, VMC. All right, so getting into the Seminole, getting into any multi-engine aircraft, we're going to have a new set of V-speeds. Pop quiz. Which 2 V-speeds are marked on the airspeed indicator in the multi-engine aircraft that are not in a single-engine aircraft?
Blue line.
Blue line.
And red line.
Excellent. What are blue line? Actually, Nick, blue line. Chester, blue line.
VMC?
Blue line's VMC?
I don't know.
Brady, what's blue line? Austin?
Speed on 1 engine.
Not quite. Aiden?
Is it landing gear?
No. Ashley?
I was thinking it was the OSI thing too, or OEI.
Has something to do with one engine operating. Garrett.
Don't look at me. Minimum controllable.
There's a
Blue.
lot more numbers on that than I was used to.
All right, so blue line, single-handedly the most important airspeed of this rating. Blue line, blue line, blue line, blue line, blue line. It is your VYSE. VY as in best rate of climb, as you already know. Single engine, that's where the SE comes from. So when you lose an engine, you will have the best chance, you'll be in the best position to climb or maintain an altitude at your blue line. The second one is the red line. That is VMC. This is your minimum control airspeed, as in when you lose your critical engine, if you slow below your VMC, you will begin to lose directional control. Right? So it is the minimum airspeed where you can still maintain that directional control when the critical engine is inoperative. Right? Not to be confused, blue line is king. Red line's sole purpose is that you stay far away from it. Don't touch it. It's like when you were a kid at the park and you played lava on the wood chips, right? Just don't go anywhere near it. If you stick to blue line when you're single engine, you'll be able to climb, or at least maintain altitude, or at least minimize your descent. You're going to give yourself the most time in order to handle your situation and make it out safely. If you don't go anywhere near this, you'll be okay. But if you're maintaining this, you won't be anywhere near this. Make sense? So blue line, blue line, blue line. Don't touch it.
Question.
Yeah.
Do these lines change?
What do you mean?
The values of the lines change at all?
Within a specific aircraft?
Or maybe based on air density?
VMC is a dynamic speed, and we're going to go all into that in this presentation. Blue line does not. That is based on the aerodynamic characteristics of the airplane, how it was designed. Right? So we'll go through a couple other ones. VXSE follows that same naming convention. It's your best angle of climb with a single engine. Anyone know what this airspeed is in the Seminole? 82, very good. This one in the Seminole? 88, very good. Double eights, lucky number in Japanese culture. Hachi. So just think it's good luck. 88. VSSE. This is your single engine safe speed. Also 82 knots. So this one and this one are the same value. This is more so a number for the MEI, saying, hey, if we're going to practice any kind of simulated single engine stuff, I'm not even going to give it to you. We're not going to try it if we're below 82. Because we know that you guys are student pilots. We're not super proficient to respond in time, and we don't want to risk accidentally getting too slow or not having the control authority to deal with it. So if it's below 82, it's a bad idea. We're not going to do it. We need to gain some airspeed. That's the purpose of the VSSC. Make sense? 82 knots. VMC, we talked about that. We will continue talking about that. And then we have landing gear speeds, because now we have retractable landing gear. So VLE and VLO is your landing gear extended and your landing gear operational speed. Some airplanes have these as different numbers, as in you can extend your gear at a slower airspeed, but then you can leave it out and fly with it at a higher airspeed, or vice versa. For ours, they're both 140 knots. You can extend it and continue flying with it down at 140 knots. LR is the landing gear retraction speed when you bring it up. 109. So 109, 140. We'll talk about those airspeeds and why they're different and that kind of stuff when we go into systems. Any questions on anything we went over aerodynamics-wise or with these airspeeds? So yeah, red line, it's marked on the airspeed indicator. And that's not working for. In the spirit of Bill being in the classroom before we started, what's the VMC speed in a 777? What do you mean? I know it.
150.
I know it exactly. What's VYSE in a 777? I know it exactly. In fact, I know it for every single multi-engine aircraft. I'm that good. I know VMC for every single multi-engine aircraft. It's the red line. You get it?
Yeah, that's a bill.
Yeah, what's VMC in a 777? It's the red line. What's VYSE in a 777? It's the blue line. It'll be marked for you. All right? We went over this definition enough times that you guys understand it, right? We don't have to repeat it. Just make sure you study it and have it rehearsed in your own words, because that'll be something that you're expected to explain, at least simply, in a stage check or EOC. So where does this whole airspeed come from? It's a long story. You can find it published formally in 14 CFR Part 23-149. Now, they give this whole textbook definition. I've simplified it into my own. That's where you can find it. However, there's a big caveat. All of Part 23 was rewritten in about 2016. And that original regulation, Part 23-149, that defines what VMC is, no longer exists in your 2025 FAR aim. It's been replaced with a new version of the regulation. That's 23-2135C, which essentially, we'll kind of get into it. First, I'm going to explain to you guys what the purpose of this is and why a FAR even exists of it, and then we'll dig into why it changed and how that impacts you guys. So, kind of as Nick was alluding to, VMC is a constantly changing number. The ability to maintain directional control of your aircraft when the critical engine is not operating can change based on a lot of different factors, right? Your weight conditions, your density altitude, how much power does that operating engine actually produce if there's less oxygen in the air, right? That how high you are, how low you are will change that as well. Where is your center of gravity based on the loading conditions? What kind of configuration are you in? Do you have your flaps in? Is your gear down, etc.? What kind of power setting are you using on that operating engine? Right? There's a whole bunch of different things that can change when you're actually going to lose directional control. It's a dynamic number. Much, much different than something like a stall speed, which is fixed and you can climb up and down and change a bunch of different conditions. You'll always stall at the same indicated airspeed for the most part, right? So because VMC is changing so much, the FAA thought it was very important to standardize how people test for and establish what your VMC speed is in your aircraft. So to kind of backtrack, this Part 23-149 is where VMC is published, is structured. However, the whole Part 23 in general, that whole section of the FAR, and this is very important, is certification standards for light twins. So if you're an aircraft manufacturer and you're building a light twin aircraft and you want to get your type certificate, if Piper wants to get the type certificate data sheet that is FAA approved that this is a PA44, they need to follow all the criteria in Part 23 that applies to them. Does that make sense? If you're like a transport category aircraft and you're making something like that, a 737, you need to follow all of the certification standards in Part 25, right? But for our intents and purposes, the whole Chapter 23 certification standards for light twins. And this 149 is a very specific certification standard for certificating what that VMC speed is. Any questions there? So what they did in 149 is they outlined what VMC is definition-wise and then established a list of criteria, a list of testing scenarios that are going to be the worst case condition, so that when a manufacturer publishes their VMC speed, nobody's going to purchase the aircraft and find out that it was actually higher and get themselves into a VMC roll, loss of directional control, at a higher airspeed than what they thought or what they saw was published in the aircraft. Does that make sense? So overall, to recap that 23-149 and the modern day version of it, it's a list of testing criteria for the manufacturer to establish what the VMC speed is, so it's known and it can never really be worse than that. Got it? Now before we get into what all that testing criteria is, which you guys are expected to know, I'll go back to my original note that you won't find this 23-149 in your 2025 FAR aim. Because the FARs were rewritten, specifically Part 23 in 2016, they established a new certification criteria that's a little more lenient for light twins. And that's what this is, 23-2135C. You guys don't need to know that regulation, so I wouldn't even waste your time writing it down. Just know that if you went digging through your FAR aim right now, you wouldn't find 23-149, which is what you're looking for. The reason you're looking for it is because any aircraft will be certificated under the rule set that was present at the time that it went through its certification. So the Piper Seminole, which all of you will be flying, was certificated in the late 1900s. And at that time, Part 23-149 was active, so it followed that criteria for establishing its VMC and everything else along Part 23. Make sense? So even though the regulation changed, Piper didn't have to change the certification. But if you're Diamond, for example, and let's say you're making a new DA 66 or whatever the number is, and it's certificated in 2025, then they don't care about this, they follow that. You understand how that works? Sweet. So now let's get into the nitty-gritty of it. The first condition that they're looking at is the critical engine, which we just went over, is inoperative, and its propeller is windmilling. So you shut off the critical engine and you leave the propeller in the windmilling configuration. This is a breakdown of the different drag profiles based if you have a windmilling propeller, it's like a big dinner plate creating a whole bunch of drag. If it's still unfeathered but it's not spinning anymore, it creates a good bit of drag in its cross section. But if you feather it, you streamline it, it's relatively narrow, reducing drag significantly. Make sense? So obviously performance in your aircraft generally is going to go down when you lose your critical engine. You have half the horsepower and you've lost how much of your climb performance?
80 to 90.
80 to 90%. Good. More than that, you now have asymmetrical thrust introduced. So the airplane wants to yaw to the left. You have drag that's anchoring you down here, further increasing that leftwards yaw tendency. So you have more factors fighting against you in order to maintain directional control. It's going to be harder for you to maintain directional control. So in order to maintain directional control, you're going to need a lot more control force to do it, right? And how do you get more control force? You need more airspeed. You need more airflow over your control surfaces. So you need higher speed. Hence, your VMC, the speed at which you can still maintain directional control, is going to be greater because now you have to do all this extra work relative to a two-engine operation to do it. Does that make sense? So for each one of these criteria, we're going to talk about how performance changes and why, and then also what changes to a VMC speed given that condition relative to the opposite. Any questions on it? And before we go even further, I want to explain this caveat right here in the top corner. Low VMC and high VMC. Which one, I guess it's already ruined for you, but which one would you assume is better?
I love VMC.
Right, low VMC, why?
More wiggle room.
More wiggle room, right? But let me ask you this question. Imagine you had an engine failure on takeoff here, and you knew that you had a really low VMC speed. If you had the comfort, the peace of mind saying, hey, I have more wiggle room, and you started slowing down because you had that wiggle room, how's that going to impact you when you're this close to the ground? If you have more wiggle room to get closer to VMC, what are you getting farther away from?
Oh, best climb.
Yeah, you're getting farther away from blue line. So even though you have more wiggle room, you're losing wiggle room with the ground. And ultimately, that's what's going to get you in a bad situation. So low VMC, bad VMC really doesn't change. Just stay away from all VMC. All VMC is bad. Blue line is king. All right. Second one here is that up to 5-degree bank and 0 side slip condition that we introduced on the aerodynamics portion. So once again, you're gonna lose an engine and you're flying in a crab. You want to raise your dead engine so that you can fight the asymmetrical thrust of this one. It's going to align you with the relative wind so that you're now flying kind of diagonally but more aerodynamically. It'll reduce your rudder workload because you're transferring vertical component of lift to horizontal. You guys remember that from an hour ago? Right. So overall, aircraft performance is going to increase because you're increasing your aerodynamic efficiency, right? So if aerodynamics benefit, your aircraft performance is going to go up. If you have less drag, then the plane just has to do less work in order to fly straight and level. So there's less to overcome and more authority that you can put into maintaining directional control. So your VMC speed will go down. Does that make sense? You reduce the drag burden and you have more energy to maintain directional control. Hence VMC goes down. You could do it at a slower airspeed with slightly less airflow over your control surfaces to produce less force. Make sense? Now, caveat that I kind of brushed up on earlier is that bank angle is very, very effective for reducing your VMC speed because you're transferring that vertical component to horizontal component and the horizontal component is fighting your asymmetrical thrust. right? So every degree of bank can reduce your VMC by 3 knots of airspeed. Now I'm going to ask you guys the question, if that's the case, why wouldn't you just fly a 0 side slip, or why wouldn't you just handle a VMC, or sorry, a single engine condition with 15 degrees of bank?
Because we lose our vertical lift too, so if we're having to climb out or maintain altitude, we don't want to have that much bank because we could lose altitude or not be able to climb.
Yeah, or get into a stall if you go past your critical angle attack. Exactly. That, and when you're doing the test, they don't want people publishing unrealistically low VMC numbers in the event that you have some kind of aircraft that's very aerodynamically capable, right? So you bank over 20 degrees, you reduce your VMC by 60 knots. We'd be negative, right? Standard day conditions. This one kind of relates to density altitude. There's a twist on this one. So standard day conditions, what's the altimeter setting? What's the temperature?
15 Celsius.
Okay, so aircraft performance relative to a standard Texas day is going to go up, right? Because standard day in Texas, it's like 40 degrees Celsius, and we're above sea level. So if you go down to sea level, you cool off the temperature, you have more dense air, performance will go up. However, if you're learning multi-engine in some place like Alaska, and you're right by the sea, and you're at sea level, and it's usually 5 degrees Celsius, performance is going to go down if you get the increase of temperature. Make sense? So this one's relative to where you are. But for our intents and purposes, we're going to treat it standard Texas day. Aircraft performance goes up because we have better density altitude. VMC also goes up. Now I want you guys to pause a second and think, how does VMC go up if our aircraft performance increased? Doesn't more performance mean more ability to maintain directional control?
Yes and no.
All right, how so?
Asymmetric thrust.
Exactly. So it's very important to understand what kind of performance is increasing and where. So with better density altitude, there's more oxygen available for our engines. They're going to produce more horsepower. However, if you're only producing more horsepower on one asymmetrically located engine, it's producing more asymmetrical horsepower. And you're going to have to work harder to maintain directional control and counter it.
So there's 2 types of performance. There's the engine performance and then the aerodynamic performance.
So far that we've covered,
Correct.
but there's many more. Yeah, so it's important to understand what kind of performance and how it changes, because that's going to have a totally different relationship to VMC. It's easy to look at this and say, hey, we're talking about performance and we're talking about VMC for each one and tie them together, but they're not related, right? You need to understand this one to understand how it impacts that one. So note on this one, where do you think people test this? Where does Piper go to establish this test? Yeah, we're located in Florida. So it's 15 degrees Celsius there, they're at sea level. So really it's wherever they can find it. And in the event that they can't find it, they're probably allowed some kind of tolerance to get close enough and then extrapolate or interpolate their numbers from there. All right, trimmed for takeoff is the next one. So once you trim for takeoff, or I guess first off, what is universal trim for takeoff?
Neutral.
Neutral. So neutral trim for takeoff, does it change your aircraft performance?
Not really.
No. So does it change VMC? Not really. So why even put it in there?
Because you want to make sure that when you're testing to get those VMC numbers, that you are just in a neutral position.
Yeah, it's to kind of standardize the test for everybody and to level the playing field. Every aircraft different. Every aircraft has, nose down or nose up or tail heavy tendencies. And the FAA just doesn't want some kind of test pilot saying, hey, I know this plane's really nose heavy, so I'm going to load up my nose up trim to exactly this degree because I know I'm going to get the engine failure on takeoff, and then I can just sit back and sip my soda while it's perfectly trimmed out and I run the engine outflow. Not that he would do it any better, not that the aircraft would perform any better, it would just make it so much easier. So they just want everybody to test it from the same playing field, so neutral, neutral, neutral. Make sense? Okay, the next one is out of ground effect. Out of ground effect. And you know what? We make this a little more interactive. What happens to aircraft performance when you leave ground effect?
Goes down.
Why?
More drag.
More drag. Specifically what type of drag?
Induced.
More induced drag. Okay, so let me ask you this. If we've left ground effect and we are now producing more induced drag across our airframe, are we going to have a easier or a harder time maintaining directional control? Harder, right? Because there's more burden on the aircraft. We have to fight this drag, and now we have to fight this directional control as well. So is VMC going to be required to be higher or lower?
Higher.
Higher, yes. We need more airflow over the surface in order to fight that. Very good. So aircraft performance goes down, more induced drag on your control surfaces. VMC goes up because now you have to fight both the burden of the extra drag and the asymmetrical thrust to maintain directional control. All right. Next one will be maximum performance on the operating engine. So let me ask you, if you were throttle 50% on your operating engine and then you went throttle to 100, does your aircraft performance increase or decrease?
Decrease.
If you went from throttle 50 to throttle 100%?
Increase and decrease in a way.
I think your performance goes up. I like more horsepower.
Well, yeah, engine performance and thrust increases,
Yeah,
but aren't we going to see some sort of negative from that at the same time, right?
that comes with VMC, yeah. But performance-wise, we have more energy, we have more performance. Now, VMC, on the other case, that's what you're getting at. That gets changed in the opposite direction. If you have more power on your operating engine, you're producing more asymmetrical thrust. You're producing more of all those past factors that we just talked about. So you're going to need a higher VMC speed to maintain directional control and counter it, right? So more power, more performance, but also your VMC goes up because you need to do more to counter all that asymmetrical thrust. Make sense on that one? All right. The next one, I would argue, is the most difficult of the lot. It is flaps set for takeoff and gear up. No, flaps set for takeoff. Not flaps 0, not flaps 10, because this is a FAR that's written universally for all aircraft, and all aircraft have different flap setting for takeoff. So it's flap set for takeoff and gear up. Similarly, trimmed for takeoff. Anyways, let's break them down individually. We'll talk about flaps first, and then we'll talk about gear. Sound good? So flap set for takeoff, what is it on the Seminole? 0. Okay. Aircraft performance. How does aircraft performance, when you retract your flaps to 0, change?
Less lift or
We're talking about total performance.
decline faster.
What's that?
Decline faster, so less drag.
Less drag, so what happens to performance?
Increases.
Yeah, performance goes up. Right, it's important not to think about just lift performance, but just overall energy in versus energy out. You bring the flaps to 0, you reduce induced drag, you have more performance. Now, what would you think happens to your ability to maintain directional control when you bring the flaps up?
Probably.
You're going to have an initial decrease.
You think you'll have a decrease in your ability to maintain directional control?
I think increase because it's slicker, so I think it'd be better. An increase.
So it should be more maneuverable with 0 flaps.
All very good things. Where is the eraser? So when you put your flaps in, they generally exist about here. Is that fair to say?
Yeah.
Flaps produce more, what? Lift. And what's the byproduct of that? Drag. Drag. So does drag hold the aircraft back or does it push it forward? Holds it back. So if I were to put a center of drag for each one of the flaps, I'll draw an anchor to represent that. It'd be somewhere there. Relative to the center of gravity, that's resisting any kind of yawing tendency, right? So it gives you a little bit of stability. Now, if you lose an engine, you might ask, well, shit, if I have drag on one side and drag on the other side, one of them's resisting the operating engine, but then the other one's also resisting the opposite, so it probably balances each other out. It's neutral, right? The important thing to remember when we get the engine failure, left one is out, this one's still operating, and out of those past factors, accelerated slipstream is still a very real and strong one. So this prop is pushing back significant airflow over the wing and into this flap. So this flap is producing significant induced drag as compared to this one. So this engine wants to yaw you over to the left and roll you over to the left. However, that flap and its induced drag from all that accelerated airflow going over it wants to anchor you and fight against that yawing tendency. Does that make sense?
That was more so what I was talking about.
Yeah. So if you bring the flaps up, your performance increases because you've reduced drag, but you've also eliminated that element of stability. By eliminating the stability, you're going to have a harder time to maintain directional control, so your VMC speed goes up. Make sense? Any questions on that?
So VMC will go up with the flaps neutral.
Flap 0, VMC goes up because you've removed the stability that was helping you maintain directional control.
Alright, so is it preferable that we have flaps in?
That's a good question. What's the most important airspeed in multi-engine flying? Blue line. Do flaps help you with blue line?
No.
So do you want your flaps in or not?
No.
And that's why we have flap 0 for takeoff. So big reality shift here. In the single engine aircraft, our main priority is really performance because we don't have any kind of redundancy, right? So if you want to do a short field takeoff, if you want to do a performance takeoff, you're going to add flaps 25 because it's going to allow you to climb over less ground distance, right? In the multi-engine aircraft, that same physics applies. You can absolutely climb with less distance on the ground with flaps 25. At the risk that if you get an engine failure, you're going to hamper yourself from maintaining blue line and a significant single engine rate of climb. So the value of minimizing risk in the multi-engine is much greater than that short field takeoff performance. And that kind of same priority goes through everything we do in multi-engine. When we put in flaps for a single engine approach, when we put in flaps for takeoff, when we're doing performance calculations, how we plan our flights. Performance is a second thought. We already have that naturally due to having more horsepower. The first thought is minimizing the risk in the event of an engine failure. And that's why flaps are 0 for takeoff. You can do flaps 10. POH says it's perfectly okay. Section 4, takeoff. And then section 4 point whatever for short field takeoff. There's a fine note there, which I encourage all of you guys to read in the POH, that says if there's any concern for an obstacle or an obstruction, take off with flaps 0, right? And that's exactly the opposite of what you guys learned in private with the archers. If there's an obstacle, you put flaps 25 because you want to go over it, right? In the multi-engine, if there's an obstacle, you keep flap 0 because if you get an engine failure, you're going into it. Unless you're flap 0, you can maintain blue line and you'll be able to troubleshoot and get out.
About the single engine approach. So we're actually gonna do that.
Yeah, lots of times. You won't fly many 2-engine approaches, period.
Okay. I was just so how do you? Let's say we actually do the single engine approach for whatever reason we have to go around. What does that look like? Let's say our dead engine, simulated dead engine.
Yeah, I'm going to teach you how to do a simulated dead engine go around because it's a good piece of experience in the event that you actually have to execute one. But in the event you're like coming into Addison and they tell you to go around and it's more important to just be situationally aware and follow instructions, you resume both engine operations and proceed as that.
Fix it immediately.
Yeah.
Like let's say we're just going out practicing.
Yeah.
We're actually just gonna fix the engine, go around 2 engines.
I mean, you wouldn't need to fix it because it's all simulated with just a little bit of throttle. So all you have to do is add more throttle and everything's already configured to go.
Okay, cool. So
Yeah.
we're leaving the props forward
Yeah.
in that situation.
Props will be forward. We're never going to actually do a feathered single engine approach because that's a
that's-
concern.
Okay.
Yeah. So any questions on the flaps part? The second part is gear. What happens to gear when we bring it up? Or what happens to performance when, reduced drag, performance goes up. VMC, same scenario as flaps. The gear dropping below the aircraft produces keel effect. It wants to center out and keep the airplane straight and level. So if you remove the gear and bring it up, you're losing that keel effect. You're taking away that element of stability. So you're going to have a harder time maintaining directional control. VMC goes up. Does that make sense?
Science.
Yeah, so gear and flaps are both sources of stability. Yes, they are drag, but they are drag that provides stability. So when you bring them up to 0 or gear up, your performance will increase because you eliminated the drag. However, your VMC will also increase because you took away that stability. That's the summary. All right, two more. A is going to be aft CG. Aft CG. So what we know from private, commercial, you move aft CG, what happens to aircraft performance?
Performance increases.
Performance increases, right, because there's less tail down force required to keep the nose up, so less induced drag, hence you can burn less fuel, go faster. What happens with VMC?
You have less stability
Less stability, why?
because you have less control authority
Why?
because you have a shorter, per se, arm to the center of gravity.
Exactly, right. If you move your center of gravity backwards, you have less leverage from all of your control and stability surfaces, right? Vertical stabilizer, horizontal stabilizer, rudder, and elevator. All of these help you maintain forward directional control. If you reduce the moment arm to your stabilization surfaces, you reduce your aircraft's stability. They has less leverage, less moment arm to act on your CG if you get knocked out of straight and level, right? And then your rudder and elevator, you have less control authority for any given deflection angle of these because they have less leverage to work on your center of gravity. Does that make sense? So CG moves backwards, stability of the aircraft reduces, so VMC goes up. You need more airspeed to compensate for that shorter moment arm. Any questions on that one? Here's kind of an example, but that one's kind of messy if you ask me. Okay, last one, most unfavorable weight. Most unfavorable weight, and this could be different from aircraft to aircraft. So in our case, does anybody know what most unfavorable is?
Lighter.
Lighter. Why might that be?
It has to do with the vertical and horizontal components of lift, right?
Somewhat. We could make it even simpler though. Anyways, if you get lighter, what happens to aircraft performance?
It goes up.
Aircraft performance goes up. Yes. We don't have to explain why. That's pretty self-explanatory. If you get lighter, VMC, the speed to still maintain directional control, is going to increase. The way I want you guys to think about this is power to weight ratio. If you change the loading of the aircraft heavy or light, that engine is still producing 180 horsepower, 180 horsepower of asymmetrical thrust, right? If I'm producing 180 horsepower of asymmetrical thrust and I'm light as a feather, what's that engine going to do to me? Spin me around. If I all of a sudden gained 200 pounds and I was a little heavier, but this engine stayed at 180 horsepower, is it going to be able to steer me out of directional control as easy?
Not as easy.
No, it has a much weaker power to weight ratio. Hence, the lighter you are, the more easily the engine will steer you out of control, so you need more airspeed in order to manage it. You can break it down kind of science-y in terms of vertical and horizontal component of lifts. Let's say you have two aircraft exactly identical, they're both flying at 100 knots. But one of them is loaded to max weight and one of them is pretty much empty. If they're flying at 100 knots straight and level, the heavier one has a higher angle of attack because it needs to produce a greater lift vector in order to compensate for that gravity, the weight, right? So this one could have a lower angle of attack. If you start banking 5 degrees to the left, let's say 5 degrees to raise your dead engine, this one proportionally is going to have much greater horizontal component because it had a much greater vertical component. The much greater horizontal component is going to have more impact to counter the asymmetrical thrust than the lighter aircraft. So that's just kind of the physics force breakdown of how that power to weight ratio works. But in terms of your guys' explanation, if you keep it at power to weight ratio, then you're golden. Any questions on that?
So is that weight almost acting like the flaps as an anchor in the power to weight ratio?
So like a stability anchor, sure, but not in the same way.
I wouldn't necessarily tie them together. Because like this is creating a force that is acting to stabilize you.
Right.
Your weight isn't necessarily producing a force. It's just you need more force to overcome your weight. More force is required to move that weight.
Okay.
Yeah. So overall, the acronym we use to memorize what all this testing criteria is custom FAM. And then I drew out all of these arrows with some notes to help you understand how they go up and down. Highly, highly recommend that you guys do not memorize up and down arrows. That's the downfall of every student on the ground. Just understand the why of how performance goes up and the why of VMC, and then you'll get the answer no matter what. You can always troubleshoot it. When it comes to the oral on either the stage check or the EOC, you'll be expected to list off all of the names, and then your examiner will probably select 3, maybe 4, and ask you to go in detail and explain the performance element and the VMC element and the why behind both of those. So it's good to understand all of them because you'll never get caught unaware. Make sense? All right. I'm going to go ahead and take a screenshot and send this to all you guys because I don't like blurry images of screens that were captured by cameras for other screens. It's just silly in my opinion. So go ahead and open up your airdrops and I'll send it to you. Is everybody able to download the content that's on the Thrust website with respect to the checklists, the study guide, the weight and balance, that stuff?
The checklist, do you have like a singular page version? Because I know that pretty much every single checklist is like doubled up.
Yeah, it's just that way for printing purposes. But I mean, you could just download it on your iPad and then crop it and then re-upload it. Yeah.
Do all the MEIs here do stage checks and EOC?
Nope.
Specific ones?
Yeah, what do you ask?
I'm just wondering who does the stage checks and EOCs.
Awesome. So stage checks are really all over the board. Be like Zach Davis, Tyler Copeland, Humberto, Chris Burrows, or myself. And then for EOCs are strictly Chris Burrows, Humberto, and myself. So yeah, if you guys needed any motivation to listen what I'm telling you, the exam that I conduct, the evaluation that I conduct, if you listen to what I'm teaching in the class, you'll be in good shape. You will not be caught unaware. We don't have a will in here, do we? I think I might have accidentally sent it to Aiden. But all right, we're done with VMC. If you got this screenshot.
I do have one more question about this.
Mm-hmm.
So this is everything they have to test to determine what our VMC is going to be on our aircraft.
Mm-hmm.
After they do all of these tests, are they just taking one big average from all of these conditions? Or is it specifically standard day conditions, this is your VMC, trim for takeoff, this is your VMC?
So I have not seen the testing criteria, so I can't answer that definitively, but my way of thinking of it is like the worst place that you can get a VMC situation is on takeoff. Mm-hmm. And a lot of these you can pretty much do all in one. So you can take off, and when you do your VMC cut, let's say it's a mixture pull, you're not going to feather the engine, right? You're going to see what VMC is. You're going to do up to 5-degree banks, 0 side slip, because that's going to help you out. Standard day conditions, you can have that during your takeoff. You can be trimmed for takeoff on your takeoff. You can be out of ground effect shortly after your takeoff. You can have max power on the opposite rating engine shortly after your takeoff. Your flaps can be set for takeoff and your gear can be up, right? You can have an aft center of gravity. You load the plane out that way for takeoff, and you can have your most unfavorable weight in that element that you're trimmed for takeoff. So usually you just put all of these conditions into place and do one isolated and very tailored test, and you measure like, okay, this is my VMC. And then I imagine they do it a number of times and maybe tweak a couple things here and there just to make sure that that number is definitive. But this just helps them establish what that worst condition is. And then they run their tests and they get their number, and then that's what they publish. And I'm sure there's some kind of safety factor on there too. Everything in engineering always has a safety factor. So if they got like 50 knots, then they probably publish 57. If they got 45 knots, maybe they publish 52. But I don't know. I'm not Piper, and I've never designed an aircraft.
Right. Okay.
So what's the general rule of thumb in regards to windmilling versus feathering, engine out after takeoff, in regards to TPA? I saw something about that.
So that's all going to be part of the takeoff briefing. That's 4 different scenarios, and it lists on how to do them. So we're going to go over that tomorrow. Yeah. Yeah, you're leaning towards more fuel efficiency, right? So kind of overall, to sum it up, in a little crisper terms, it allows you to change the configuration so that you can use the engine for what you want to use it for the most efficiently, whether it's max performance for a takeoff or max fuel economy in the cruise, right? You have all this flexibility. And the analogy I love to give is that the constant speed propeller is almost identical, at least purpose and function-wise, to the gears on your bicycle or the gears in your car, right? So if you go full RPMs, full forward, it's like selecting gear 1 or 2 in your car. If you're about to take off and climb, or if you're stuck on a hill in your car or on your bike and you want to start moving forward up the hill, you're not going to select your 4th gear or your 5th gear because you start pedaling and it'd be so dang hard to get the pedal down that you break your legs, right? Same thing with the plane. If we had our props selected really, really low at like 2,000 RPM and we try to take off, we're putting so much stress on the engines. They're just like, inefficient. Versus we're on takeoff, you select gear 1 and you can spin out your wheels. The engine can spin really hard and it's not, chugging away at anything too much because the angle of attack is relatively low. So it allows it to get less of a bite of air so that it can spin faster and overall get more bites of air, and then use the maximum amount of power available, right? I think a lot of people miss that point of it as well. So this isn't identical to our engine, but it's, again, a trend. This right here is going to be RPM, and this right here is going to be horsepower. At 0 RPM, we're producing 0 horsepower. At like 1,000 RPM, we're producing a percentage of our max horsepower. But right here, at 2,700 RPM, we're producing 180 horsepower. If you have your props stuck at like 2,000, or if you're on your hill and you're in the 4th gear of your bicycle and you want to start climbing and you can't even get your feet turning, you're at 0 RPM. You're not really using any power, right? The faster you spin, the more power you're able to use. Hence, props full forward. Make sense? The way it achieves that RPM is by varying the angle of attack on the propeller. So the comparison I like to make here is in the Archer and the Cessna, whatever you're familiar flying, if you're doing a short field effort and you're holding on the brakes and you go throttles full forward, what RPM are you getting?
Like 24.
I think if you're lucky, you're probably getting 23. Why is that?
No relative wind.
Yeah, no relative wind. And the blade is fixed. It can't change. So like the blade or the engine physically can't turn that blade to take that big of a bite of air. It's just too much work. The engine doesn't have that much power to spin it at that RPM. So you get stuck somewhere in this range where you're only producing 160 horsepower to spin at 2,300 RPM. It's inefficient. You're not using the full 180 horsepower. This is where the constant speed prop comes in. You can slightly reduce your angle of attack so it's a little less of a bite of air. That way you can spin faster and you can get higher into your power curve. This way, even though the angle of attack's a little less, you're still spinning much, much faster. You're getting more bites of air over time and producing more thrust. Make sense? And then the exact opposite is true of cruise. If you're in a single engine, the Archer or the Cessna, and you're full throttle at altitude, what's going to happen? It's going to be 2,700. You're going to start overspeeding it. And do you need 180 horsepower to do 125 knots and burn whatever that fuel burn rate is, 14 to 13 gallons per hour? No, it's really silly. It's inefficient. You get diminishing returns. You'd much rather fly here at 2,300 RPM and do, instead of 120, maybe 115 knots, but you get way better fuel economy using 160 horsepower, right? So you guys kind of understand that relationship? The constant speed prop is like the gears in your car. It allows you to operate in different conditions, use different conditions of the engine based on how you need them. Full power available for takeoff, best fuel economy for cruise, and everything in between. Any questions? You guys pretty much know that. That's essentially what Garrett's been referring to with the relative wind. The faster you're moving through the air, the more attractive relative wind angle the propeller has, or rather less of an angle of attack. It's like the corkscrew analogy. Propeller moving through the air is like a screw moving through a solid material. It's going to pull itself in as you twist it, but it needs to move forward and backwards. If you keep the screw steady in the same position and try to twist it, it's not going to turn anywhere. Propeller works very similar. There's the bike analogy. So if you're going up a hill, low gear, high cadence, so that you can climb the hill. And the prop, you go low pitch, high RPM, so you can use the max takeoff available. In the bike example, if you're rolling with plenty of momentum, and you're just straight and level down the road, you select the high gear because you can move your legs more slowly, more efficiently, but still maintain your speed. Same thing, high pitch, low RPM and cruise. You can keep your speed up, but you're using less fuel burn. We already talked about the mechanism. It achieves all this by just varying the blade of the propeller. Now, I told you guys about that comparison that we're going to make, this trend that we're following through all of the topics. Failure mode analysis. There's a very important difference between the constant speed propeller in a single engine and a multi-engine, and it all has to do with the failure mode. Right, so in a single engine, if you have a catastrophic loss of oil pressure, because oil pressure is ultimately what causes the blade to change, what would you want your blade to default to in a single engine?
A low angle of attack.
Low angle of attack, right? Because if the engine's still turning, you have a low angle of attack, at least you can climb or descend. If you're stuck to like a feathered position, you'd kind of be screwed, right? In a multi-engine, on the contrary, If you were to have some kind of problem with one of the engines or the oil systems in one of the engine, would you want high angle of attack or low angle of attack? High angle of attack, yeah, you would want it to go to complete feather because you have another engine. You just want your inoperative one to get the heck out of the way and reduce drag. So that's the main difference. By default, each one of these systems is designed to respond differently in its failure mode, whether it's a single engine or a multi-engine. So if there's no oil pressure, there's no control input from the pilot, in the front of the hub there's a mechanism that helps this default condition, right? And from here on out, we're just going to talk about the multi-engine, where the default in the failure mode, if you lose oil pressure, it goes to the full feather position. Clear? So this is the hub of the propeller if you take the nose cone off. This is a cylinder within it. Can you kind of see how this picture represents this reality? In the front is a nozzle, which corresponds to this. You can attach the nose into the nozzle, or sorry, you can attach a hose onto the nozzle and fill it with a nitrogen gas. Inside the cylinder is a piston and a chamber. This chamber is filled with the nitrogen gas and it pushes against that piston. The piston acts on a shaft which is geared to the propeller to make it rotate one way or another, right? So both this nitrogen pressure wanting to expand and push the piston that way and this spring acting to push the piston that way is what default sends that propeller towards a high angle of attack or a feather condition. So if you have any scenario where you cut oil pressure out of the engine, the nitrogen and the spring will default feather it. Does that make sense? Okay, from there we can start introducing the oil pressure. We do this primarily with our prop lever in the plane. There's a system here. It's like a little black box. We call it the governor. The governor has flyweights in it, but we'll get to that in a little bit. That's actuated by our lever. So if we move our lever, it manipulates this valve. It's called the pilot valve. And the pilot valve controls how oil is flowing into or out of the hub. Right? So if we want to reduce our angle of attack, we need more oil pressure to go in there and fight against that nitrogen and spring trying to feather it. If we want to increase our angle of attack, we need to take out oil pressure so that the nitrogen and spring can take over. Make sense? And we adjust that pilot valve that changes that relationship with our blue lever in the plane. So memory aid for you guys to understand how it works. If we move the lever forward, then our oil pressure goes forward into the hub. And that sends RPM forward as in upwards to a higher RPM. So lever forward, oil forward into the hub, RPM forward as in a higher number. Any questions there? The exact opposite is true. If you move the lever backward, it moves the pilot valve into a position that allows oil backwards out of the prop hub to allow RPM to come backwards down. So lever backwards, oil pressure out, RPM down. Make sense? So one little caveat is that this lever doesn't directly lift the pilot valve up or down. The lever is attached to a metal cable, and that metal cable is attached to a disc, right? So if you see right here, there's this nut, there's this black cable that goes across, and it's attached to the disc. So when I move the prop lever forward, it rotates that disc, and it adds tension to the spring. The spring is what's attached to this valve, and based on the spring tension, it sets the set point of the valve position, right? So lever goes forward, it turns the disc, adds tension to the springs, and adjusts the valve. And that's what manipulates the oil pressure, the position of that valve. Make sense? It's called a pilot valve. Any questions on that? Overall summary, lever forward, oil pressure forward, RPM forward. Lever backwards, oil backwards, RPM backwards. The lever sets your RPM by setting the position of the pilot valve to manage the oil pressure. Now, if the lever sets your RPM, the flyweights are what keeps your RPM there, right? The lever sets your RPM, the flyweights keeps your RPM there. So flyweights are these little L brackets. They spin in a circle around the pilot valve. They're geared to the propeller shaft. So however fast the propeller is moving, the flyweights move at the same speed, right? They behave on centripetal force because there's a pivot joint on the L brackets. So if the prop starts to spin too fast, faster than what you set it, the flyweights are going to start bowing out. And you can see my thumbs, like the L brackets, they raise. And they're going to raise that pilot valve and allow the oil pressure ratio to change and make a small adjustment to the angle of the attack of the propeller to reduce the speed. Right? So if we're too fast, the flyweights will bow up. It's going to raise the pilot valve. That's going to allow some oil to come out and let the nitrogen and spring take over to increase the angle of attack. If the angle of attack's increased, the prop has to take a bigger bite of air, more drag, more workload. It'll slow down and come back to the set point. Make sense? So a good way to kind of put this into real practice how it works. Let's say we're flying straight and level, we're just cruising, and we set our RPM to 2300 with the lever, right? We pulled the lever back and we set it at 2300. If we were just sitting around and we didn't touch the quadrant, we didn't change our power setting, we started pitching up by pulling back, naturally, the engine's going to want to slow down, right? So you're going to pitch up, the prop will, for a moment, start slowing down, so the flyweights will bow in. It's going to move that pilot valve, which will allow more oil pressure into the hub. It'll reduce the angle of the attack of the propeller slightly to allow it to slip more and catch back up to that 2300. And it's making these constant micro adjustments on the valve in order to maintain the RPM by making those micro adjustments to the prop. Does that make sense? So yeah, overall, the levers set your RPM and the flyweights help keep it there. They all manage oil pressure in and out. Any questions?
Are there any limitations to the governor in regards to your desired RPM and pitch changes? Will it
Pitch changes, no, but RPM and manifold pressure, yes. We'll talk about that at the very back of this. All right, so we have a very special addition to our prop system here called the unfeathering accumulator. And the entire purpose of this is because we're a trainer aircraft and we go up in the air and shut off our engine and feather the propeller and restart it again multiple times per day, if not per flight, right? If we had to totally shut down and secure an engine, how would you get it started again? On the ground here, yeah, you use the starter, but if your prop is full feathered and now you have relative wind that wants to keep it full feathered because it's streamlined, you imagine how hard that starter has to work to turn it against it? You'd probably be breaking starter motors left and right. And then Mike from maintenance would walk on over here and he would smack you silly because you're running up his bill. Right? So this unfeathering accumulator helps us restart the engine without using the starter. It behaves as a reservoir. It's quite literally a cylinder made of stainless steel that just looks like a big stainless steel can. On one side of it, there's nitrogen gas again, which is compressible. There's a cylinder in the center that moves up and down. And on the top side, it's open to oil from the engine. Because oil is a fluid, it's not compressible. So it's very difficult to store pressure with it. Gas is compressible, so it's easy to store pressure because it wants to expand. Make sense? That's why they use nitrogen. It's also very thermally stable. Anyways, as the engine's operating and the oil pump is working on the engine, it's going to be pumping oil into this cylinder. There's a special valve here called the ball valve. It's essentially a one-way valve, as in you can see the spring down here. If oil pressure is higher here, it's going to push the ball down against the spring and allow it to flow into the container. If this oil pressure were ever to cease and non-exist and this oil pressure was high, the nitrogen wants to expand, it pushes the piston up, it pushes the ball valve up and the spring expands and it seals this off. You see how it works? So it allows oil in under pressure, but it doesn't allow oil out under pressure. So the function of this is as we're flying around, we're in cruise and the engine's running fine, we're constantly putting oil in there and storing it. And then when it comes down to run our entire secure checklist, we cut the prop to feather, we cut the mixture, boom, oil pressure is gone. This wants to expand, the ball comes up and it seals it off. So even though oil pressure went to 0 in the engine, we have this little reservoir of oil stored under that nitrogen pressure, right? Then we fly around, we do all of our, secure stuff, and then we try to air start the engine. So we start turning everything back on. We move the prop lever to full forward, and that opens up a bypass valve around this one way that releases the oil pressure. It allows the nitrogen to expand. It moves the piston up. It pushes the oil back into the governor and sets the propeller slightly unfeathered, right? It unfeathers it, and then the relative wind catches it, and then it begins windmilling. So now if the relative wind is windmilling the propeller, it's turning the crankshaft, it's moving the pistons up and down, and that's pumping oxygen through the engine. So if you have oxygen going through the engine, and then we start putting our magnetos on, we have oxygen and spark. And then if we start feeding in our mixture, we have oxygen, we have spark, we have fuel, we have combustion, the engine starts running again. And there's no need to break a whole bunch of starters. Does that make sense? So that's the whole purpose of it. It stores oil under pressure while you're flying so that when you secure the engine and you want to air start it, you can unfeather the prop, get it windmilling, and nicely start the engine without breaking starters. Any questions on it?
This happens automatically.
Automatically, yeah.
So there's no switch or anything that we need to actuate
Nope.
in order to get it to do it.
This is what it looks like. So here's the engine. This is the fuel tank on the back of the nacelle. So if I was standing right here, I'm pretty much looking at the engine from the prop. It lives on the back wall behind the engine on the firewall to the fuel tank. There's the little nozzle for the nitrogen. The piston lives somewhere in there, and then has the oil line that goes over the top of the engine into the governor.
So, like, let's say we really do have an emergency. Are we just automatically going to go to, like, single engine and keep it there? Or once we have everything secure, are we going to try to start that other engine up again?
It depends on what the emergency is, yeah. And we'll talk about that very much tomorrow. So, fourth and final point. First one's the lever, the second one's the flyweight, the third one's the unfeathering accumulator, the fourth one is this anti-feather lock pin. So within that front hub, and note that hub rotates with the propeller. On the inside wall of it, there's a spring and there's a little ball. So as that hub's rotating, that ball experiences centripetal force and it wants to fly outwards and it compresses the spring. If the prop hub ever slows down, then that spring wants to expand and it wants to send the ball inwards, right? So this pin, this ball pin, works on centripetal force. And there's a slot right there on the shaft that moves backwards and forwards and sets the pitch of the propeller. This whole system is made so that when we shut down the aircraft, when we're done flying on the ground, it does not fully feather the prop. Because if you had to start over the plane every single time with a full feathered propeller, again, you would be very much stressing out the starter motor. So this pin is designed that when that hub is moving less than 950 RPM, it's going to fall into the slot, the groove on the shaft, and lock the propeller into a lowest angle of attack position so that when you kill the engine and the oil pressure goes to zero, the prop doesn't default to feather. Does that make sense?
Yeah. What's keeping it from not doing that in a engine out situation?
The relative wind is going to be windmilling your propeller way faster. Yeah, like if you have throttles idle, or even if you cut the mixture, the relative wind is spinning your propeller at like 14 to 2,000 RPM.
So how come in a engine out scenario the prop feathers by itself?
It doesn't. You have to pull the lever all the way back to feather it.
So with the oil missing, as long as if we want to feather during an engine out, as long as we move the control back, it will feather.
Yeah. So here's the case, right? If you're flying around, if you go throttle idle, you still have 2,000 RPM because the relative wind is spinning that propeller like a windmill. If you're on the ground and you go throttles idle and props full forward, throttles idle, you don't have a lot of power, you don't have a lot of oil pressure being maintained, right? So the props are working with very little oil pressure and little power. If you're demanding props full forward and full RPM, it needs to send all the oil pressure available to try to reduce the angle of attack as much as possible. And that's going to send the shaft all the way forwards into the position for this pin to lock in. So throttles idle, props full forward is less than 950 RPM. That's the tuning point. The pin will not lock in below 950. So you're below 950 because you have so low power. The pin falls in even while it's still rotating so that when you kill the engines, it gets locked into place and it doesn't feather. In the contrary, if you're cruising around out here in the run-up area, and let's say you add enough manifold pressure that you're at like, I don't know, 1250 RPM, and then you just kill both of the mixtures. 1200 RPM and props full forward is probably giving you some kind of angle of attack. Well, it might actually fall into place. But if you were to go, let's say, like 1200 RPM and move the prop levers back to a point where you were demanding a higher angle of attack, and then this slot was moved backwards and the pin wasn't in place, if you stalled out the engine there, it would default to feather and you'd be stuck. The point of this scenario, though, is this pin is designed so that it's very difficult to get the propeller to feather unless you're trying to. Like, you would have to actively go out into the run-up area and set your manifold pressure to a certain setting and start pulling the props back to a certain setting and then pull the mixtures out and stall the engine, or stall the engine with the props in order to get it to feather on the ground. Like, it'd be tough. All right, so props on top. This is kind of the operational procedure that we follow. I had a hard time understanding this when I was in multi, so I like to teach you guys. This is just an order of operations for when you're flying the airplane, because we have both manifold pressure, which is the black levers, and prop controls, which is the blue levers that we're changing in flight. So when we're in a cruise straight and level, we configure the aircraft in what you call 23 squared, which is going to be 23 inches of manifold pressure and 2300 RPM. And for all intents and purposes for this procedure, we only care about the first two digits of each one. And that's why we call it 23 squared, as in 23 and 23. We don't care about the zeros and we don't care about the decimal places. So scenario, let's say we're in cruise and we want to configure for a cruise climb. We want to go from 23 squared to 25 squared. The way we're going to keep props on top is by making sure that the prop number is always on top, as in a higher value than the throttle. That's all it means. Higher value for the props on top of the manifold pressure. So going from 23 squared to 25 squared, you're going to do your props first. Props will come from 23 to 25 because 25 is a greater number than 23. They're on top, you see? And then you bring your manifold pressure up to 25 to match it. That way they're both the same. If you were to do the opposite, you go first manifold pressure. Well, now your manifold is on top because 25 is greater than 23. You're going to overstress the engine. Imagine like you were climbing a hill and you selected the fourth gear and your legs just can't do it anymore to the point where you don't have the muscle to keep turning and your bike comes to a standstill. That's kind of similar to what this is. If you put manifold pressure on top and RPMs lower, you're putting a lot of stress on the engine. You're demanding huge torque output to drive that high angle of attack. Make sense? Opposite scenario, if you're coming here from a climb configuration to level off in a cruise, if you want to go from 25 squared to 23, you're going to move your manifold pressure down first, so that manifold's 23 and props still on top on 25, and then when that's set, you'll bring the props back down to match it. This way the props are always on top. Is that clear?
Yeah, question about manifold pressure
Yep.
versus RPM. So RPM is
Yep.
that is physically changing our blade angle to get the desired. Manifold pressure is basically like how much air we're letting pass the throttle body into the engine.
Mm-hmm.
Okay, I just wanted to clarify.
Yeah, and
Kind of helps people understand the difference between manifold and...
oxygen is directly proportional to torque production in terms of internal combustion engines. So the more manifold pressure you have, the more oxygen you're allowing into the engine, the more torque the engine is producing. So if you have more torque, you're able to spin at either a faster RPM or you can spin the same RPM with a higher angle of attack. Make sense? So manifold pressure is pretty much how much torque your engine is producing, and then the torque multiplied by the speed that you have selected is how much power you have. Make sense? That's into the weeds. Any questions? The constant speed prop. All right, landing gear. We'll take a short break after this one. So there's a phrase that I believe comes out of our study guide and also comes out of the POH that describes our landing gear. I really don't like it because half the time people repeat it to me, they don't actually have an understanding of what it is. So we're gonna state that and then we're gonna dig into the what. Make sense? So our landing gear is electronically activated and hydraulically actuated. That's the phrase that I'm not so much of a fan of. So let's break it down. Electronically activated. It's activated with electronics. We have a switch in the plane. You toggle the switch, it sends an electric signal to an electric motor, and that electric motor starts spinning. right? On the shaft of that electric motor is a hydraulic pump, and that hydraulic pump pumps hydraulic fluid into and out of different reservoirs and cylinders to actuate the gear, hydraulically actuated, right? Electronically activated, electronic switch, electronic motor. The motor, electronic motor runs a hydraulic pump, and that is the hydraulic actuation. Make sense? Before we get into that even, we're going to talk about the V-speeds. So landing gear extension is 140 knots. Landing gear operation is 140 knots. Nice that those two are the same. However, landing gear retraction to bring your gear back up is 109. So why do you guys think that that speed is different? You have to be slower to bring the gear up than you do to bring it down.
Because the hydraulic pressure in the system has to fight the forces outside of the airplane, like the relative wind.
Exactly, right? So if you're flying along, the hydraulic pump, one, has to fight against the relative wind. So 140 is what Piper determined is going to be enough that it doesn't overstress the hydraulic pump to bring that gear outwards into the relative wind, right? And the exact opposite is true on retraction. When you're bringing the gear in, all of that relative wind is assisting the gear to come in. And if you're any faster than 109, you now have the hydraulic pump to help the gear up, and you have the relative wind that wants to slam it into the plane. So you don't want it to be too strong. There is no hole. Interesting. But does that make sense, right? You don't want to, one, overstress the hydraulic lines to bring it out by requiring too much pumping force, and you don't want to slam the gear into the carriage from going too fast when you bring it up. And that's really where the difference in these speeds come from. How do you operate it? We already talked about this electronic switch. It looks pretty universal in all planes. Most part, it looks like a wheel, like your landing tire, and it moves up and down. Note, when you guys get in the sim, for your first sim, you can just toggle that thing up and down, slap it up and down. In the plane, you have to pull it out and up and then back in. You don't actually have to go back in, a spring will pull it, but if you want to move it, it's out and down or out and up, right? It won't let you just slap it up and down. If you move that switch, it activates the electronic pump, and that pumps hydraulic fluid under pressure into the cylinders that actuate the gear. It has a 6 to 10 second transit time to cycle from either gear down to gear up or vice versa. Important thing here is if you accidentally make a gear selection that you didn't mean to make, and you will, it will happen in training, wait for the cycle to complete before reversing it, right? So gear down, 6 to 10 seconds, you got 3 green in the mirror, verified it, then bring the gear up. Make sense? If you just immediately switch it back, it's effectively like driving your car 10 miles per hour in reverse, and while it's still rolling in reverse, slamming it into first and hitting the gas. I mean, there's no transmission in there, but the hydraulic equivalent will similarly hate it.
Say we accidentally bring the gear down, traveling too fast. In that situation, yeah, you let it cycle, but you're not just going to leave the power where it's at, right?
Yeah, you would
Shock
reduce
everything.
power and try to slow it and gently pitch up to bleed off the airspeed. Yeah.
Okay.
I mean,
Just to make the
it's difficult to go faster than that.
Okay.
Like, you'd probably have to be in a nose down descent with 25 squared, very high power settings to get to 170-ish. Normally, if you're cruising straight and level, even at a pretty aggressive power setting, you're at like 150, 155. At that point, it's very easy to bleed off, yeah. All right, so how the hydraulic system works, these 3 cylinders here on the diagram each represent a cylinder for your respective landing gear. Right main, left main, nose gear. So when you move that switch and it activates the electric motor and the pump, it's pumping hydraulic fluid into the cylinders. Rather, this picture here is showing you the reverse. And I'm slightly getting ahead of myself, so let's backtrack. Before we talk about cylinders and pump pressure going up and down, let's go back to our favorite theme, failure mode analysis. If you have a failure in your hydraulic system in the landing gear, what do you want the default condition to be?
When you lose pressure, down, gear down.
Yeah, when you lose the pressure, you want the gear down so that you can come back in to land safely, because it would suck if you had a failure that you had to belly up the plane. Like, I don't think anybody wins in that scenario. So, by that design, if there's a failure, the hydraulic pressure is released, the gear comes down. And the opposite of that, hydraulic pressure is what keeps the gear up, right? So we're going to start in this diagram because it's the most simple. 3 cylinders. The red identifies hydraulic pressure being pumped into the cylinders, right? So the motor spins, it pumps hydraulic fluid out of the reservoir. Each one of those cylinders is attached to each leg of gear. The hydraulic fluid gets pumped in. It raises a piston within the cylinder. As the piston raises, it's attached to a linkage, and it brings the gear up with it, right? So gear selector up, electric motor turns, pumps running, hydraulic pressure goes up, raises the piston, gear gets up, cylinder closes off, and the hydraulic pressure is maintained in that cylinder to keep the gear up. Pretty straightforward. Make sense? So our hydraulic pump is reversible. When you select gear down, that electric motor turns on, but now in the opposite direction, and the pump's spinning in the opposite direction. So it helps drain fluid from the bottom end of that cylinder. Not only is it helping drain fluid, gravity is now dragging the gear down. There's a series of springs attached to the gear legs that help pull them down and lock them in place as well. So the relief of hydraulic pressure, gravity, and springs are what bring the gear down. On top of this, there is a top loop that comes into the top of the cylinder. So when you go gear select down, not only does it help drain hydraulic fluid from the bottom, as if I were to open the cap here, it drains the fluid out, it also pumps fluid into the top to help push that cylinder down. Make sense? So all in all, to kind of decipher the diagram for you, this is the reservoir, which lives in the back of the plane that the hydraulic fluid is located in. These 3 cylinders are for each gear leg. To keep the gear up, hydraulic fluid is pumped into all the cylinders. To keep the gear down, the pump spins in reverse. It drains out fluid from the bottom of the cylinders. It drains out fluid from the bottom of the cylinders and simultaneously pumps fluid into the top of the cylinders to drive the piston down and the gear down with it. Also aided by springs and gravity.
So naturally it wants to be down.
Naturally it wants to be down.
Force it to be up.
Exactly. Naturally it wants to be down. In the event that you had some kind of hydraulic pressure loss or failure in the motor, it will come down and you can land. Any questions on that? All right. So along this system, this is just a screenshot of the reservoir on the bottom. We have a series of valves that help manage where the flow of hydraulic fluid is going. So first one is pressure relief. Imagine a scenario where your gear selected up and the pump just kept running. It never turned off. It would just keep producing pressure and keep trying to feed hydraulics where it's already full. So there's a series of valves that are tuned with springs that allow a bypass into the reservoir if it ever exceeds a certain pressure. This way you're not overstressing the lines or damaging anything. There's a series of thermal relief valves that deal with changing climates. As we fly around, temperatures change a lot, and as the temperature of hydraulic fluid changes, its viscosity changes as well, right? So lower temperatures, viscosity decreases. It gets more thick, like a syrup. Higher temperatures, viscosity increases. It becomes more fluid, like a water, and there's an associated pressure change. So that thermal relief valve acts very similar to relieve pressure due to that thermal change. And then there's a shuttle valve. The shuttle valve here closes off the top and the bottom loops for that pumping circuit, right? So here's the shuttle valve. What this is effectively doing is if you want to bring the gear down, it is making it so that there's no way hydraulic fluid can go in and pump up the cylinder. It can only drain it, and hydraulic fluid can only go to the top of the cylinder to help push it down, and vice versa. If you wanted to bring the gear up, it's going to close off this top one to make sure that there's no hydraulic fluid on top of the cylinder, keeping it from being pumped up if you want to bring the gear up. Make sense? So the shuttle valve just works to open and close one or the other side of the loop based on if you want to bring the gear up or down. So 3 valves: pressure relief, thermal relief, and shuttle valve. In terms of indications, all of our planes are equipped with the G1000. So the G1000 will be the primary indicator of if your gear is down or not. Not to mention the mirror as well. If you look out the window right on the engine nacelle, there's a little circular mirror. If you look at it, it's angled perfectly so that you can see if your nose gear is up or down. There's no visual indication for the mains, just the nose gear, right?
We could just pull over and check.
In the air too, right? So 3 green is going to be your landing gear is down. 3 black, your landing gear is up. 3 hash marks, your gear is in transit. And 3 red means there's some kind of disagreement between the sensors and there's something wrong, right? It's pretty self-explanatory. In the old school one, you used to have these actual lights and sometimes a bulb would burn out. So you'd select gear down and you'd get 2 green and 1 was dim. And you didn't know if it was an error or if because the light was out. So you'd unscrew this light and unscrew that light and swap them and make sure you had 3 green. Yeah. Gear position indicators. This is essentially how the system knows where the gear is at a given point in time. So there's 2 of them, very simple. An up limit switch to tell you when the gear is up, and a down limit switch to tell you when the gear is down. The up limit switch lives up inside the gear carriage. You won't be able to see it unless you go over to maintenance and you're lucky and the plane's on hydraulic jacks. Otherwise, you just can't stick your head up there far enough. Anyways, it's an interference switch. So as the gear comes up, it triggers that switch, and then you get the indication, okay, the gear's up. All 3 legs come up and they trigger that switch. You get 1 limit switch, 2 limit switch, 3 limit switch, 3 black, the green is, or sorry, 3 black, the gear is up, and the pump turns off. The opposite is very true for the down limit switch, right? This picture could be a little confusing. This right here is a squat switch, which we'll get to. The down limit switch is almost in line with the spring. It has this plate here that interferes with the trigger right there. So when you bring the gear down, right, it comes down and it clicks the switch. And you get 1, 2, 3 limit switches triggered, 3 green, the gear is down, the pump turns off, the cycle's complete. Make sense? And if there's any kind of disagreement, let's say you have 2 up limit switches and the 3rd one's not quite triggered but the pump's still running, that's where you can get a red indication because there's a disagreement. All right, this one on the gear leg is called the safety switch, or AKA the squat switch, and its sole function is to make sure that you don't gear up the plane. These 2 pictures are of the same strut. The one on the left is with the plane sitting on the ground. The one on the right is with the plane jacked up by its wings. So this gear is hanging freely as if you were in flight. Make sense? This L bracket here is compressed because the gear's squatting on the ground, and that plate at the top of it has a gap from the switch. So because the switch is not triggered, it disconnects the circuit, and no matter where you move that selector, the gear should not activate. The pump will not turn on. It prevents you from gearing up the plane when you're on the ground. As soon as you lift off and the gear starts to hang freely, that L bracket expands. This plate triggers the switch, and when the switch is triggered, the G1000 understands that the plane is airborne, and when you select the switch up, it will allow the cycle to complete. Make sense? So that's the squat switch, the safety switch. The one on the left is what serves this gear up, gear down function. The one on the right runs the takt time for maintenance. Any questions on that?
What do you mean by left and right switch?
So you have your right main and your left main. So the right main gear has the squat switch, and that squat switch is wired to run the takt. And the left squat switch is wired to serve this function for allowing the gear up or down. All right, safety feature. This is going to be a pop quiz item that you'll probably get on a stage check or EOC. There's a horn in the plane, an indicator that's very similar to the stall horn. You know, stall, stall, stall. This one is the lady's voice that yells at you and goes, gear, gear, gear. There's 3 configurations that triggers that gear warning. The first one is if you have flaps set to 25 degrees or 40 and the gear is still not down. The system thinks, hey, the pilot's got flaps 25, flaps 40, the gear's not down, he's coming in to land, you better warn him, the gear's not down. Gear, gear, gear. The second one, if you have manifold pressure less than 14 inches in either one of the engines, same thing. Plane thinks that you're coming into land because power's so low, but the gear's not still down, so gear, gear, gear. Hey, remember, put your gear down. And then the very last one, if the plane is on the ground but your gear selector is selected in the up position, the system's going, oh, this moron, he thinks he's about to, pull the gear up, but he's on the ground. Hey, gear, 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 something's wrong. So this indicator is meant to warn you so that you can put your gear in the proper position if you're coming into land, or if you're on the ground, it's in the proper position. Make sense?
Will it tell you,
say you're flying at a lower altitude, or you're doing just a low pass or whatever, would it start barking at you?
No. What do you mean low pass? Like low altitude?
Low altitude pass over the runway, you don't have the gear down, and you're not. Let's say you're at, or you're near, 14 inches manifold pressure. Don't know why you would.
If you're above 14, it wouldn't yell at you.
Okay.
If you have some kind of approach bugged in, it'll tell you low altitude. It'll give you that warning, but you won't get the gear warning.
Okay.
This is another scenario that you guys are going to get for either your EOC or your stage check or both. So let's say you're in the pattern, 2,500 coming back to Addison, and you're running your checklist to bring the gear down before coming into land, and you had 2 green indications but 1 red. It's like, what are you going to do?
You have 2 green indications, but 1.
Yeah, you're in the pattern here, 2,500. They cleared you to land. You're running your checklist to get your gear down, and your right main gear is giving you a red indication. What are you going to do?
Tell tower first and then just recycle them. See if it'll give you a green.
Okay, and then what if it doesn't work?
I know most have a backup, like a manual. I don't.
Are you going to pull that out in the pattern?
No. I don't mean like a.
Go to a safe place.
Oh, okay. So you're saying.
Well, yeah, you depart the area and troubleshoot.
Yeah, exactly. You're not going to tie up everything in Addison just to do that. We're flying a multi-engine aircraft. We have 110, 108 gallons usable. If you're coming back from a training flight, you probably have at least 40 gallons left, so you have an hour or 2 to burn. You're going to go out to the practice area, and then once you're there and you're not in anybody's business and you got all the time and space in the world, you pull out your checklist and you start troubleshooting. So that's an important thing.
So, in a practical sense, let's say we're doing this on a stage check, EOC, whatever, and they give us a situation. Let's say we're going to Terrell,
Mhm.
right? And they give us a situation at Terrell or whatever. We would just talk through the process, right? We're not actually going to go.
Yeah, I don't think you'll get that on a stage check or EOC. You'll get it in the ground, in the oral, just like this.
Oh, okay.
Like,
Not in a
let's
practical sense.
let's role play that we're at Addison, 2,500, cleared the land, the gear didn't
What are you
come
gonna
down.
do?
What are you going to do? And then,
Cool.
the responsible answer is, well, I would tell tower I'm departing the pattern. I'd go out to the practice area. I'd whip out my checklist and I'd start troubleshooting. And then it'll develop. It's like, okay, let's say you run your checklist. You start checking your mirror. You recycle the gear. You pull some circuit breakers and reset them. You cycle your master battery. None of that works. What then? You have this emergency extension knob. It's this red one right next to the gear selector lever. And when you pull it, it drains hydraulic pressure, or it opens up a bypass to the reservoir to relieve hydraulic pressure throughout the entire system. So essentially any hydraulic pressure that was keeping the gear up, it just zero.
Before you depart the area, would you ask Tower what they see?
No.
You wouldn't ask them if they see your.
What are they going to do for you?
I mean, it would tell you whether or not it's like an issue with the sensor other than.
Well, you can also have gear down and it not be in the right position. That may be why you're getting a red light.
Yeah.
So it could be down, but it's not locked in a position for you to land with it. So they can tell you, yeah, your gear's down, but.
Yeah, and if you have a red indication, like, you're going to want to run that checklist before you come into land. So I'd much rather have the assurance that I've ran my entire checklist and I still have a red and towers told me it's down, rather than just saying, yeah, that guy with binoculars said he looked at it and it kind of looks okay, but I haven't tried anything yet.
No, I was just saying, like, you
Yeah.
wouldn't go, I wasn't saying you wouldn't go troubleshoot, but just for more information of like, hey.
Yeah, but here's the thing. If that's your first response, if you come over here and you haven't troubleshot and you're telling tower, hey, I'm having gear issues, one, you're doing laps in the pattern knowing that you're not coming down to land and delaying the 5 jets that are final on instrument approaches. Two, in order for Addison to deal with all that stuff, they're going to declare an emergency for you before it was necessarily a situation where it needed to be an emergency. And then 3, Patrick's going to be right there in the 6th story of his building watching a Seminole do low approaches without the nose gear down, panicking, not knowing what's going on. For what?
I wasn't saying like stay compatible.
Yeah,
Like,
so you should absolutely ask tower to do a low approach and take a look at the gear. That is totally valid, and I agree with it 100%. But that shouldn't be your first priority. You should go troubleshoot first, depart the pattern, try to troubleshoot it, try to solve it, and if you absolutely can't get anything on the troubleshoot checklist to work, then come back and ask for a low approach to see if they see anything that you haven't found. I mean, even if you run your troubleshoot checklist and you get the gear down and you have 3 green, I would still come back to Addison and say, hey, I want to do a low approach so you can verify before I come in to land, right? But the idea of doing it first, you're going to do low approaches, and then you're not going to find anything out, and then you have to go back to the practice area, and then you have to come back for another pair of low approaches. It just creates a lot of chaos that's not needed.
I have a kind of similar, whenever we do say, hey, we're departing the pattern or whatever, do we tell them, like, why? Or do we just say, oh, we're gonna go back out for a little?
Yeah, you tell them.
Okay.
I mean, I personally had this issue myself. A couple other MEIs have had it too. You just say, Tower, I'm having gear issues, I'm going out east to troubleshoot. They're like, okay, do you need assistance? I'm okay for now, I'll call you later.
Okay. That's what I was wondering, if they're
Yeah.
just gonna automatically try and declare or.
Yeah, so another instance is one of the guys actually had this happen where he came in asking for low approaches, and like that's a real scenario. Patrick was in the 6th story of his office and he saw the Seminole doing low approaches without the nose gear down, and then it turned out that Tower declared an emergency for them to open up a block of airspace in the north, and then had them go up north and pull out the checklist and troubleshoot there. They eventually pulled this knob and got the nose gear down, and then they came back into land and no problems, right? So everybody got away safely, everything was managed well enough, but in hindsight, we could have caused a lot less chaos and panic throughout the airspace and for everybody involved if they just went out and troubleshot first and then came back later. So it's not like, you know, it's a hard, no, you're not allowed to, but from past experience, there's ways to do things better.
So at what point, like when we're coming back in here, are we gonna go gear down before our initial call? Or like how far out? are
5
we-
nautical miles.
Okay.
Yeah.
Gotcha.
It's a rule of thumb
Okay.
to run your gum spring or gear down.
Gotcha.
But anyways, back to this. You're out east, you're going to be doing your troubleshoot checklist, you run through all those items. One of the last things is to pull this knob. There's a speed restriction on it of 100 knots. Now that's another pop quiz item. Reason being is now that you pull that knob, you're relieving hydraulic pressure. So even if that hydraulic pump is turning, it's not going to be pumping fluid into the top of the cylinder to help you out. So all you have is gravity and springs against the relative wind. So you got to reduce your speed to below 100 knots so that that relative wind isn't strong and the gravity and the spring can do their work. And if they're still not strong enough, then you have to start pulling some maneuvers to apply G-forces, some loading to the gear to persuade it down. And the important thing there is understanding how that gear leg that's stuck or jammed or whatever it may be comes down so that you can apply the proper force to persuade it down. So for example, the nose gear comes down and forward in front of the plane. If you want to swing it down and forward, you're better off doing some kind of maneuver like a pitch down and a yank up, like like in an accelerated stall, but without the bank in it, right? You pitch down and you yank and try to accelerate the nose to come down. With the main gear, they come outwards and to the side, and they're relatively in line with your CG. So if you're to pitch up, you're pivoting around your CG, that gear doesn't have much of a moment arm for any kind of force to be experienced there. So it's not going to do you very much good. In that case, you're much better off mashing the rudders and getting the plane to fishtail side to side, or just kind of doing more aggressive lazy 8 types of maneuvers, or an accelerated stall, because now you're applying a force to that gear leg with a moment that acts in a way that swings it down. Make sense? And in any case that I've ever experienced, applying these kind of G-forces is going to get the gear down if you have this pulled and the gear selector down, because the last thing you want is to pull the extension to relieve the pressure and have the gear selector up, because then the motor is going to be working against you. So any questions on the gear? We'll move into the combustion heater. We'll dig into the POH for a little bit, and then maybe we'll get out 15, 10 minutes early. Garrett can get some food, and me too.
So many offers. Yeah, there's like 30 restaurants. I've been ranked the last 2 weeks. The only thing there is a dirt.
Sounds awful.
All right, so janitral combustion heater. It's essentially a heater for the cabin. And common question you might get is, why the heck do we even have one in the Seminole?
It's easier to do that than try to run pipes all the way from the engines out there into the cabin to the heat.
Best answer.
Dude, he knows everything.
I don't know about all that.
Yeah, I swear. Like, he gives the most simple, straightforward, all-encompassing answer for every single question I've asked. And the ones that people usually struggle with, too. You've been spot on, Garrett. Bravo. So yeah, exactly. If your engines are out on the wings, it would be a huge pain to route all that plumbing, stainless steel pipe, and get all the heat loss and pump it into the cabin. So you have some space in the nose of the fuselage. You slap a heater in there. It's going to be a lot less complex. It's going to be heater that's more tailored to the job, more efficient, less risk for carbon monoxide, and a lot more effective, right? So this is kind of what it looks like by a cross section. If you look at the plane head on, right, so the nose is right in front of me. On the left side, there's a little slit there. It's a thin one. It kind of looks like the Archer's slit on the right side for the air intake for combustion. Don't be confused. That slit for the heater is the air intake that goes past the fan, gets heated up and pumped into the cabin. So the slit is for the cabin air that's being warmed up. Then a little bit further, there's a little hole that's about 1.5 inches diameter, and that is the air intake for combustion. So that air intake for combustion that comes in through that 1.5 inch diameter hole moves into a combustion chamber. In that chamber, there's a nozzle, a sprayer, that pulses fuel going in, and there's a glow plug. A glow plug's a little different from a spark plug. So rather than just providing a spark at a pulse, it just heats up to a temperature warm enough for combustion to occur. And once the fuel ignites and continues to pulse, the exhausting pulse of fuel that is burning out is enough to ignite the fresh pulse that comes in, and it's a self-sustaining cycle. So it's just a continuous combustion event, and then the glow plug can turn off and save energy. Make sense? So as this combustion is occurring and that fuel is burning, it gets routed through a series of heat exchangers and then exhausted out the bottom. And you can see that exhaust pipe on the bottom of the nose. The cabin air moves past the fan to help pump it through, past the heat exchanger, and then straight into the cabin. And that's what warms you up.
We won't get to use it.
Why's that? Oh, it's summer, so. But if you want to, you can turn it on and suffer for a little bit. Suffer for the sake of education. So this is a fuel diagram. It's not super important that you guys get familiar with it. I would just kind of ignore it. The main purpose is just that the heater lives here and it has its own pump. So the heater has its own fuel pump. If you ever ask how many fuel pumps we have on the Seminole, 5. 2 engine driven, 2 auxiliary, 1 for the heater. And then,
Same as the Archer, man.
yeah, it gets lined towards the left tank. So the combustion heater is located in the nose compartment. It gets its fuel from the left tank, and it gets it at a rate of 1/2 gallon per hour, as in 0.5 gallons per hour. It burns 100 low lead. Nice and efficient.
Nice and clean.
Yeah. There's some operation limitations which are very important. They're located on placards that are right in front of the right seat of the plane and also next to all of the controls. So first we'll talk about the controls. It starts with these rocker switches. So there's 3 position rockers. Neutral in the middle is off. You push the top, cabin heats on. You push the bottom, fan is on, right? You push the top, it's high vent. And you push the bottom, it's low vent. This doesn't matter for us because they're all placarded in-up because we have aftermarket air conditioning installed. So that's part of the installation process. Those don't work. Anyway, so if you want to turn on the heater, you want to open the air intake. So you just move the slider to open, and that opens up that little slit to allow air inside the cabin. In the Archer, in the Cessna, in the sides, you have those little, levers that you can move forward and backwards to open up those vents to allow fresh air from outside into the cabin. That effectively acts as the same thing. This slider here shifts and changes the ratio of outside air and air that's coming through the heater and mixes them together to set the temperature in the cabin that you're getting. So you can make it all air from the heater and you can cook yourself, or you can keep it on cold and it'll just be fresh air from outside. And then the last one is the defroster. That's essentially just the bypass routing to allow hot air to come up in the front and defrost your windshield. So those are the 3 sliders that help with your control. And then this pretty much turns it on. So first you want to move the air intake open so that you're actually drawing air in, and then you turn the cabin heat on and it'll turn on that whole heater. On the contrary, if you move it all the way down to fan, it only activates the fan portion, not the combustion. So it'll just draw air in from outside a little more effectively and pump it in the cabin.
A question about the defroster.
Yeah.
It runs off of the heater, correct? So it's not its own independent unit?
No.
Okay.
These 2 limitations are quite important for it. So first one, if you're using the heater in flight and you decide you're hot enough and you want to shut it off, you'll move the switch to off. However, you need to keep the air intake open for at least 15 seconds to allow enough ram air to move past the heater and cool it off so that it doesn't set on fire. Because when you turn that thing off, if there's no relative air moving past it, it's just going to radiate until it sets the whole nose of the plane on fire. Same thing on the ground. On the ground, we don't have that relative wind to come into the air vent in that slit. So when you shut the heater off, you need to keep the air intake open and turn the fan on for at least 2 minutes to draw air past the heater and cool it off for 2 minutes until it's safe to shut off completely, and then you can close the air intake. Make sense? So this is all located in the POH section 7. It's also right in front of the right seat of the plane. Good on that?
Great presentations, man.
Thanks. Made them all myself for my MEI check ride.
Yeah, they're solid.
And then I thrustified them. 7652. All right, so go ahead and open up section 7. Page 205 is going to be the table of contents. When it comes to studying the POH, chapter 1, chapter 7, and chapter 4 and 5 are going to be your best friends. 1, 4, 5, and 7. 1 is just general and limitations of the aircraft. You should know that for every plane you ever fly. 4 is going to be the checklist and procedures. It's just good to have a once-over there. 5 is all your performance charts, which you'll naturally do. And then 7 is the most studying that goes in. That's all of the systems. So going through here, section 7.5 and 7.7 is a good one, page 210. This references, for example, what that spring and pin is, the centripetal lock pin or the anti-feathering lock pin. Gives you the 950 RPM set point in there if you ever forget it and need to reference it. And under 7.7 in engine controls, it also gives you some conditions where you can get a gear warning message. So page 254, section 7-11 is the beginning of landing gear. This and the next few pages is very important information. I highly recommend you read through all of it, highlight all the good things. Tells you about the electronic activation, the hydraulic actuation. It gives you this nice note here that if the gear's in transit, do not select it in the opposite direction unless it's finished its cycle. The next page over tells you about the limit switches, also springs assisting in the gear extension and how they lock them into position, and the such. All the indications, lots of good stuff. Page 261, still in section 7-11. You have this nice breakdown of those 3 scenarios that give you the gear warning horn. The 14 inches manifold pressure, gear selector in the up position if you're on the ground, and flaps extended to 25 or 40. Next page over, still section 711 is all about the squat switch and the emergency extension knob. So a good place to read in there to see how that works. Tells you that the squat switch works off of the left main gear. Also the emergency gear extension and the airspeed suggestion on that one. Brakes, 7-11, this is page 264. Talks about the brake hydraulic reservoir. Let me ask you guys this. What hydraulic fluid do you think we use for the gear?
MIL 5606H.
Yeah. What hydraulic fluid do you think you use for the brakes?
6H.
So do they share a reservoir?
No.
Why not?
Why would you do that?
Why wouldn't you? It's the same hydraulic fluid.
Why the hell would you do that? That doesn't make a lot of sense.
Yeah, it's a concern for redundancy, right? Because if you have a brake issue, you don't want to have gear issues, and if you have a gear issue, you don't have brake issues. So there's separate reservoirs for that redundancy. The way I like to remember it is your brakes, your toe brakes are out in front of you with your feet, so your brake reservoir is in the nose of the plane. And then your gear reservoir, your landing gear is relatively underneath you and slightly backwards, so the gear reservoir is in the back of the plane. Make sense? That information is all here on page 264. 266 is the beginning of 7.17, all of the fuel system information. Tells you about how many gallons are in the tank, how much is usable. It has the diagram. And then this is just a fun feature that isn't necessarily mentioned in detail in the POH. However, do we have traditional fuel tanks in the Seminole?
No.
No, what are they?
I don't know this one.
So they're fuel bladders. Yeah, they're kind of malleable. They can change shape somewhat. Reason being is traditional fuel tank is made from aluminum. And aluminum, in order to get it to seal at any of the seams, you need to weld it together to make it watertight. However, when you weld aluminum, you expose it to really, really high heats, and it begins to heat treat it. It makes the metal very strong, but also very, very brittle. And brittle metals do not do well with vibrations. They have very, very short fatigue lives. So if you put them right next to an engine and they're just shaking all the time, they're going to crack, and those cracks are going to propagate, and then you're going to have fuel spilling all over the place, right? So in the Seminoles case, where you have the fuel mounted right behind the engine, we have the bladders, which are more resistant to vibrations. This way they don't crack, and we don't spill fuel everywhere.
Where is that at?
It's in the study guide.
Okay.
Yeah. Or the maintenance manual.
Okay. Just like a description of how those function, or is that probably not really necessary?
They function all the same as any fuel tank. You know, there's just no tab indicator in there. You have to use the fuel straw.
So it has the same fuel level sensor in it.
Hmm?
If the bag or the tank itself is malleable, how do we know we're getting accurate readings from the tank?
It's not that malleable.
Okay. It can just kind of flex
Yeah.
a little bit. What's it made out of?
It's like a Kevlar type of material. It's pretty
Some sort
stiff.
of fabric.
Yeah.
Okay.
Page 268, this talks about the crossfeed. We'll talk more about it tomorrow, but if you really want to get into it, this tells you how to orient your crossfeed selectors, what the different positions are in order to achieve the fuel distribution that you want. Electrical system is page 269. Electrical is very similar to what it is in the Archer. 28 volt system, two 24 volt batteries. We have two alternators now. The only difference is there's 65 amps as opposed to 70. There's voltage, over voltage protection, voltage regulator, all that jazz that's in here.
So the videos talked about a 12 volt battery and a 14 volt system.
That's old. That's old. Yeah. Hey, it's on.
Learned that
It's
from
on?
everything.
Right, 279 is the beginning of section 7.23. That's all about the combustion heater. Tells you about the things that we covered in that last presentation, and specifically where it gets its fuel and at what rate. Also gives you a little diagram of how things are routed and plumbed throughout the Seminole, and then you can find all those placards that you just saw me talking about. And that's pretty much the bulk in section 7. So there's a lot in there, but there's also a lot of good information. I think definitely before you guys go off the stage check, you should go in there and highlight all the key points with respect to each section. So 7.11, make sure you get all the gear things put up. 7.17, make sure you got all the fuel things set up, and so on and so forth. This way, when you get asked a question, one, you have the familiarity because you already read through it all, but two, if you forgot a little detail, you have it tabbed and bookmarked and highlighted so you can pull it up nice and easy. So it's relatively short time to learn a new aircraft. Any questions on that?
These sections that you highly recommended.
I'd say one in 7, like 1 in 7 study them. 4 is going to be procedures, so I recommend you go through there and at least look at short field takeoff and VMC demo and just any kind of single engine stuff because that's new. But most of section 4 is pretty much translated into our maneuver guide. I'd like you to look at short field takeoff because it has those notes about why we don't use flaps on takeoff, and I'd like you to look at VMC and single engine operations because it's new, and it also publishes that it wants us to do it at or above 4,000 AGL. And then section 7 is all of systems, so you guys need to know that. That's going to be the bread and butter for what's required per the ACS on the EOC or the check ride. Section 8 has maintenance stuff in there, so you can get some nuggets, just kind of pop quiz fun facts, but not necessarily any concrete stuff that you're going to be tested on. Yeah. All right, so plan for tomorrow. We're going to resume on performance calculations. We'll talk about some scenarios associated with those, and then we'll go over the bulk of this stuff on the board and some more. Probably get done with like half an hour of extra time unless you guys had plenty of questions, but that's the plan going forward. Any questions to round off today? All right, keep studying. Oh, actually, one last thing. You all have a homework assignment. Very, very important, okay? I know a lot of you guys are driving here and driving home and just driving in general outside of training, right? If you can, print out a checklist, keep it in your car. Every single time you get stopped at a red light, I want you to run the engine outflow in your car. Pick something that represents gear and flaps. I don't care if it's your air conditioning button or if it's your dial to change the temperature on the air conditioning, just something to physically touch and get that sensory input, right? So engine outflow, mixtures, props, throttles, gear, flaps, identify, left leg, verify with the throttle, and start getting in the habit of that. Every red light that catches you. Now when that red light turns green after you've completed your engine outflow, I want you to verbally state in your car, positive rate, gear up. Positive rate, tap the brakes, gear up. You tap the brakes because when you lift off, the wheels are still spinning and you don't want them to spin retracting into the wheel well. But the two things that people always come short on is they're not familiar with the engine outflow and it makes them nervous and they get panicky. So rehearse it in your car so that you get the repetitions in. And it's their first time flying a retractable gear plane and they leave the gear down on takeoff because they're not used to it. They don't have that primacy. So red light, engine outflow, green light, positive rate, tap the brakes, gear up. Every light on the way home, back to school, whenever you're driving. That's the homework assignment. From now until your EOC.
Cool. All right. Thank you.
You're welcome.
That wraps up day 1. It is a long course. We have day 2 coming right up. But if you are enjoying this training so far, this is sort of what it looks like here at Thrust Flight. Our ground courses kind of go this way. If this is the kind of training you might be looking for, feel free to visit thrustflight.com. We have many ways of entering our program no matter where you are in your journey. I'm sure we could figure it out if you really were interested in looking into joining us at Thrust.
All right, so beginning off with performance calculations, I'm biased just given my background, but it's my opinion that this is probably one of the most practical and probably important topics that we'll cover in all of multi-engine flying. If you can kind of understand the basics and the fundamentals of how to use these charts to make educated and safe decisions, then you can manage the risk in all phases of your flight. You can always have a plan A, B, C, D, E, F, depending what your scenario is. So no matter what happens, at least you have a reasonable enough understanding to get yourself out of whatever situation that might be. So first, departure brief. We're going to break this thing down in full on the whiteboard when we get to it here. So this is just heads up, plant the seed in your brain. We have 4 scenarios that we now brief on departure. It's going to be when you have an engine failure on the runway when you're still rolling, when you've taken off but you still haven't brought the gear up, when you've taken off but you've brought the gear up and you're still at a relatively low altitude, and then the last scenario is you've taken off, the gear's been up, but now you've climbed to a substantial altitude. So that's just 4 different phases of the takeoff that slightly change how we're going to execute the engine outflow and go on from there. So that's just the heads up of what we're going to go into a little bit later. We'll blow through that right now. So first performance chart that comes out of our bundle that's different from anything that we've seen in both the Archer and the Cessna is this accelerated stop distance. So now that we have 2 engines, if we potentially had one fail on the runway, this calculation is going to help us understand how much runway distance we need to abort that takeoff and come to a full stop. So the formal distance is in terms of a short field effort. So you're beginning here using max runway available, standing on the brakes, putting in full power, verifying instruments are on the green, releasing and accelerating all the way to your rotation speed. And then by some kind of divine intervention exactly at your rotation speed, one of your engines fails and you execute an aborted takeoff and begin braking. Once you come to a full stop, once again, that distance from full stop in the beginning to full stop at the end will be your accelerated stop distance. Does that make sense? Going into the POH, this is the chart that we have for it. It looks very similar to your standard takeoff chart in the Archer. In the Cessna, is it similar, different?
We don't really, I don't think we even have a chart like that. It's more crunch number.
Yeah, so in your case, since it's a little less familiar, the way this chart is made, it's broken down into 3 separate sections. So you can see here's a section just for your field elevation and characteristics, temperatures listed on the bottom, and field elevation in terms of pressure, altitude with the weather effects is here. This is the section for your weight and balance. So after you've calculated your weight and balance and you know your loading criteria for takeoff, this makes the adjustment for that. And the last section here is for a headwind component. So the way I always like to do these charts is to begin with reference lines on the things that we already know. So off your weather briefing, you'll know what the field elevation temperature is, field temperature is. You can draw this yellow reference line all the way through it so that you have a starting point. Second, after completing the weight and balance, you know what your takeoff weight will be, yellow reference line drawn all the way up. And lastly, you know your headwind component on the runway, so you can draw that reference line. From there, you come back to where you started, and this is where you can connect all of the sections. So if we're taking off out of Addison, field elevation 645, let's assume that it's standard pressure 299 So you start at this intersection 20 degrees and 645 roughly. You'll drag it across to the beginning of the next section, and once you get to this weight and balance reference line, you'll follow these guidelines down until you hit the next reference of what your weight category is. Once you've hit that, you're done with this chart, and you'll continue along to the headwind reference line, and again, follow these reference lines down until you meet your wind component. Here I'm using 5 knots headwind, and then drag it across, and that'll be your calculated takeoff, or sorry, accelerated stop distance. Yeah, the reference lines really make it a lot cleaner, more organized. One thing I will note to you guys, and this is a suggestion from Bill Peterson, based on all of his years in the airlines. He informed us that whenever they're doing these performance calculations, accelerated stop, takeoff distances, landing distances in the airlines, they always consider winds calm. This way, it builds in a little bit of a safety factor, because the weather's always changing. The forecast isn't always right. It might not be what was expected, especially if you have a longer trip and the forecast is however many hours out. So if you were told that you're going to expect a 10-knot headwind component, but really you got there and it was 5 knots, now you've planned for a shorter, let's assume this is for landing, right? You've planned for a shorter landing distance than what's actually there. However, if you plan for winds calm, no matter where you're taking off from or where you're landing at, whatever the weather conditions may change to be, you're always going to have slightly better performance than what you planned for, unless the case, of course, that the runway being used has a tailwind for whatever reason. So just an idea for you guys to take with whatever grain of salt you want to take it with. All right, so on the reciprocal, the last one was accelerated stop. This is accelerated go. So it's kind of same scenario. You got the engine failure right at your rotation speed, but instead of aborting the takeoff, you made a go decision. All right, so at that rotation, you can make a go or a no-go decision. Same thing, short field effort, max distance available. You've released the brakes. At rotation speed, you had that divine intervention and your engine somehow failed, but you continued to go. And as a very skilled pilot, you took off, you maintained 88 knots, you went mixtures, props, throttles, verified the gear was up, verified the flaps were 10, you identified, you verified, and you feathered in perfect fluid pace and climbed to a 50-foot obstacle. That distance from very first start to clearing the 50-foot obstacle is your accelerated go distance. So once again, calculating how much distance you need in the event that you have to continue. Any questions on that? Now a little idea for a scenario to kind of plant in your minds. When would you use an accelerated stop versus when would you use an accelerated go?
Which runway lengths available to it? Shorter runway, probably accelerated go, longer runway, accelerated stop.
Yeah, that's a good idea. If you calculated your accelerated stop distance and you didn't have the runway length available in order to make that happen, would you be comfortable taking off from that airport under those conditions? I think it would be dependent on what's on the other side of the far threshold, right? If you're taking off into a city and you don't have accelerated stop, hell no, I'm not taking that risk. Into water, probably not taking off that risk. Into something that has plenty of available aborted landing scenarios, maybe, but it'd still be pretty inconvenient. Anyway, so here's an important caveat in terms of the regulations, and this is something you will be asked on either the stage check, EOC, or check ride. It's where this comes from in the regulations. So 2 charts that we just went over, accelerated stop and accelerated go. Our PA 44 does not have a chart for accelerated go. We only have accelerated stop. The reason being is this is very similar to Part 23-149. When the Seminole was certificated, the FAR that was in place that's of relevance here was 2367. And 2367 dictated that if you are under 6,000 pounds and you have a stall speed of less than 61 knots in the landing configuration, then that manufacturer is not guaranteed, or it does not need to guarantee single engine climb performance. So I'll repeat that one more time. If you're less than 6,000 pounds and you have a VSO of less than 61 knots, then that manufacturer does not need to guarantee single engine climb performance. I.e. the PA44 doesn't have that chart because Piper was not required to guarantee that you can climb with a single engine. That being said, it can climb with a single engine, right? It's just they didn't have to per part 23. So this is the historic one. This is all the criteria that needs to be met. And just like 23-149, it's rewritten. This is the current modern day. So if you're flying some kind of modern diamond that's going to be certificated in 2025, it will meet 23-2120 and 23-2125. However, the Seminole met this standard when it was certificated in the past. Any questions on that? So one thing to consider is this single engine climb rate. In the past was a climb rate, and more present after 1991, it had to be defined as a climb gradient. So climb gradient is very similar to what you guys have in instrument on your obstacle departure procedures or your minimum climb gradient, as in you need to make it 200 feet per nautical mile, right? This is expressed as a percentage. So it's just how much vertical distance you've climbed per how much horizontal distance across the ground you've covered. So in this example, if you've climbed 500 feet using a horizontal distance across the ground of 5,000 feet, you would have a very aggressive 10% climb gradient, as in 500 divided by 5,000. Is that clear? Cool. All right, another new performance calculation that we have, and that is very important to our operations, are the single engine ceilings. We have two of these. And the second one is kind of half of one because it relates to the second. The first is your service ceiling. This is where, with a single engine, you can still maintain 50 feet per minute climb rate. Right? So one engine, 50 foot per minute. Your two engine service ceiling will be 100 feet per minute. You lose an engine, you cut that in half. Make sense? Two engine service ceiling, 100 foot per minute. One engine service ceiling, 50 foot per minute. The absolute ceiling with the single engine is just when you cannot climb any more, period. There's also an OEI drift down distance. So in this scenario, or I guess in this scenario, the absolute ceiling you might think of if you lost your engine really low to the ground, how far can you climb before you can't climb anymore? The drift down distance is more so if you're at a high altitude and you lost your engine and you try to maintain blue line to the best of you can, how far are you going to drift down until you stabilize? As in you lost your engine above your absolute ceiling, so you can't maintain that altitude anymore. You're going to drift down to your drift down altitude. These are the same. Absolute ceiling and drift down altitude are the same. The drift down distance is just the difference between where you are when you lost the engine and how far you're going to go until you get to that absolute ceiling. Is that clear? Any questions so far? All right, so how to calculate it. In section 5 of your POH, we have this chart. You can kind of see the title up here on the top. It's going to be your climb performance with one engine operating and gear up. So here you can get a very good idea. Let's say we're flying on a cross-country IFR plan to the west at 8,000 feet, and you want to see, hey, if I lose an engine, what can I do with 8,000 feet? You can follow this chart naturally, get your temperature wherever you are, bring it up to whatever your altitude is, drag it across to whatever weight category you are, and then bring it down. And at 8,000 feet, if you lost an engine, you're below zero, so you know that you're above your absolute ceiling. You're going to drift down at whatever feet per minute that it ends up at. If you want to be clever, the way to calculate your absolute and service ceilings, you have to work backwards on this chart. So using that information that we just learned, the absolute ceiling is where you can no longer climb. 0 rate of climb. So you'll start from the 0 and drag it all the way up until it meets whatever your weight and balance category is. So here in this example, I'm using 3,600 pounds. So I brought it from 0 to the 3,600 reference line, and then you drag it across to whatever my reference line was for the field temperature. So this is using 20 degrees. I drew that reference line, and where these intersect, that's how you can roughly estimate what the absolute ceiling is by gauging where it is between these pressure altitude lines. So if this one here is 4,000, the next one's 5,000. This is roughly 3/4 of the distance in between the two. So we can say, 4,700-ish. I chose 4,600, conservative. And then we use the same exact approach to do the service ceiling. This time you start with a 50 foot per minute climb, the definition of the service ceiling. Drag it up to your weight and balance line, drag it across to your temperature reference line, and then you estimate between which two pressure altitudes it is. It's once again about 3/4 between 3,000 and 4,000 feet, so you can call it about 3,700. Any questions on that method? So one more thing, there's a little bit of confusion and people teach it in various different ways. In section 5 we have another chart identical to this one. It's just it's adjusted, aligned for 2 engines operating in gear up, or also 2 engines operating in gear down. So you can use the very same method to get a rough estimate of what your 2 engines operating gear up, absolute and service ceilings will be, and same for the gear down. The one in the gear down, where might you guys be concerned with actually having that number? Of what relevance is it to you to know what your absolute and service ceiling will be flying around with the gear down?
Coming into land at a high elevation.
Yeah, but you're not really trying to maintain altitude or climb there. So it's kind of a long shot. Maybe you can get some nugget of information there, but I'd argue you can still safely fly without it. So
So if your absolute ceiling with your gear down, when would that be pertinent?
yeah, when is it good to know that information?
Gear malfunction.
Exactly. If you had a gear malfunction somewhere across your way. So if you're planning a route that goes through a lot of mountains or some kind of hazardous terrain, and for whatever reason you had expectation that your gear was a little funky, it might be worth knowing what that number is, saying, oh shoot, if the gear malfunctions and it drops down, right, that's all I got. Or if you're flying around somewhere just perfectly, everything's working, but the field elevation is fine everywhere, and you're going into land and you find out that you do have a gear failure, you at least know what kind of options you have to climb out there. Can you still guarantee at least having a service ceiling if you do an approach to land somewhere in Colorado in the mountains at 9,000 feet? If you have to go around or go missed for whatever reason, will you be able to climb out? So again, this is kind of the first of many questions that I'm going to pose you of. This example isn't explicitly put in the chart, but the chart at least gives you a rough idea of what kind of capabilities you may have if you get yourself in these situations. And under the caveat, yes, that's a lot of, what ifs. 1 in a million chance that I have a gear failure flying around in Colorado. But would you rather be slightly informed or in the dark? All right, critical density altitude. This kind of relates to some of the VMC characteristics that we were talking about the other day. So let's cycle back to that characteristic of standard day conditions, right? We determined that at 15 degrees Celsius in 29902, what happens to aircraft performance relative to a standard Texas day? Performance is going to increase, right? It's cooler, there's better density of air, so the engine gets more performance, our control surfaces have more performance. What happens to VMC as an impact of that? If you have more engine performance in your single engine, it's going to be easier or more difficult to maintain directional control. You guys are conflicting. Let's sort it out.
If you have more engine performance in the VMC condition, it'd be harder to combat.
All right, Brian's saying that if you have more engine performance in a single engine condition, it's going to be harder to counter it. Do you have a counter argument?
If it's heavy or light, but that's kind of
Yeah, we're just talking about weight's not a category.
I guess, yeah, if you have more, no, he's right. 'Cause if you have more performance in one engine, then it's going to be harder to.
Exactly, yeah. There's more strength in those past factors that are trying to steer you out of directional control. So your VMC speed will go up, as in you need more airflow to manage it. Make sense? So we can take that trend and then just post it on this chart. This chart gives us a relationship between airspeed here on the bottom and altitude, specifically density altitude. So based off that same principle, instead of changing temperatures and pressures, we start climbing higher and higher. What happens to the engine performance? It gets worse, right? Because the engine's gasping for the air that's not really there. So if the engine performance is getting worse, what's happening to VMC? Yeah, VMC is getting decreasing because there's less of that force trying to steer us out of directional control. Make sense? So that establishes this trend. That red line there is the VMC speed. It continues to decrease as we climb in altitude because that engine power and those pass factors are getting weaker and weaker. Make sense? Now, here is the relationship of stall. And given this is indicated airspeed. This is stall. As you climb in altitude, indicated airspeed is going to be the measurement of the pressure that you're experiencing from the air, the mass airflow into the pitot tube, also the mass airflow over the surfaces. So you're always going to stall at the same indicated speed. That doesn't change within altitude, right? So we have this relationship established. Stall speed doesn't change, but VMC gets lower and lower as you climb because there's less air for that engine to perform. So if you have a VMC speed that's higher than your stall speed, as you continue climbing, there's going to be a point, a certain altitude, depending on the conditions of the day, where your VMC speed and your stall speed are identical. And that is a very, very dangerous place to be in, and something that you should always be aware of before going out, especially if you're doing any kind of training flights, right? The reason it's so dangerous is if you're practicing, for example, a VMC demo and you get too slow, not only do you start to lose directional control, but you have a wing stall as well, and you no longer have any of your control surfaces available. The plane will rapidly turn into a VMC roll, and you'll get yourself into a very terrible, unrecoverable situation. Make sense? That being said, the regime below and the regime above are still dangerous if they're not handled properly, but you can be prepared for it. So below here, VMCs first, you're going to get slow, slow, slow. You're going to have max rudder deflection in your up to 5 degrees 0 side slip, and you're going to notice that you're trying to maintain your heading, but the nose, even though you have full deflection, just keeps veering over. And the farther it gets away, the more it's going to accelerate before it exponentially accelerates and gets you in a bad condition. So that's the indication of a VMC event. It starts out very, very benign and slow, but it accelerates very, very fast and gets very, very dangerous. Hence, we have the VMC recovery to recover from that situation. Make sense? And we'll talk about the VMC recovery later. Above, in this regime, stall is the higher speed. So you can get slow, 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 and you'll feel a buffet. Or if you have a stall horn, you'll get the stall indication, at which point you continue with a stall recovery. Important thing to remember there is that if you don't manage the stall recovery properly, especially with a single engine operating, it's still very easy to get uncoordinated and fall into a bad condition. So unsafe, unsafe, terribly unsafe. You should always be aware of what regime you're in so you know what you're looking for in these slower conditions. Make sense? Now here's a bit of a twist. What's our VMC speed? 56. What's our stall speed in the clean configuration? All right, so 56 VMC and 57 stall speed. So where on this chart are we? And that's VMC as certificated under all those conditions that we went through yesterday. So where are we on this chart if our VMC is 56 and our stall is 57? Don't think about it too hard. No, we're pretty much smack right there. Like, this isn't 1 knot difference, right? It's a pretty big chart. 1 knot difference is like this. So we're pretty much at critical density altitude. That means if we take off from anywhere, even if it's an airport at a higher field elevation, we're pretty much starting from here. The only potential for us to really be in this regime in our airframe is if it's a really cold day and you're in Louisiana and it's a high pressure system and the local pressure altitude that morning is below the ground. Make sense? So really, if you're flying, we're always going to be in this regime, and it's a stall condition first. Now you might ask, okay, well, when are you ever going to see that? Why does our airplane not even have this performance chart? Why do we not operate in that regime? What's different about our twin than most others? Yeah, counter-rotating propellers, so we don't have a real critical engine. And because we don't have a real critical engine, our VMC is innately low compared to a Baron or an Aztecs or a Twin Comanche or name your conventional aircraft of choice. So those guys that are conventional, they have a higher VMC speed in comparison, at least for the most part. And they will have this bigger discrepancy and a proper critical density altitude that should be accounted for. Because we're the trainer, because we pretty much start from here, our POH doesn't include it because as soon as we take off, we already know we're in that regime. Make sense? Sweet. So scimitar propeller for short field landing. Let me see. Here in the landing chart, there's this note, scimitar blade propeller. We have two charts if you actually look in the POH. One is for a straight blade and one's for a scimitar blade. The difference is how they're shaped. You can see the scimitar has a curve and a flare at the end, just like a scimitar sword. That's where it gets the name from. The propellers have slightly different thrust and drag profiles. The scimitar blade's very effective at higher RPMs. It kind of behaves like the swept wing in a jetliner in that the propeller tips that are approaching transonic speeds, the effective length that the air is traveling over is diagonal, just like on the swept wing of a jet, hence tricking that air into moving slower and not producing a shock wave, hence not producing drag at the tips of the propeller when it's producing such fast speeds. So by reduction of that shock wave, it reduces drag and makes them a lot more effective at higher airspeeds. However, at lower airspeeds, there's more effective surface area, so it creates more drag. Hence, your landing distance calculations are going to be slightly different because you bring the plane in nice and slow. It's operating in that higher drag profile regime, so it helps anchor you, slow you down, almost speed breaks too aggressive of a work, but some fraction of a speed break in comparison to the straight blade propeller. Make sense? So you have slightly different performance charts for straight versus scimitar. It's important knowing the difference. All of our Seminoles have the scimitar blade propellers. Do I need to explain how this chart works? Bowser, are you good with it coming from the Cessna?
I'm tracking on it.
Okay, sweet. So that's just, exactly the same as the accelerated stop distance that we went over. Now, takeoff distance over a 50-foot obstacle. Do you guys notice anything different here?
Shaded area.
Yeah, so this is of the main difference between our archers. The shaded region corresponds to the caution warning in the top, stating that if you've done your performance calculation and you happen to be in this regime based on your conditions, when you lose an engine, if you lose an engine, you cannot guarantee a 50 foot per minute climb. It's kind of a scary thought. So high field elevations, really high temperatures, Arizona, really heavy weight, low pressure systems, not super impactful, but slightly. All these things are different factors that could get you in this regime. If you're planning a flight out of Aspen, Colorado, and it's a warm day, and you're taking full passengers, you're probably going to be up here. And you're surrounded by mountains. If you have an engine failure, you have very limited options. Is that something that you want to do as a pilot, as PIC, planning and conducting this flight? If it's something that you need to do because it's a high priority customer and you have all the incentives to do it, how can you reduce the risk? I ask you guys, how can you reduce the risk but still take your paying customer?
Reduce the risk if you're inside of the shaded area.
Yeah.
You can see how much fuel you need first. You could still have a safe amount without taking too much, but you could also limit what they bring on. And just kind of thinking out loud.
But what if your passengers really want to bring their equipment because it's a luxury service and they're paying you a lot of money?
They shouldn't be taking a Seminole.
Yeah.
True. But let's talk about that fuel. I'll take that even further. Let's say you want to go Aspen to Addison. You're not going to take minimum fuel to get from Aspen to Addison. You take minimum fuel just to get out of the mountains. Select a route that has some kind of valley path, lowest peaks, see what the nearest airport is, 3,000, 4,000 feet lower field elevation, and just take minimum fuel to get there with your reserves that are needed. Refuel there and take off from somewhere much lower on the chart where you don't have to worry with that regime again. Right? That's one way to reduce weight. The other thing, maybe there's huge temperature swings depending on the time of the year. It could be 75 degrees in the afternoon, but in the morning it's closer to 40 because some cool mountain air descends or who knows what's happening around there. But I guarantee you a 30 degree or even 20 degree difference in temperature is going to give you significantly lower density altitude and better performance. Maybe there's some kind of weather coming through and there's a high pressure system and you have an extra, 0.4 on your altimeter reading. It's another 400 feet of better performance. All these little things are tuning knobs that you can play in your favor to manage your flight and minimize your risk. So again, one of these seeds that I'm trying to plant into your brain. It's not checking the boxes, it's not directly there in the performance charts, but all the information is here and all the critical thinking can be applied to make you the safe multi-engine pilot that can analyze what risks you're taking on the flight and at least have some kind of idea of what you're going to be capable for in the worst case scenario. Make sense? Sweet. We'll blow through a couple extra charts just to get you familiar. This is your, I forgot what the title of this is, fuel and power settings. It tells you what kind of RPM and manifold pressure combinations you have with respect to the altitude you're flying at and what rating of power you're going to be using. So it helps you set your throttle and RPM settings in cruise. Important thing to call out here is this chart also gives you an approximation of your fuel flow. Note that is per engine. A lot of people make the mistake coming into a scenario saying, hey, I'm only going to burn 10.2 gallons per hour. And I always ask them, how much fuel would you burn in the Archer per hour doing that? And they go 9.5. And then I ask them, hey, the Seminole with 2 engines only burns 0.7 more gallons per hour than the Archer. And then they think about it for a while and they have a revelation. So just know, it's per engine. Per engine. Speed power, you can get an estimate for your true airspeed. This is good for cross-country flight planning. Same thing with your performance cruise. This one gives you a decent estimation of how much range and how long you can fly. Short field. This is one that I want to talk about. Climb performance, both engines operating and gear up. So if you were to use this chart in order to calculate what your absolute and your service ceilings are when both engines are operating, it doesn't fit within the chart itself. If you're trying to use this reverse method and go from 0 foot per minute, you'd have to drag it all the way up and look, the chart ends. So to preface this, the very, very first or second page in section 5 of the POH has a warning that says do not interpolate or extrapolate data from the charts. It is not valid. To me, what that means is if you're going to take any data from extrapolating or interpolating from the charts, it's not going to be accurate enough to make a legal or even actionable decision for your flight planning. However, I still do it. I extend these lines with my drawing line tool, and I extend these pressure altitude lines with my drawing tool, and I get a rough ballpark estimate for what the absolute and the service ceiling is going to be. And I don't use it for flight planning because I understand it's not accurate, but at least I know, okay, given these conditions, maybe somewhere in the 10 to 12,000 range is what the Seminole can comfortably maintain altitude at. Maybe somewhere in the 13 to 14,000 range, depending on the conditions. Does that make sense? So just beware. So a lot of instructors teach you to extrapolate. Know that that Section 5 warning exists. The POH advises against it. It is not good for actionable flight planning or legal decision making. Is that clear? I want to go to one more thing. So this chart is particularly useful for another one of these planning scenarios. And this again is going against that Section 5, do not interpolate, extrapolate. Pose you with this question. You're flying from Aspen back to Addison. And you've made it past the mountains, right? You're past the worst part of it. But then somewhere over West Texas, far northwest Texas, you've lost an engine. Field elevation's about 3,000 feet out there. You're in hard IMC conditions. Vertical visibility 500 feet in every single airport around you, and they're all non-precision approaches because you're in a rural area and they don't have that kind of equipment. What do you know about your aircraft to help you in that situation? What are you thinking about?
Think about whether I can maintain altitude.
Okay, so you get that from calculating your single, absolute, and service ceiling. So great, you did that calculation, you determined, yes, you can maintain altitude 1,500 feet over the ground. So you're skimming it. You're scud running the surface, but you can't even see it because you're in IMC. What's your next concern? All right, so how are you going to tell what your range is, single engine?
I guess you can get a rough estimate on this cruise chart. That's if you can maintain altitude at that current flow rate and everything else. So if you have a similar flow rate, then you're going to generally burn that.
Yeah. Let me ask you this. If you're single engine operating at your absolute ceiling, and you're just milking the plane trying to maintain that altitude, are you going to be in your 75% horsepower rating? Yeah, you're going to use 100, full throttle, everything to the wall, right? So if at 75% you're burning 11.75, It's 11.75 divided by 0.75. You do the math to figure out what that extrapolates to at 100% burn. Maybe add in a little safety factor because of all that extra drag and dead weight and loss of thrust that you have. Call it 15 to 16 gallons per hour. Great. Now how much fuel do you have in your tanks? Say it's 80 gallons. You have 15 gallons per hour single engine maintaining your absolute ceiling. How long can you fly?
5 hours.
Yeah, roughly 5 hours.
And as you keep going east, the elevation is
Exactly. Yeah, now we're thinking. So you can go about 5 hours. What's your airspeed going to be? What's your ground speed going to be?
depends on the winds.
It depends on the winds, but if you're holding blue line, it's going to be 88 plus or minus whatever kind of wind component you're fighting or having against you or with you, right? So let's say 88 and you have a 12 knot tailwind. Perfect, 100 knots. And you can go for 5 hours. Shoot, I can fly 5 hours for 100 knots. I could go 500 miles before I run out of fuel. And just like you said, Bowser, you can keep going on east until either the IMC conditions clear or the field elevation gets lower. And maybe you'll find a precision approach that gets you down 200 feet off the ground, below the clouds. But then you're asking yourself, based on the field elevation, based on my service ceiling, if it doesn't work out for me, can I go missed? Can you climb out? Well, you go back to that performance calculation. So again, this kind of critical thinking. It's not explicitly mentioned in the chart, but having at least a rough estimate of what your aircraft is capable of is going to be the difference between totally panicking and butchering a bad situation when you're all juiced up full of adrenaline versus being calm, cool, and collected and making a logical step-by-step process to get yourself safely out of whatever mess you're in. The other thing too is, let's say you get the engine failure over the mountains and your absolute ceiling is below the field elevation. You can still use that chart to calculate what your descent rate is going to be holding blue line. You can still make the rough same estimate. If I'm holding blue line, depending on what the winds are, how far can you drift before you hit the ground? Maybe you can go north and clear the peaks. Maybe you can go east and clear the peaks. Maybe you can go south and clear the peaks. Maybe you can go west and clear the peaks. How much time do you have before you get down that 2,000 feet if you're holding 88 at 100 feet per minute? So, next level planning. Any questions on all that? So that's the wrap up I have for you guys on performance charts. Once again, I'll conclude with the same little precursor that I said. I'm very biased. This is my favorite portion of all this. I understand a lot of it's like, oh, you're planning for doomsday, but 99 flights out of 100, none of that's ever going to happen. But in the business we're in, right, people pay us a lot of money to be prepared for all these kind of scenarios. I'd rather be. Performance calculations, scenarios. All right, we will go through the engine out flow now. We'll talk about the takeoff brief. We'll talk about flaps for takeoff. And maybe either after those three or before the third one, we'll take a little break. Sound good? Any questions before we jump to the next topic? Okay, so engine outflow. Raise the hands. Who has it pretty well memorized? That's scary. From what I told you guys yesterday, I expect all of you to come to class saying, yeah, I chair flew it 25 times yesterday, and I know it. It's that important. I'm telling you. If you get in the plane and you don't have this thing memorized, if you even get in the sim and you don't have this thing memorized, you're shooting yourself in the foot. Like, it is the single-hand most important thing to flying, at least in the twin. So you don't have it, as soon as one of those engine fails, you're going to panic, adrenaline's going to flood your mind, your vision's going to narrow to right in front of you 20 degrees, and you're going to be so frantic, you'll run it out of order, you'll bust everything because the ACS clearly says you need to follow the POH's or AFM's recommended procedure, and that's it. The more you know it, the easier it is, the more you can let that adrenaline out, and you can flow through it logically, procedurally, patiently, get everything right. If you don't know it, you're going to panic, and then you're going to build terrible, terrible primacy, and you're going to struggle with it for the rest of your training. So please, chair flight, chair flight, chair flight. Important thing to remember here is what kind of phase of flight you're going to be in when this engine failure happens, and how you might prioritize going through the flow. So just a little review. This is the pace you should be taking it at in the plane. There's no urgency. I know it's emergency engine outflow, but slow becomes smooth in multi-engine flying, and smooth is fast. I'll even write that down. It's the solo motto of the course. Slow equals smooth, and smooth equals fast. Fast equals sloppy, and sloppy is slow. If you try to rush anything, you're going to make mistakes, then you have to backtrack to fix it, and it's going to be twice as long as if you just took your time in the beginning. So please take that to heart. I'd even write that down on a piece of paper a few times. So engine outflow. Engine fails, take a second. Feel what the play's doing. It's not immediately going to roll into a VMC spin, especially if you have the airspeed. So don't mash rudders, don't try to raise the dead engine because you don't know what the hell's going on. Just take a second, feel where the plane's going. Establish directional control on your heading by using your ailerons and rudders as you naturally know how to do with however many hundreds of hours you have on your belt, right? And pitch in a direction that you're on your way to 88. You go mixtures, props, throttles. 1, 2, 3, all in the quadrant. As soon as you've done that, reestablish your scan and verify that you're maintaining your heading and you're still either at or very close to on your way to 88. Verify the gear's up, the flaps are up. Identify obnoxiously. This is another thing that a lot of people struggle with is they mumble, they're shy, they're quiet. If we fly together, we're going to have 8 hours of dual training. I'm going to get to know you, you're going to get to know me. I'll know what you're thinking as you're doing something. But as soon as you step into the exam with a DPE or an evaluating instructor, all that history is gone. So if you just go and skip gears and flaps because you looked at it and visually recognized it, they can only judge you on what you verbally say or physically do. So obnoxious. Gears up, flap 0, right leg is the dead leg, verify with the right engine. And then it's time to make a decision. Make sense? So first thing, go through it slowly and patiently, keeping your scan up to verify that directional control in the heading. Second thing, be very clear verbally with everything you're doing so that you can be evaluated properly. 3 scenarios where this engine outflow has slightly different priorities. I shouldn't say priorities, but maybe concentrations is a better word for it. So there's takeoff, there's going to be cruise, and then an instrument approach. So when you're on takeoff, you're naturally slow and in a high risk situation because you have a elevated pitch attitude, right? Usually holding about 10 degrees pitch up, your airspeed somewhere between 90 and 105 knots. So when you lose that engine, you're already close to that blue line that you want to maintain. So here, there is a large focus on immediately, but patiently, maintaining directional control and going towards 88 knots. And then continuing engine outflow. Make sense? Every single time you do the engine outflow, when the engine fails, I want you to take your time to feel what the airplane's doing, start establishing directional control as you've assessed it and getting to 88. Mixtures, props, throttles. After throttles, reassess your directional control before continuing gears and flaps. Make sense? But main priority on takeoff, you're already slow. So you're going to need to be a little bit more aware of where that blue line is because it's going to come fast. And if you don't pitch level to maintain it, it's going to run away from you and you're going to get slow and you bust. So that's the big thing here. 88 knots is not a pitch up attitude. 88 knots will minimize your descent rate until you finish your flow. Does that make sense? You will usually, in most cases, not be able to hold much of a climb. It's just going to minimize your descent until you finish the flow and you're properly configured after feathering to resume a climb. Good? Second one here is going to be at cruise. Same exact scenario. You get the engine failure, you feel it out, you establish directional control, but it's not as urgent of a pitch attitude to get to 88. Here your concern is just arrest your descent. You have an engine failure, you're going to have to troubleshoot. Maybe do a secure, but you have some altitude. Just make sure you're not losing it because it's pressure. So just maintain your altitude or a slightly higher pitch attitude so that you can be on your way to 88. But you don't need to be there immediately because if you're cruising around and you start immediately pitching for 88, you're going to do this. And then you're going to get here and you're going to get really slow and then it leads with all this silly business. Right? So just establish a pitch attitude so that you arrest your descent and start slowing yourself to 88 as you're continuing through that flow, and it's a bit of a multitasking element. Does that make sense? Good. Instrument approach. We maintain IFR, altitude, or glide path, if able, with 88 blue line or better. Make sense? On the instrument approach, you're going to be cleared. Maintain 2,000 until you cross over this point, or this heading, maintain 2,200 until established. or you might be cleared for the approach and you have a minimum crossover altitude for the final approach fix. Real life scenario, your IMC, you were given that altitude for a reason. If you start descending below it, there could be obstacles, there could be traffic. You can't see, you can't guarantee your visual separation. So you got to maintain that altitude. You're going to be doing 100, 120 knots if you haven't started descending yet. So it's the same as here. Just maintain that altitude. Pitch to maintain altitude, start running your engine out flow. Once you get through everything and you feathered, you should have no problem staying at that altitude until it's time to descend. Make sense? The only case where you're not going to stay at altitude is for whatever reason if you can't hold 88. But I guarantee you if you can't hold 88, it's probably because you're not going through your flow or something's terribly, terribly wrong. Make sense? So kind of 3 different phases that have a slightly different concentration of that initial orientation. Takeoff, you're going to be really, really slow. So you just got to pitch pretty much for level to arrest that drop in speed and get to 88 nice and quick, continue your flow. Patiently, but at a good pace so that you can get everything configured and feathered and continue climbing. Here, cruise, this is the easiest one. You've got plenty of time. Just arrest your descent and you'll be on your way to 88. Don't drag and take forever, but again, you don't have to be in a huge hurry. Take your time going through the flow. Instrument approach, just stay to your IFR altitude as you're simultaneously running your flow. Make sense? Any questions on those? Sweet. All right, so that's engine out flow. We'll talk about the takeoff brief. So takeoff brief, like I briefly mentioned, how many times can I say brief in one sentence? In the first presentation, there's those 4 scenarios that we're concerned with in the takeoff phase of flight. And based on where we are in those 4 scenarios, you're going to behave slightly differently or execute the engine out flow slightly differently. Make sense? So I really like to break this down in terms of a pattern, kind of a visual pattern in a table, because that's how I learn. So I'm going to do that on the board, talk you guys through it, and hopefully it kind of structures it in your mind in a similar way to learn as I picked it up. So first off, those 4 scenarios, they are broken or triggered by 3 different events, right? So 3 events between those 4 scenarios are the triggers. The first event is going to be that rotation has occurred. You've lifted off the ground. All right, so I'll put that down here, rotation. The second event in between 2 and 4 is going to be that the gear has been brought up. And the third trigger between events 3 and 4 is that you've climbed to a sufficient altitude. For training purposes, we're going to call it 2000 AGL. So these are the 3 milestones that separate our 4 scenarios that have different flows. Clear? All right, so 1. This is going to be on the takeoff roll. We're still on the ground. Rotation has not occurred yet. If we have an engine failure on the roll, both throttles equal idle, come to a stop. Very, very clear. Any questions on that? All right, second, we've passed the milestone of rotation. However, the gear has not been brought up yet. So we've rotated and the gear's still down. Scenario 2. Again, both throttles equal idle and you commit to land straight ahead. Now this one takes a little bit of explanation. So if you've taken off, you've rotated, the gear's still down, that means that you're still really close to the ground. Because like I gave you guys the homework yesterday, positive rate, tap the brakes, gear up, right? So it should almost be within a few seconds. That means you've got the engine failure a few seconds off your wheels touching the ground. You're still really slow because you're close to your rotation speed. You're still really close to the ground, if not still in ground effect. And now you have 180 horsepower using maximum power available, low angle of attack, 2,700 RPM, all of those pass factors, and this anchor here windmilling to the left. Except you don't know if it's this scenario or the other way around. You don't have time to figure that out. And it's going to steer you out of control quick. So you're just going to pull both throttles to idle to ensure that you've eliminated that asymmetrical thrust and pitch the nose over to get back down into ground effect. And if you're lucky, you'll have leftover runway. In Addison, you should always have leftover runway. And you'll just put it down straight in front of you. In the event that you don't have leftover runway, you're probably not going to be able to execute the engine out flow with the gear down and all those things happening. your best option is to still very smoothly bring the throttles to idle and land straight ahead, whether it's a field, a road, or whatever you can find there. It's your safest bet. Any questions on that? All right, 3. Now, rotation has occurred. The gear has been brought up. However, we haven't quite reached a significant altitude yet. In this position, we're going to run the engine out flow. Upon running the engine out flow, we're going to feather the inoperative engine because we've identified it. We'll declare an emergency if we have the time and the headspace to do it, and return to land. Make sense? So we're still pretty low to the ground. We don't have so much time, we don't have so much altitude, so we're just going to do the bare minimum. Oh, directional control, mixtures, props, throttles, verify the gear's up, the flaps are 0, identify, verify, feathering this engine, establishing my blue line. If I haven't already, I should have already. Climbing at your best rate of climb, blue line, until you get back to TPA, getting into the downwind, coming straight back into land. Safest option. Make sense? Last scenario, rotation has occurred, the gear has been brought up, and you have climbed to a significant altitude. You will run the engine out flow, troubleshoot, and assess the situation. You no need to feather, because you don't know what's going on. Right, maybe it's something silly, like, oh, the fuel selector got jammed in the off position and it was kind of delivering fuel, but it starved the engine, but I got it forward and now we've established fuel flow. I mean, that's something totally silly. You should have caught it in the pre-flight. But for the sake of imagination, right? It could be something harmless that just was missed and it's totally fine and the engine can operate and you can continue. Or maybe it's something that's working right and you need to properly secure it and come back to land. But you run the engine out flow, you try to troubleshoot it. If you can fix it, great. Make a decision from there. If you can't fix it, secure it, come back to land. So these are the 4 scenarios. Gear up is really the breakdown between no-go and go. So highly recommend that you guys study this structure, the 3 milestones and the 4 scenarios that exist around them, and how to proceed with the engine failure when you get them. Because this is the briefing that we're going to give before every single takeoff. And it's worth putting into your own words, because you're going to have to recite it and you will be judged on it. So for example, this is how I proceed mine. Right? There's 4 scenarios that we're concerned with an engine failure. First, if we're on the roll, the engine fails, we're going to pull both throttles to idle and come to a stop. If we've rotated but the gear's still down, again, we're going to pull both throttles to idle and stop. If we've rotated and the gear's been brought up, that becomes a go decision. For below 2,000 feet, we will run the engine out flow, identify, verify, and feather. If we have the time, we'll declare an emergency, come back to land. For above 2,000 feet, in that case, we're going to try to run the engine out flow and troubleshoot to fix it first and assess from there. A little 25-second spiel. Any questions on this? Sweet. You want me to leave it up for anybody to copy, take a picture? You guys have the mental endurance to talk about flaps quick before we take a break, or you want to break? We'll talk about flaps. It's short. Before I get rolling, go ahead and open up your POHs to section 4, please. All right, so this is kind of what we talked about yesterday when we went through the VMC scenarios that they're tested and discussed the flaps and that our flap setting is 0 for takeoff. So I'd like you guys to find in section 4 of the POH the checklist, the procedure for a normal takeoff, and on the following page should be for a short field takeoff. If anybody can't find it, please raise their hand or let me know. Give me a thumbs up when you get there. Alex got it. Mr. Tettleton's got it. Joe, you got it? Good. Brian, you got it. Elliot's got it. Brevin, you got it?
Look at it, it's like, keeps telling him.
Bowser, you got it? Okay, sweet. So in the normal takeoff, I'd like you guys to look at the note that exists right underneath the procedure. It says that you can use flaps for takeoff. You can use flaps 10, although it's advised that you use flaps 0 if there's any kind of concern for an obstacle underneath the departure end of the runway, right? It says something along those lines. So let's think about it. If you go into a single engine and you have a short field landing and you need to clear an obstacle, you add flaps 25 because it helps you get higher in a shorter distance before you get to that obstacle, right? However, what the POH, what the AFM is saying for the twin is exactly the opposite. If there is an obstacle, it highly recommends that you use flap 0. It's because of this paradigm shift. We're more concerned with risk management in the case of an engine failure than we are getting that extra bit of performance. We have two engines. We have a lot of excess thrust on the plane. It climbs very, very well. So clearing the obstacle of flap 0 isn't that big of a concern. The concern is if you get the engine failure, you're now dirtied up with 10 degrees of flaps that you're going to have to clean up and prevent you from getting to blue line quicker. Make sense? Going to the next page, there's the short field landing. And there's another similar note in there as well, saying it advises that if you need to conduct a short field landing, especially if there's obstacles, to use flaps 0 as your takeoff configuration. You guys all see that? Yes? No? Nodding heads? Good. So just be aware that that's in there. Bookmark it. Moral of this topic here is that yes, we can take off with flaps 10. There's nothing against it in the POH and the AFM. You should just be aware that it's ill-advised and usually not necessary, especially if there's some kind of obstacle there, because blue line is king. Any questions?
So for short field takeoff, so you know how like single engine you pitch off for us 56 for 50 foot and then level off to 74. This is saying just rotate at 70 and then climb at 82. And then is that the same like 50 foot where you hit 82 and then level off to 88, or is it just like a graph?
Yeah, once you get to 50 foot, that's where you can start configuring for your cruise climb. So that's essentially when you've cleared an obstacle. And I mean, in the real world, it's going to be a case-by-case basis. You'll want to hold for 82 as long as you need to, or as short as you need to, in order to clear that obstacle. So the big differences on that short field effort is a sooner rotation at 70 knots. Also, it's not explicitly stated in there, but you should be a little more prepared to bring your gear up. So instead of maybe waiting and delaying 3 or 4 seconds, positive rate gear up. As soon as you feel your butt lift off the ground and the wheels are no touching the ground, tap the brakes, bring the gear up, eliminate that drag, help you establish the best climb. This way you get over it, and then once you're there, you can reestablish your cruise climb, bring it to 90 to 105 knots, 10 degrees pitch attitude, 25 squared on the engine controls, etc., etc. All right, so resuming maneuver setup. This isn't necessarily concrete. It's not something mandatory, something that I find very, very helpful just to make sure that you don't miss anything as you're setting up and going through maneuvers, especially when you get to a stage check and an EOC and all the check ride nerves come in and you get task saturated. It's just, I call it a ritual, because if you do treat it like a ritual, it gets built into muscle memory and it'll just naturally happen for you. All right, so imagine this is your throttle quadrant. You're gonna have 2 levers here, which are the throttles. Next up, you'll have 2 blue levers, which are your props, and 2 red levers, which are your mixtures. So the ritual, as I call it, is just a verification that each one of these is set up properly before going to every maneuver. And the maneuver guide is designed to follow this same flow as well. 1, what it does for you is make sure that you're not missing anything. 2, it keeps the props on top at all times. And 3, whenever you're going props full forward, it puts a lot of stress on the governor because it has to put all that oil pressure in there to get the lower angle of attack, right? If you put the props full forward at a high manifold pressure, it's significantly more stress on the governor than if you put the props full forward on a low manifold pressure. So the third thing this flow does, this ritual does, is reduces the stress on those governors, right? So I call it working outside in, 1, 2, 3. So if you're setting up for a maneuver, you'll verify that your mixtures are set to roughly 1300 to 1400 EGT. 1350 is like a nice sweet spot. It doesn't need to be perfect. If you see the first 2 digits, 1, 3, you're good. Set your throttles for whatever maneuver you're doing, and then set your props for whatever maneuver you're doing. So just an example, let's say we're going into steep turns. So you climbed up to 3000. You're going to set the mixtures for that altitude. You're going to set your throttles to 20 inches, and you're going to move your props, if you're coming from cruise, forward to 2500. This way you've worked outside in on the quadrant and you're all set up. Make sense? Another good example where this practicality for taking care of the governors comes into place is slow flight. First thing, you set your mixtures for the altitude. You bring your throttles to 15 inches, and then props full forward. A lot of people forget to put props full forward, so this ensures working outside in, you got them. And also you reduced your manifold pressure before you went props full forward and introduced all that oil pressure into the governor. Less stress. Make sense? So for every single maneuver, if your first thought is pre-maneuver checklist, set up outside in, you're going to be in really, really good shape. There's two exceptions that one element precedes this. And that's going to be VMC demo and emergency descent. Now, of these two maneuvers, is there anything you guys can identify that they have in common? It's not blatantly obvious. It might be a stretch asking you guys.
88 knots,
Cow flaps closed.
Cowl flaps closed. VMC demo, in order to get configured for it, we're going to first configure the airplane to represent an OEI operation with the critical engine in op. So when we bring that left engine offline to idle, it's going to be really cold. Hence, you want to close the cowl flap. So you close the cowl flap first, preceding your outside in flow mixture set for the altitude, 15 inches manifold pressure, props full forward. Same thing with the emergency descent. You're going to be descending with both throttles idle at a fast speed, introducing lots of convective cooling to the engines. You want to close those cowl flaps to make sure they don't get shock cooled. So you close the cowl flaps, proceed, set your mixtures, usually to full because you're descending. You don't know how low you're going, so it's better to have the fuel. Throttles idle, props full forward, gear down, bank over to 30 degrees, pitch the nose over to 120 to 140, right? But both of these, what they have in common is that one, if not both of the engines are going to be riding idle for an extended amount of time. So you want to take care of them by closing the cowl flap first. Make sense? Second thing is on these two maneuvers, as you're cleaning them up, something that I want you to get planted in your mind very, very early is on the MFD. So on the right side, you're going to have this soft key that takes you to the engine page. And this shows you all of your engine instrumentations, temps, and EGT pressures. You're going to have a little bit of a gauge here that's going to show you CHT, and there's going to be like a green bar that exists here. Imagine these are progress bars. Every single time you finish this maneuver, let's say VMC demo, you've done the stall indication, you pitch the nose over, you've recovered. It's time to clean it up. First, you want to bring the engines to roughly 15 inches of manifold pressure. You're going to hit that engine button to take a look at your CHTs, your cylinder head temperatures. And if they're in the green, this is where it's important to have the mental tie together. If your CHTs are in the green, open up your cowl flaps and then resume balancing out your throttles to full. The whole purpose behind this is like starting your car in the winter, right? If your car's been sitting at night in the garage, the engine's really, really cold, you're not just going to turn the key and then start revving it up to 5,000 RPM, right? It'd be terrible. There's so much heat being introduced, everything's still cold, the fluid's still cold, the oil's cold, everything's pumping hard, temperatures all different all over the place, things are expanding and contracting, loads of stress. So if the engine's just been cooled so much, we bring it to 15 inches manifold pressure, that's roughly at idle setting. It's going to warm up nice and slow, and then once it gets warmed up, we're free to go full throttles. The important thing though is as soon as you see it in the green, tie it to, oh, my cowl flaps are closed, I should open them while I'm still slow, because if you balance out the throttles, you accelerate, you're going to be fighting all that relative wind to open up the cowl flaps, and you're going to have a really hard time. Make sense? Cool. So that's maneuver setup. Do you guys want to talk about crossfeed again? We kind of hit that yesterday. Is there any confusion on that? No, 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 no. Good. Reagan, right? Excuse me. Okay, so next is going to be VMC demo. Raise the hands, honest hands, who's pretty familiar with it from the maneuver guide right now? Okay, so I'm going to break it down kind of systematically into 3 different sections for you guys so you have a good understanding of why we do it the way we do it. So first, there's going to be the configuration. Second will be the actual VNC demo plus recovery. And third, I call it the cleanup. So if you guys want to pull up your maneuver guides right now, it'd be good for you to visually look at it as I'm speaking through. So the whole maneuver can be broken down into 3 sections. The first part is all configuration, as in you're just establishing the aircraft to represent that your critical engine has been inoperative, establishing a nice 0-degree side slip with 2 to 3 degrees of bank, etc., etc. So this is where you go cowl flap closed on the left engine. You bring the manifold pressure to 15 inches after setting your mixtures, of course, because you've done your ritual, right? So cowl flap, ritual, set the mixtures, 15 inches manifold pressure, props full forward, and then slowly bringing the left engine offline to idle. So the reason you go 15 inches of manifold pressure first is theoretically, yes, you could just blow straight into it and pull the left engine straight to idle, except now you have all that passed and it's going to be really aggressive. So going to 15 first just slows you up, reduces the engine power so that when you go idle on the left, it's a lot more controllable. All right, so you went idle on the left engine and you're still not done configuring. You're going to slow to blue line by maintaining altitude and then very, very gently, slowly increase the right throttle to full. And you should just take a second there and pause at your blue line, 0 side slip condition. Big importance in adding that right throttle to full is it's going to increase your past factors proportionally. So you have to be ready with the right rudder. This should be almost tied together going in full. Make sense? So once you've gotten there, you've slowed to blue line, left engine's in op, right engine's full. That's the end of the configuration phase. You've configured yourself to represent the critical engine in op. Make sense? Any questions on all that? Okay, the second half is going to be the VMC demonstration and the recovery. So this is quite simply demonstrating the recovery process if you are either to one of 3 things: lose directional control, get a stall indication, as in the stall horn, or flat out stall. This is the recovery process we do to get out of that scenario. So the first half we're going to encourage it by pitching up and slowing our airspeed, and the second half we're going to demonstrate that scenario. Remember the critical density altitude slide I showed you? We're going to get the stall horn first in 9 out of 10 cases because we're operating in that regime. Only time you wouldn't is if the stall horn's not functioning properly. At that point you would get an actual buffet, and it's important to recover at the buffet. So first of 3 indications you get: stall horn, buffet, loss of directional control. All right, so this begins, you're establishing your 0 side slip, 88 knots. You start pitching up very slowly, just to bleed off your airspeed about 1 knot per second. You keep pitching up, bring your pitch attitude to roughly 15 degrees pitch up. No more than that, but it requires substantial and continuous pressure to maintain your dot on 15. As you slow to about 65 knots in our Seminoles, you can expect the stall horn. And this is where it's very important. Your first reaction should be to very slowly reduce power on the operating engine and let the nose start coming over. It can be simultaneous, but in order of priority, operating throttle comes out in order to eliminate all those pass factors, and nose comes over so that you can gain airspeed and accelerate back to a point where you have authority on your control surfaces. Make sense? So 2 things: you're eliminating the pass that's steering you out of control, and you're gaining airspeed so that you have more authority from your control surfaces. Good? This whole time that you're doing those 2 steps, it's very important to keep your feet alive. They should be reactive, not proactive. If you try to think that your right foot is attached to the right throttle and guess, you're going to get it wrong. If you go very, very slowly and you feel the plane as you're doing this and add the right rudder as needed, you'll be able to maintain your heading nice and smoothly. So you're pitching the nose over all the way to about 5 degrees nose pitch down. That's a healthy balance in our planes where you'll see the airspeed accelerate at a very manageable pace. And as soon as you see that airspeed growing, you can start very slowly reintroducing the right engine to full and managing that right rudder as well to maintain your heading. So what this is doing to you, you're accelerating airspeed, and now you're reintroducing engine power while you have the authority to balance the past and reestablish your blue line condition where you're most capable to fly or deal with anything you need to do. Make sense? So that's the whole VMC and VMC demo and the recovery. Step 1, configuration. That's your cowl flap, your ritual, left throttle out, right to full. Then you go into the VMC demo, slow pitch up, recovery procedural, throttle out, nose in, throttle slowly in, reestablish blue line. Then the cleanup. Now we're following that same procedure. The critical engine's been idling for a long time. It could be cold. So you bring it to 15 inches manifold pressure. You verify that the CHTs have warmed up to at least in the green indicator. Once they are, you have that mental note, oh shoot, the cowl flap's closed, I better open it before we get too fast. You open the cowl flap, and then you can bring the throttles to balance them out. And that's the cleanup. Make sense? Any questions on it?
It's basically like a power on first indication stall.
No.
No.
No. It's power on, you get the stall and you go power full. Here you get the stall, not either. It's power off, again, you get the stall and you go power full. Here's the exact opposite. You get the stall indication, you pull out your power because you eliminate that pass from putting you into a VMC condition. So it's exactly the opposite. It shouldn't be confused. You eliminate the power, pitch the nose over to accelerate, and once you've accelerated, you can slowly and manageably with the rudder reintroduce the throttle to reestablish your blue line straight and level. Yeah.
On the standard, it says recovery airspeed plus or minus 5 knots
Mhm.
on 88. So it's just whenever we get to 88, just hold that.
Exactly.
Okay.
You're going to hold 88 on the climb out.
And then we're coming back to the altitude at which we were at.
That'll be up to the evaluator's discretion. Cool. Now we'll segue this straight into the troubleshoot versus secure. This kind of went off of Brian Hahn's question. Unfortunately, he had to step out. A lot of times when you're finishing the VMC, especially on a stage check and EOC, for the sake of time and being efficient with the flight, the evaluator will give you a prompt, a verbal cue that, oh, that left engine, the critical one that you still have idling before you did this cleanup, is on fire. It's smoking. It's shaking violently. Something has gone urgently wrong with it. If there's something urgently wrong with it, as in like you have a clear indication that it should not be operating, there's no reason to troubleshoot it. You want to secure it immediately. Make sense? That goes for at the end of the VMC demo, or if you're just flying around at cruise. If we're up at 6,000 feet, 23 squared, in between maneuvers, and I look over to the right engine and say, oh shoot, we struck a bird. The right engine's shaking violently. I think the prop's bent. I go, yeah, the prop's bent. It's shaking violently. You can't troubleshoot a bent prop in the air, right? It just needs to be secured. So you're going to go straight to the secure checklist, and the memory items for that will be throttle, idle, prop, feather, mixture, cut. Establish your blue line, 0 side slip, pull out the checklist, run through the secure checklist. Make sense? On the other hand of that, if we're flying around and I just pull the left throttle to idle, that's a simulated engine failure. You don't know what's going on, right? In that case, it's unknown. Is there a problem with the engine? Should it be shut down? We don't know yet. So that's when you're going to do the proper engine outflow, mixtures, props, throttles, gear flaps, verify, identify, verify, feather. Just kidding. You're not going to feather because you're above 2,000, you'll troubleshoot. So let me rehearse that one more time. Left engine comes out. It's a simulated engine failure. You don't know what's going on. You're going to run through your engine outflow, and at the end of it, you need to make a decision. Are you under 2,000 feet? If you are, feather, return to land. If you're above 2,000 feet, troubleshoot it because you don't know what's going on. And in most cases, especially in training flights, evaluation flights, you're going to troubleshoot it. The instructor, the evaluator will tell you, oh, none of that worked. So then you got to go through the secure checklist and you secure the whole thing and they say, all right, demonstration over, let's air start it, and you go through the air start checklist. Make sense? So, moral of this whole story, if there's something urgent, violent, dangerous, bad going on with the engine where you have a visible, clear indication that that engine, either right or left, should not be running, go straight to secure. Throttle out, feather, mixture. If it's unknown, the instructor pulled the fuel selector, pulled the mixture, simulated throttle out, just the engine died out of nowhere. Engine outflow, troubleshoot. Make sense? I suppose on that note too, with these simulated engine failures, below 3,000 feet, it's always going to be a pulled throttle to idle. So if we pull the throttle on you, you will have whichever one is remaining standing. Try not to touch the one that's pulled idle. So you'll run your flow. If you do need to feather, never pull a propeller to feather, right? Always, always, always. Once you identify and you verify with the throttle, just point with one finger and say, I would feather this one. And then look at your instructor. And the instructor will either give you the heads up, saying, yes, you can go ahead and feather, or if you're at a lower altitude doing something different, they will simulate a zero drag condition to you by adding a certain amount of manifold pressure, and that throttle that they pulled will belong to them, and you will have ownership of the other one. Make sense? Same thing goes for mags. When you're running the secure checklist, there's going to be a point where you can turn off the mags on the inoperative engine to secure it. Always, always, always point to them with your fingers and say, I'm going to shut off these. Wait for a nod from your instructor, shut them off. So two things. Never feather the propeller, never shut off some mags without getting some kind of okay from your instructor. Make sense? That's just for safety, because none of us want to be up in the air when we've pulled the mixture on the left engine and you were trying to go fast and you got sloppy and you pulled the feather on the right engine, and now we're a glider. Very heavy glider. It sucks. So just err on the side of caution.
Does that happen to you?
No, because I always brief people very, very thoroughly. I imagine it will one day.
Yeah.
But I have very fortunately not have had to deal with it. It's been close. It almost happened once. I was like, oh no, think again. All right, so that goes through that checklist. We're doing really good on time today. It's only 2 hours in, and we probably only have an hour of material left to go through, and that's even if I stretch it. You guys have any questions? So, if we finish an hour early, I'm just gonna have to think of stuff to talk about. And that could get boring. What do you got, Reagan?
Did you ever practice put the rod engine out or no?
For the VMC demo or engine failures?
Maybe any of them.
Engine failures, yeah. It's just random selection. I like to switch it up with the engine failures all the time. In terms of VMC demo, I'll have all you guys do it with the left engine first, at least until you're pretty proficient with it. And then when you're proficient, because it's ace or counter-rotating propellers, I'll say, hey, this time around, let's do it for the right, just to switch it up on you guys. So yes, but not primarily. Good question.
Do we have a critical engine then? If it's like they're both counter-rotating, right?
Not a true one, no. I mean, they're both going to give you all of those past factors,
Yeah.
but it'll be equal on both sides. Good questions. Anything else? All right. Gumps. Gumps. So this is your before landing checklist. There's no real before descent checklist in the Seminole. You don't have to pull throttles. You don't have to do anything. It's as simple as pitching the nose over. The only thing you want to be aware of in descending in the Seminole is if you're making a very high descent or covering a lot of altitude in your descent, there's going to be more or less oxygen depending where you're going. Right? So if you have manifolds pressure to 23 squared, and your mixture set to 1350 at 8,000, and you descend all the way to 2,000, by the time you get there, your manifold pressure is going to grow, and then also you're going to be running really, really lean because there's more oxygen available but less fuel. Make sense? So the only descent checklist is keep an eye on your throttles and keep an eye on your mixtures and make small adjustments as you need to. Besides that, you pitch the nose over and you have so much tape before you get to the yellow. Make sense? Good. Now, Gumps is your before landing checklist. So you don't have any kind of formal thing like you do in the Archer. It's all included in Gumps, and then you just follow the procedures that we have for either the instrument approach or the short field landing. Make sense? The G is for gas. 2 S's or one? One. Yeah. The U is for undercarriage. These two always get confused. People think about gas, or G stands for gas. It means to check your fuel selectors and your fuel pumps, but people mistake it for gear. So just try to drill that into your mind. G is for gas. It's going to be your fuel selectors, which are located in between your seats. There's those 2 levers that you can switch to cross feed or to off. You're not going to be able to visually see them very well, So it's good to get in the habit of just sticking your hand backwards slightly behind you in between the seats and doing a swipe forward and feeling with your fingertips to catch those little tabs and see what position they're in. Full forward is on. So for gumps, you just go gas, stick your hand back there, full forward on, and you verify that the fuel pumps, the auxiliary fuel pumps, are turned on. Those are located just underneath the yoke. They have little red linings on them. Make sense? So gas, they're just going to be fuel selectors plus pumps. Welcome back. That was fast. U is for undercarriage. I know a lot of you want to refer to the gear as gear, but in this checklist, just refer to it as the undercarriage so you don't get confused. Personally, I say I'm dropping my undies because it's comical and it helps me remember and not say gear in the G part. So gas, fuel selectors on, fuel pumps on, dropping my undies, dropping the gear down. Now, when you're running your gumps, if you go through the maneuver guide, there's that visual call out that you're supposed to check the mirror and verify that you have 3 green. And you guys are going to get really, in the zone, feeling like a badass pilot every single time you drop the gear and go, I have 3 green, 1 in my mirror, can you verify? Here's the caveat. When you drop the gear down, it's a 6 to 10 second cycle in order for the gear to come down. So that's 6 to 10 seconds until you get that 3 green, 1 in the mirror indication. Don't wait for it. G, U, jump straight to M. Forget about verifying the gear until you've finished running through your gumps. And if you don't have the time at the end of your gumps, you're going to do one in your base leg. You're going to do one in your final leg, so just verify it there. On the instrument approach, you're going to do one more at least as you're descending, and you should do a third one 300 feet above minimums. So you're always going to run at least 3 gumps before an approach. The first gumps is to do everything. The second gumps is to verify everything. The third gumps just solidifies that we want to go props full forward on final so that we have max power available in terms of a go-around, and also because we're in a training environment and we really want to drill it into your guys' brains. Make sense? First gumps do it, second gumps verify, third gumps for props full on final and to drill it into your brains. Good? And the moral of all that was don't wait for the undercarriage to get your 3 green, 1 in the mirror on the first gumps because you can just verify it on the second one and the third one. M equals mixtures. Technically that falls under gas, but mixtures will be the mixture controls. And right next to it on the quadrant will be props. If you're in the downwind, if you're in the base, if you haven't gotten to your final approach fix yet, or you are not 300 feet above minimums, you'll just make sure your props are synced at 2,500 and you'll state that you're going full on final. Beyond that, you don't actually have to physically move anything. It's just a reminder that you're going full on final. Make sense? And the S is your seats, seat belts, and switches, just making sure that they're all fastened. All of your lights are coming on to landing. Make sense? So a quick run through. If I'm in your guys' seat, right? G, gas. Fuel pumps on, or fuel selectors on, fuel pumps on. U, dropping my undies. M, mixtures full forward. Props, they'll go full on final. Switches all on, seat belts fastened. That's my gumps check. Shouldn't take any longer than 10 seconds. The second time through, you're just verifying. Gas, on, undercarriage, 3 green, 1 in the mirror. Can you verify? Always ask your co-pilot, can you verify in the mirror? They'll verify. Mixture's full, that's just a verification. Props, stating again, full forward on final. Switches, they're all still on and our seatbelts are on already. The last one, you're really just looking props full on final, especially if you've done those first 2 already. Make sense? Any questions on that? All right. Hey, can you close the window over there? This is probably going to get in the way of your audio. Thank you. Yeah.
Sounds like views.
Okay, so up next we're going to talk about the instrument approach procedure. I'm going to break it down for you in terms of a 2-engine instrument approach, and then we'll break it down how you proceed with a single engine depending where you get the engine failure. So if you guys have gotten tired or you're sleepy or whatever, I highly recommend that you kind of bolster yourselves and gear up for the next 30 minutes, because this instrument approach right here is the single criteria that people fail the EOC on the most, or the check ride on the most. Causes the most confusion. What's that? Alrighty. Alright, so basic instrument approach course. We'll draw the final approach fix here. We're gonna have a 1 mile checkpoint, a 2 mile checkpoint, and a 5 mile checkpoint. And the rule that we're gonna follow for the 2 engine approach is the 5-2-1 descend rule. That's how we're gonna break up all of our procedural steps. Make sense? And the descend comes at the final approach fix or your glide slope intercept. All right, but for simplicity, we're just gonna start as if we're crossing over the final approach fix every single time at the minimum crossover altitude. Good? So 5 nautical miles. I title this slow down because everything we do in this step is just to help slow the airplane down. So 5 nautical miles, you slow down. You're gonna go 20 inches on your manifold pressure. Props will go 2,500 RPM. And verify that your cowl flaps are open. This third one here, it's not super important. It's not gonna make or break your instrument approach. This is more for your guys' help being in a training environment. Because when you're introduced to the plane, you might do 2 instrument approaches, 3 if you're lucky with 2 engines operating. Every single one after that is going to be single engine. And when you're single engine, you have the cowl flaps open underneath. There are those little hatches. They create a little extra drag, which adds stability and kind of anchors you from that yaw moment. It also helps slow you down a little bit when you're already descending, which prevents you overspeeding the flaps as you're trying to run your engine outflow and do the proper configurations. So not necessary, but it's in your best interest knowing that you're going to get the instrument failure somewhere on this approach. Make sense? So 5 nautical miles, you want to slow down by going 20 inches manifold pressure, 2,500 RPM, and verify that your cowl flaps are open. 2 nautical miles, we're going to run gumps. And this is where it's really important how I was stressing on the U part of gumps, the undercarriage. Put it down, go straight to mixtures, props, switches, and seat belts. This is going to be your very first gumps. There is absolutely no reason to sit there for 6 to 10 seconds and wait until you get 3 green and ask your co-pilot to verify, because in those 10 seconds you're going to be continuing on and on and on, and you'll get here before you go to mixtures, and then you'll get here when you go to props, and then you'll get here when you get the switches, and then what happens? You're past the final approach fix, you're behind the airplane, you're speeding through, you're not configured to land at all. You're going to ruin your whole instrument approach. So just put it down, continue. You'll catch it in your next gumps either here or here. Good? 1 nautical mile. Very easy. Flaps 10. What's our flap speed? Maximum flap extension speed? 111. What's our maximum gear extension speed?
140.
Yeah. And what's the restriction to pull a throttle to a lower manifold pressure? There isn't one, but all 3 of these things slow you down. So logically, which is the one that you're least restricted to do? Pull the throttle. And then the second?
Gear.
Good. And then the third? Good. We'll circle back on that in a little bit. So gumps will get your gear down. This is going to slow you. This will slow you below 140. Getting the gear down will help slow you below 111. Getting your flaps down under 111 will help slow you to 90, which is roughly your descent speed. You see how that all works? Again, we're going to circle back on this later. I've had circumstances in the winter when we have very, very good performance days, especially with the new Seminole that hasn't been broken in and has great performance, that with flaps 10 and 20 inches manifold pressure, you're still pushing that 111. This 20 inches of manifold pressure is a suggestion. It is not law. It's not published in the POH. It's not in the ACS. So use it at your discretion. It'll work for 9 cases out of 10. But if you're here, the gear's down, and you're screaming at 115 for whatever reason, bring it to 18, bring it to 17, get below 111, put in the flaps 10. Make sense? All right. At the final approach fix, manifold pressure goes to 15 inches, and you're going to pitch down to descent. You're just going to nicely start following the glide path. Super easy. Yeah? Right here, about that point, that's where you should be comfortable in your descent. You're on the glide path, you're on your course, everything's going nicely. Run gumps, numero dos. Straightforward. The U, that's where you can go 3 green, 1 in the mirror. Ask your co-pilot to verify. Props still don't go full because you're not on shore final yet. So it's really just verification of everything. Right here, roughly 300 feet above your minimums. I'm gonna do gumps number 3. And the big highlight is the P, props full on final. Reason being is if you have to go mist, you have to go around, you have the maximum power available to do so. You're configured for it. The reason you don't do it sooner is because the thrust characteristics there at 15 inches of manifold pressure are very unstable, and it creates a lot of drag. So it's going to slow you more than you want. You want a nice, steady, stable approach, so you keep it at 25 until you're on short final where you're good to put them forward. Make sense? Now, when the landing is assured, let's call that roughly here, flaps code 25. If you want them, you don't need them. I like it, adds stability, slows you properly. If it's really windy, you can land flaps 10, no problem with it. However, you want to wait until the landing's assured. Why? If you got to go mist, you got to go around, get an engine failure, more stuff to take out. Make sense? Cool. So this is just standard instrument approach. I know it looks like a lot. Try not to read too much into this. Just think of it as 5, 2, 1, descend. You're always going to run these gumps and flaps 25 when landing's assured, despite what the scenario is. This doesn't really change. This is just basic logic, right? This is kind of the core milestones to remember. Any questions on that? Now, red marker is going to highlight the procedure that we do when you lose an engine. I'll put it up here. So this flow, I've named it the top-down flow. I'll explain it in a moment. Now, this screen isn't on. Do you guys go ahead and go on your iPads if you have a moment and pull up that picture that I showed you yesterday on Piper's website that has what's equivalent to our posters for chair flying. If you're super familiar with the cockpit and you know where the throttle is, you know where the gear lever is, and you know where the Johnson bar is, then you'll understand this. Give me a nod when you've gotten there, or if you feel confident. Good? All right, so top-down flow. This top-down flow is named so because you are working on the flight deck vertically from the topmost component down. Very straightforward, right? The throttle will be the highest of these three things, as in it's in the quadrant. The gear is slightly underneath the quadrant in the middle, and then the flap is all the way on the floor. So vertically, you're working top down to introduce these configuration changes. Make sense? Not only is it physically top to bottom, it is airspeed restriction top to bottom, like we just covered. There's no airspeed restriction to pull the throttle to 17. The gear restriction to come down is 140, flap is 111. So you're working top down in that sense as well. And then the big kicker, the place where you run the top down flow is going to be at your top of descent when you're running single engine. So if you're single engine, at the top of your descent, you're going to run the top down flow to get configured. Make sense? That's going to be true whether it's an instrument approach and you're crossing over your final approach fix. That's going to be true if it's a single engine pattern and you're at your beam point for whatever you want to land on. That is the top of your descent. You'll run the top down flow in order to configure yourself for that descent. Make sense? Now where this gets introduced and how, we're going to overlay onto this. Make sense? Okay. When you get an engine failure, this 5-2-1 rule goes out the window. It no longer exists. It's no longer relevant. You're going to follow it as far as you get until you get that engine failure, but whenever you get it, it goes out the window and this dominates. Make sense? So it's never going to be a perfect world like this, but you can kind of segregate how the procedure changes in 3 different phases of the instrument approach. So first will be roughly here, area 1, where you've slowed down, but you haven't introduced the gear yet, you haven't introduced flaps yet. However, you haven't descended, so you still have quite a distance to go and maintain your altitude before gravity can help you out, right? Second will be somewhere within this pocket. You've ran your gumps, your gear is down, you've introduced a lot of drag. However, you still have a certain amount of distance to go before you can start descending. So you got to think about, okay, the gear, it's dragging me down. Can I maintain altitude in blue line? Maybe. Maybe not. Maybe I need to make a configuration change. Maybe I can keep it, right? We'll talk about it in a little bit. Third one, you're past your top of descent. You've had the engine failure, your gear's down, your flaps are in, but now gravity's assisting you. Again, you got to make the decision. Can you maintain the glide path and at least 88 with those configuration elements in there. Maybe you got to clean one of them up. Maybe you keep them both in, right? We'll go into that. So first one, I'd argue the easiest one. You get the engine failure here somewhere before you've ran the gumps. First concern, pitch for IFR altitude, and then the caveat is at least 88. You got to maintain at least 88 knots or above. If for whatever reason you can't maintain 88 knots, you're doing something terribly wrong. You're probably like frozen for 20 seconds and you haven't ran your flow. So pitch for IFR altitude and at least 88 knots. As you're doing this, you run your engine outflow. Two things to highlight here. Gear will be up, flaps will be up. And with your engine outflow, you feather. Always, always, always. On the instrument approach, your intent is to go into land. So you're always going to feather, even if you're above that 2000 AGL rule that we had on the brief, right? Because it just doesn't make sense. You're coming into land, you're multitasking, trying to follow this procedure, talking to all the controllers. You're not going to introduce more complexity and try to troubleshoot or secure. You're just immediately going to go into feather to give you the best chance. Make sense? From here, you're going to maintain IFR altitude to your top of descent. And then at your top of descent, you'll run the top down flow, TDF. Then you run your gumps once you've established the descent, and you follow the rest of this. That doesn't change. So to walk you guys through this scenario-wise, you're flying in, you're on the instrument approach. You got 5 nautical miles, you've got cleared for the approach, let's say, maybe not, you got your vector. 2025, you verified your cowl flaps open, you're nice and slow. You're doing maybe 125 knots. Boom, engine failure. All right, you're gonna pitch to maintain directional control in your IFR altitude. Mixtures, props, throttles. Still verify again, pitching for IFR altitude, I'm not descending, and on heading. Verify the gears up, flaps are down. Identify, verify, I'm coming into land, I'm going to feather this propeller. I'll go ahead and simulate zero thrust for you. At that point, the rest of that 521 goes out the window. You're just cruising at your IFR altitude until you get down to your top of descent. When you get to the top down of descent, you run the top down flow. Throttle comes to 17, gear comes down, flaps come 10, pitch the nose over. Try to maintain straight and level as you're doing this. Don't try to be a perfectionist and sit there fine-tuning the throttle like, I need exactly 7. Just pull it down close enough. When I'm simulating zero drag for you, I'm going to use about 10 to 12 inches of manifold pressure, and the throttle might be right about here. 17 inches of manifold pressure is like right there. So if you just pull it to close enough, you're going to put yourself in a great position. If you put the gear down, put the flap in, you're going to put yourself in a good position, and you're going to have all the time you need to come back after that and finally adjust that throttle to 17 or whatever you need to establish the descent with 90 knots. Make sense? Rule of thumb here, don't spend too long trying to get perfectly 17 because you're going to end up blowing straight through it, getting way above the glide slope full deflection. Just pull it close, gear down, flaps, reassess. Now, as you're descending, this is another one of those seeds I want to plant in your mind. If you're just chasing a glide slope or a localizer or a path, and it's quiet in the cockpit, and you're just waiting for the next thing, you should have alarms going off in your head saying you're forgetting something. I need to run another gumps, right? You shouldn't panic that you need to do 40 of them, but if you feel like you're not doing anything in the plane, run another gumps. Make sense? So once you've established the descent, you ran the top down, you're cruising, you're on glide path, you got your 90 knots, everything's hunky-dory, run that gumps number 2. You keep descending, 300 feet above minimums, run another gumps just to verify. Your props are going to be full forward anyways because you ran the engine outflow. And then this is the important point. Only go flaps 25 when your visual and the landing is assured. Per the POH, per the AFM, only when the landing is assured, we add flaps 25 on a single engine approach, and we do not go flaps 40. If you had to go around, if you had to go missed for any kind of reason, it's way too much drag, it's a bad situation. Make sense? So this is the easiest scenario right here. Any questions on it? The only way it can get more complicated than this is what sometimes we'll do to more advanced guys, is we'll give you on a vector onto your final approach course, And as we give you that PTAC clearance, we'll fail the engine because now you got a multitask of maintaining your heading, running the engine outflow, turn to intercept the course, continuing, etc. So that's where this one could get dicey, but for the most part, it's very straightforward. All right, number 2, we've slowed down and we've ran the gumps and the gear is either in transit down or put down. Maybe the flaps are in. Same thing. Pitch for IFR altitude, at least 88 plus knots. Or blue line if it's a different aircraft. Proceed with the engine outflow simultaneously if your headspace allows it. Feather, none of that changes. But there's the caveat. Gear plus flaps, or rather I'll split it individual. The gear is an assessment, flaps is an assessment. This is what makes this one so complicated, is it's all depending on your specific scenario, what the conditions are, and where you are on the approach. If you're right there, 1.8 nautical miles, the gear's in transit all the way down, bring the gear up, bring the flaps up. Because if you're that dirty and you're operating single engine, you will not be able to maintain IFR altitude all the way to your top of descent. You'll descend 200 feet over, you've busted the basic instrument approach criteria, and you're at risk of hitting obstacles. Make sense? So if you're anywhere near that 2 nautical miles, clean it up. If you're right here next to the final approach fix, I'm not going to give you a particular distance because that leads to bad habits. But if you're running your engine outflow and you've gotten to the point where your hand is over the gear and you're making that assessment, you should pause and think to yourself, okay, I have point X nautical miles to go, my airspeed's 110 and I am 50 feet over the minimum crossover. I can stretch it for this point, whatever, 100% full confidence. At that point, leave it in, because it makes no sense to cycle it, wait 10 seconds, get to your top of descent, and bring it all back down again, right? Then there comes that middle regime. Maybe you're 1 nautical mile away, and you don't know. You're right at your IFR altitude, you're at like 98 knots, gears down, flaps are in. At that point, it just comes down to how familiar you are with the aircraft. I always err on the side of caution. I'll bring it up, or at least put the flaps down and see if I can leave it with the gear. If that doesn't work, bring it up. But if you have any doubt and you're a mile, some kind of extended distance, just bring it up. You're not going to bust for making a safe decision. But you will bust for thinking, oh, I can stretch it, I'm leaving the gear down, I'm leaving the flaps in, because then you'll find out that you can't maintain 88, you'll get 200 feet under. And the other more practical consideration is if you get in the habit of, oh, during training I did it 4 times that I left the gear and the flaps in, and I stretched it from 1 nautical mile, the next time you might be flying out in New Mexico and the field elevation's 400 feet higher and the temperature's 25 degrees hotter, but the aircraft's exactly the same. You think you'll make it then? Probably not. So always play it on the side of safety. Big thing is it has to be a true assessment, and you're going to learn from experience. If you're close to here, bring it up every time. If you're right here and your hand's making the assessment, you have the airspeed and the altitude, leave it in. Don't task saturate yourself. After you've ran that engine outflow, you've feathered, you're going to continue maintaining IFR altitude to your top of descent. At the top of descent, you're going to run your top down flow. Now given, if you've decided to leave your flap in, you've decided to leave your gear in because you're so close, at least treat that as a verification. Top-down approach, throttle comes to 17 from full. You'll have to do that. Gear's already down, flaps are 10, hunky-dory, pitch down, start descending. And then you run your gumps, and the rest of this is all the same. 300 feet above minimum, you run your 3rd gumps to finish verifying everything. If you go visual and the landing is assured, flaps come to 25. An important caveat that I forgot about in the first explanation, as you're descending all the way down here with your 17 inches, you need to maintain at least blue line. There's a lot of confusion here. The POH wants us to hold 90 knots, so we're going to pitch for 90 knots. The ACS gives you plus or minus 10 on this instrument approach section. Once you've gone visual, and it's a visual approach to landing with a single engine, you get plus or minus 5 of that 90 knots. So in summary, you get 80 to 100 all the way down until you're visual, and then you get 85 to 95 when you get to the threshold. That's what the ACS says. In my personal opinion, it's way too lenient. I don't think that you should ever be below blue line on a single instrument or single engine instrument approach for the sake of safety. So if you have to go around, you're only going to be able to use what excess energy you have to initiate that climb and clean up your configuration. So if you're sitting down there at 80 knots, you have to go around, you're kind of already in the hole, especially if your gears and your flaps in. So if you're training with me, I'm going to ask you to hold 88 to 100 on the emergency or on the descent portion, and then 88 to 95 on the visual approach to land. ACS gives you a little more lenience. Got it? On that note as well, you guys recognize that as your glide path indicator? When you're single engine, best practice is to be slightly above the glide path, as in the center line is just on the top of the diamond. For the exact same reason, if you have to go around, you have 20, 30 feet of buffer above whatever obstacle or whatever to make your exit. Follow those procedures. Not an ACS standard, but very good practice going forward. Any questions on those two? Sweet. Now, third and final. This one, I'd argue, is the easiest, although leads to the most task saturation because everything happens so fast. First step here is different than the other two. You're going to pitch for your glide path at least 88. If you can't maintain 88 while following the glide path, there's a bigger issue. You're probably not following your engine outflow and you haven't gotten the power in. So as long as you don't freeze for an extended amount of period of time, you'll be perfectly fine. Just pitch for the glide path. Reason being is if you try to hold 88, you're going to end up doing this into a full-scale deflection. You might as well just go missed. Make sense? Engine outflow, feather, gear, in the Seminole at least, keep it down. Flaps, you can keep it at 10 degrees. You're descending. You're following the glide path. You have the help of gravity, and with your engine outflow, you've just put full power on that operating engine. You should be able to maintain blue line and that glide path, no problemo. If for whatever reason, let's say you've done all that, and you're noticing that you can't maintain the glide path and the blue line, what do you guys think is a smart decision to take out first, the gear or the flap? Flap, exactly. So play with that first and see what it gets you. After you've ran your engine outflow, you've assessed your gear in the flap, and you've feathered, come back and assess your operating throttle. From the engine outflow, everything will be left full forward. And once you've feathered, reduce that drag, even with the gear down and even with the flaps 10, at least in the Seminole, you'll blow straight through that 111 flap extension speed if you continue to have full throttle. So just be aware, the game's not over yet. Engine outflow, verify, verify, feather. Bring that throttle back to whatever you need to get yourself reestablished on the glide path into 90 knots. Make sense? Then from there, you run our gumps. 300 feet above mins, landing assured, flaps 25. Whenever you have an engine failure, especially in this last scenario, because here, you're probably flying, you've slowed down, you ran your initial gumps, you started descending, maybe you even ran your second gumps, and then you got the engine failure, you went through all of this, and you might think to yourself, oh shoot, I already did 2 gumps, why would I do a third one? If you get an engine failure, there's so much going on in the cockpit. There's so much tasks to get saturated with. Always run a gumps after an engine failure just to verify that you haven't accidentally or without thinking changed your configuration for landing. So that's pretty much the whole breakdown of one of the more complicated tasks that's required on the check ride. Single engine instrument approach. Area 1, you're clean, pitch for your IFR altitude, run your engine outflow simultaneously. Gear comes up, flaps come up because you have to maintain your altitude to your top of descent. Maintain that IFR altitude to the top of descent, run the top down flow. Remember, don't lag behind on that throttle, just bring it close enough. Gear down, flaps 10, run your gumps once you establish the descent. If you're ever descending, just waiting for something, chasing after needles, mental reminder, gumps, gumps, gumps. Second one, if the gear's down, you have to make a true assessment for your gear and flaps. How far away are you? How much altitude do you have? How much airspeed do you have before you get slow and you start descending? The rest is all the same. Here, big concern is after you ran the engine outflow and you feathered, you're going to be screaming with full power in So just manage that operating engine throttle to what it needs to be. Clear as mud? Anybody need to take a picture? This is a good thing to chair fly at home. You can pull up that poster on your TV and just walk through each scenario. One of the downfalls, though, of chair flying it and getting familiar with it is people start to recognize what the right thing to do is for each scenario, and they start anticipating it, and then when they get the engine failure, they jump the gun. And instead of running it in the order that they should, mixtures, props, throttles, they just go straight to, oh shoot, I'm right here, engine failure, gear up, flaps down, and then they freeze because they're out of order. So just be cautious of that. The engine outflow is designed in the order that it is designed for a purpose, because it is the most functional that way. Okie dokie. So next up, we're going to go into the single engine pattern, because it relates to this pretty closely. So in terms of the single engine pattern, I guess I shouldn't have erased that, but we're going to take this portion of the approach and pretty much add 2 turns in it, somewhere for your downwind to base and your base to final. The rest is quite similar. This top-down flow is kind of the center point that makes them similar. I'm going to go ahead and just redraw a traffic pattern rectangle. We'll say the runway is right here. It's 1-8, centerline stripes, 3-6. So let's break it down from takeoff to landing, kind of procedurally what you can expect to have, at least in terms of the exam. And then we can branch off from there and talk about the what if you're already at altitude and you're coming into the pattern and you get an engine failure somewhere around here. All right, so you're going to take off, and at roughly 500 AGL, you're going to start configuring for your cruise climb. That's where you go 25 squared, right? So throttles, 25 inches manifold pressure, RPM, 2500 RPM. And that procedure in our maneuver guide is pretty specifically designed so that at this altitude you set your throttles, take your hands off the throttles so that we can reach under and pull a throttle and simulate an engine failure. So you're going to go through with the engine outflow, and that's going to be along the lines of what we highlighted earlier. Remember when we broke it down 3 phases on takeoff, in cruise, and instrument approach? Here, that 88 is really important, establishing it to arrest or minimize any kind of descent rate as we're running our engine outflow. If you get the engine failure here on your departure leg, just continue flying runway heading until you've at least finished your engine outflow and feathered the identified and verified in-op engine. If you're in your crosswind leg, continue flying crosswind until you've finished all that. Moral of the story is whatever leg you're in, just continue on that leg until you've managed your engine failure. Make sense? After you've finished your engine outflow and you've feathered, you're going to be crawling to maintain altitude. You might get 50, 100, 150 feet per minute climb, but it's going to feel really, really slow. And it's probably going to take somewhere until your crosswind leg, or maybe even the beginning of your downwind, in order to get to TPA. But once you get there, you're just going to continue flying all the way down to your top of descent. The top of the descent will be your abeam point. So here it's 88 for climb. Here it's airspeed as needed. Once you're at TPA, totally fine, accelerate past 88 knots. If you want to, you could reduce the throttle a little bit so you're not putting so much stress on the engine, but just make sure you have at least 88 knots. For the most part, you could leave it full. That way you have less to think about. But once you're here, that's your top of descent. So you're going to run that top-down flow. And it's the very, very same thing that I told you guys on the instrument approach. Don't spend too much time trying to get that throttle perfectly to 17 inches. Just bring it close enough, put the gear down, put the flaps in. Once you start descending here, somewhere in this leg, you got to run your gumps. I know this got your gear down and it got your flap in, but you still got to check your fuel pumps. You still got to make sure your mixtures are full. You got to verify all of your settings and configurations. And then last bit, it's only on final, we go flaps 25. Flaps 25 should be reserved for final when the landing is assured. In this leg here, after your top of descent, extending the downwind, you want roughly 100 knots. In your base and your final leg, you want roughly 90 knots. On final, whether it's instrument approach, Single engine pattern, you're always going to maintain at least blue line, 88, until you're over the threshold and the landing has been assured. You're going to be coming over concrete hot, fast. You're not allowed to have control of both throttles until we tell you to. Both throttles are yours, but our trigger, in order to give you back your throttles, will be at least 88 knots and over concrete, at which point you can go throttles idle and use as much runway as you need in order to put the plane down. Make sense? So in summary, usually get the engine failure here around 600 AGL. Be very conscious of what pitching for 88 looks like. You're slow, so it's probably going to be about a neutral pitch attitude. Mixtures, props, throttles, reassess your pitch attitude, verify the gears up, the flaps up, identify, verify, feather, crawl your way back up to TPA holding 88 to the best of your ability, fly the downwind at whatever airspeed you need. Full throttles is fine. If you want to be a little more healthy on the engine, you could reduce the throttle a little bit, just don't slow below 88. You get to your top of descent, you run that top-down flow, throttle roughly 17, gear down, flaps 10, reassess the throttle, descend at roughly 100 knots, turning into your base, run a gumps to verify everything, maintain 90, keep maintaining 90, turning final, once your landing's assured, flaps 25, hold 90, 88 until you're over concrete, at which point the landing's assured, both throttles are yours, close them, gently round out and put the plane down. Any questions on that?
So this is going to be a pretty decent sized pattern then.
No.
It's not?
You're going to be a lot less maneuverable because you're single engine. So try to keep this tight. This spacing here should be roughly 1.25 nautical miles. 1.5 is okay. These turns are not going to be so sharp because you're going to be less maneuverable with the single engine. So you should plan for it. I mean, they should be very broad, almost like you're doing an oval. Yeah, so you don't want to be too close because then you're going to overshoot this for sure. You don't want to be too far because then you're running around with the single engine, getting really close to the ground, having to stretch it out, and that's not a good idea. So 1.25 to 1.5 is a nice sweet spot. That gives you good spacing. Good on that? Sweet. Okay, next we're going to talk about the short field pattern, short field landing. I guess the only thing that we didn't touch on that is what if you don't get the engine failure while you're climbing in the pattern? What if you have an engine failure 5 nautical miles away from the field? It's going to be very similar to the instrument approach, right? You just run your engine out flow, you maintain TPA, you feather. Once you get to your top of descent in the downwind, you do the top-down flow and continue in. Make sense? It's not that difficult. Same thing for entering a pattern. You can take that 5-2-1 descend rule that we do for the 2-engine instrument approach and apply that to entering a traffic pattern. So 5 nautical miles away from the airport, slow down, going 20-25. When you're 2 nautical miles away from entering the pattern, run your gumps. When you're in the downwind, top of descent, throttles 15, flaps 10, continue on in. And that's all in the maneuver guide. Okie dokie. Give me a second. I need to draw out a runway again. This time maybe a little bigger and a little more centered. These are going to be 1,000 footers just in case we're aiming for them. Okay, short field effort, traffic pattern. As soon as we take off, what's the first thing we got to do? It's a homework assignment from yesterday. Yeah, pause the rate, tap the brakes, gear up. So we go tap brakes, gear up. Excellent. We keep climbing around 500 feet AGL. What do we do there? 25 squared. Go 25 inches manifold pressure. 2,500 RPM. When do we start this turn into the crosswind?
300 feet below.
Yeah, 300 feet under traffic pattern, or 700 AGL. Actually, this traffic pattern isn't always 1,000 feet. Standard is, but there's Lake Charles that has 1,500 AGL traffic pattern, which I need to do more research into. Or it's not Lake Charles, but Chennault International right next to Lake Charles. So TPA minus 300 feet, we make that turn. Sweet. Somewhere within this leg, you're going to reach TPA. Let's just call it here. So the plane climbs pretty dang well. Let's go at TPA. Anybody remember what we do? Slow down. Yeah, you level off, 20 inches manifold pressure, and your props are already at 25 from your cruise. but just verify it. Now, you've reached TPA somewhere in your crosswind leg. Important thing here, the Seminole climbs a lot better than the Archer or the Cessna. So as soon as you get to TPA, it's going to feel really early for you guys. And you're going to have this natural intuition to start turning right into your downwind. Don't. Be patient. Fly it out for a little bit and then turn. Slightly faster plane, slightly bigger pattern. Takes a little more time in the crosswind. Doesn't need to be huge, but slightly bigger. So this spacing here should be roughly 1.5 nautical miles. 1.25 is fine as well. We'll call that a range. Make sense? Somewhere 1.25 to 1.5 nautical miles. It requires you to be a little patient flying this out. As soon as you get to TPA here and you've configured your 20 inches of manifold pressure and 2,500 RPM, I encourage you to begin, but not get solely focused and committed to, running your first gumps. So depending on your ADM, anywhere in this region, right? Either crosswind, through the turn, around here, run your first gumps. The first gumps is to do everything. So don't sit there waiting for the gear too long. Just make sure you assess and switch anything that needs to be switched, right? Anywhere in this region. The important thing too is to be situationally and spatially aware of this distance in your crosswind so you don't start doing your gumps here, get so fixated on it that it doesn't finish until here, and then you start flying a 777 pattern at 2.5 nautical miles away. All right? If you start your gumps, still be aware of the turn, time it so that you're roughly within this distance, and you can continue wherever you left off. You will have plenty of space in the downwind. And if you run it here, you've done your 1 gumps for the downwind. You don't need to do it again. So do not panic. Make sense? Now, this point right there is your top of descent. Very straightforward. We go 15 inches manifold pressure, flaps, 10 degrees, and airspeed roughly 100 knots. I'll tell you from experience, it's much better to be on the low end of 100 knots than it is to be on the high end, as in bounce around between 95 and 100 rather than 100 to 105. Good? The other thing here, this 15 inches manifold pressure, exact same method as when you're running that top-down approach or that top-down flow. Bring your throttles close enough to 15, get the flaps in, establish your descent, and then come back and fine-tune your throttles to 15. That's just a little technique thing that helps you do 80% of the work using 20% of the time, and then in your time left over, you can come back and fine-tune that 20% left over. Make sense? Pareto principle. Be efficient. Now, the 2 single-hand most important portions of the short field landing are all about how you establish yourself. And they come in the 2 turns. This turn into your base and this turn into final. And it's all about airspeed management. I get very, very passionate about this. It's all about having your priorities straight. So this is what your turn looks like. As soon as you're right there, see that dash? It's pretty much as close to the beginning of the turn I can make it. As soon as you've committed to that turn, flap comes to 25, pitch for 85, trim for 85. As soon as you begin that turn, flap up, you're gonna have to pull back on the nose. It is a nose-heavy plane. If you just sit there complacently and let the plane fly you instead of vice versa, the nose is gonna dip over, you're gonna start almost side-slipping in towards the ground, and your descent rate's gonna be 1,200 feet per minute before you even blink. Not a dangerous scenario, it's just the nose is heavy, it wants to sink, it's very inefficient in the turn. So it is imperative. Flap comes to 25, you hold the nose from falling over, and you get down to that manual trim wheel, and you trim the plane to sustain 85 knots. By the time you roll out of here, you should be able to pretty much say, look ma, no hands, and be able to take your yoke or your hands off of the yoke and just fly the plane with your rudders. Not safe, not ideal for a good landing, but just to make the point, that's how well you should trim out the plane for 85 in this turn. What that's going to do for you is give you all the head space you need in this base leg to 1, make your radio call, and 2, run your second gumps to verify it. The biggest pet peeve I have with students is they get here and they start panicking because, oh, I have to run 3 gumps, one for every single leg in the pattern, coming into the turn. Cato traffic, thrust 40s in the left base. No, you're not in the left base. You just started your turn out of the downwind. You're still in the downwind. Why are you making a radio call? And then they start running their gumps halfway through it. They get out of here. They're blowing through 110 knots. They've descended 600 feet, and now the entire approach is ruined. Priorities. Flap, pitch for 85, get it trimmed out. You'll be sitting here for a good 20 seconds. You can make as many radio calls as you want. You can run as many gumps as you want. You won't even have to think about it. Just trust me on that one, because the opposite gets really ugly really, really fast. So here, radio, gumps, number 2. Same thing, right here in the base to final turn. As soon as you've initiated it, flaps come to 40, pitch for 75 knots, trim for 75. I'll make a note. Oh, that's a bad tilde. Once you're in this base leg, just flying it out, waiting for that turn to come, you should be eyes outside looking at your point, making an assessment. Am I really, really high? Am I really, really low? If you're really, really high, make a slight power adjustment. If you're at 15 inches manifold pressure, which you should be, drop it to 14, maybe even 13 in an extreme scenario to help you get back to where you need to be. If you're really, really low, bump it up to 16 to 17, help you out. This is a good place to make a minor adjustment. The last thing you need is to be making rapid throttle adjustments, but we'll cycle back to that later. So flap 40, pitch to 75. If you've done this assessment properly, you should have no problem being at 75 by the time that you roll out here. Make sense? On the back end here, you do your last gumps. If you've successfully done this gumps and you've successfully verified everything on this gumps, the only thing I care about on this one is that you've once again checked your gear and that you put your props full on final. You don't need to waste your time on your gas, your mixtures, and your switches if you've already twice verified to me or to yourself or to anybody who needs to know that you've done them. But undercarriage and props full on final, at least do those because those are the most important. Good? And you can say plus radio. In this space between your touchdown point, you're going to slow from 75 knots to 70 knots. And that's the speed that you want to take into your round out. It should happen naturally. When you go props full forward, it helps slow you down a little bit, and that'll make most of the difference from 75 to 70 as you're aiming for your point. I'm going to erase all of this in a moment. We'll draw a big runway, and I'll teach you guys the good technique in order to hit your point every single time. But first, I want to be very, very clear that you guys have a good understanding of this. The big thing here is priority. Aviate, navigate, communicate. Aviate first. Get your flap, set your pitch attitude for your airspeed, trim for it so that you don't have to work. Navigate your leg, communicate on the radio. Good? These 2 turns are key. If you can set yourself up at that airspeed and manage the energy properly, the plane's just going to slow flight itself exactly where you need to go. This is a very important skill that's going to translate to every single aircraft you fly. It's not the Archer. The Seminole's a heavier plane. It doesn't get tossed around in the wind as much. So if you configure 75 knots, you're beginning to be in the reverse region of command. Your pitch attitude is going to be slightly high, and it's not as if your nose is going exactly to the point. You're going to be in slow flight on a trajectory to wherever the plane's aiming based on its energy profile. If your trajectory is a little too short, you can add just a little bit of manifold pressure, half an inch. Readjust your pitch to capture that airspeed with that new power setting and trim for it, and you'll see your trajectory slightly extend. If you're too far, reduce manifold pressure, half an inch. Readjust your pitch and your trim very slightly to capture that 75. Your trajectory for that slow flight will shorten. That is proper energy management in the area of reverse command. This is an analogy that I give to everybody. It really helps them click how the Seminole behaves, but I want to preface with it's an extreme exaggeration, right? Extreme exaggeration, but the concept is true. Compared to an Archer or the Cessna, the Seminole flies a lot more like an airship rather than an airplane. And by airship, I mean it's very large. There's a lot of lag. When you make some kind of setting change with your throttles and your RPMs, it takes a while for that change to be experienced in the aircraft. Think of like a large vessel, Titanic. You can't just go throttles full and expect the Titanic to be 25 knots faster in 2 or 3 seconds, right? Probably takes minutes. In the Seminole, if you move the manifold pressure from 15 inches to 18 inches, it's not immediately going to gain 10, 15 knots. Over the span of 15 seconds, it might. So there's a big delay. Hence, you can't just sit there on the throttles making all these micro adjustments as if you're in a Cessna or an Archer. Make sense? The other thing, going back, accelerated slipstream has a lot more impact than just what we covered in past for single engine operations. With 2 engines operating, both of those propellers are running and they are pushing significant amount of air over the wings. There's significant induced flow over the wings. So there's significant induced lift over the wings. Multi-engine aircraft have an inherent characteristic that they can create artificial lift at a whim. You don't need to accelerate the airframe to produce more lift. You just have to accelerate how much thrust you're producing, and as a byproduct, they will push more air over the wings and produce more lift for you. So in comparison, where this comes into play, if you're in the Archer and you go from 1400 RPM to 1600 RPM, it's not going to make much of a difference. So you didn't get much faster or slower, the wings act exactly the same, all your prop wash is just getting obstructed on the fuselage. In the Seminole, if you go from 14 inches of manifold pressure to 16 inches of manifold pressure, yeah, maybe you had a small adjustment in your airspeed from that extra thrust, but you had a significant increase of amount of induced flow over the wings, which is going to produce significantly more lift. So your trajectory that you're trying to hit in slow flight is going to significantly change. Make sense? So when it comes to these short field landings, when it comes to any kind of approach to landing, setting your airspeed early on, 75 knots, and getting the estimate for what the trajectory of the plane is in slow flight towards your point, and getting that time, that distance, is crucial. Because you make one small change, you reassess, you see what it's doing. You make another small change, you reassess, you see what it's doing. If you treat it like a Archer, like a Cessna, and you're trying to chase everything, you're not going to know what kind of lag you're creating, and you're going to start overcorrecting for a correction that you didn't even let settle prior, and then you're just chasing this oscillatory ghost motion that you're creating yourself. Make sense? So big thing, set your airspeed, understand your energy profile, give yourself the distance and time to make those micro adjustments. Good? Sweet. Now to tie all this together, I'm going to draw a much larger picture of the runway and break it down to you guys. How to aim, how to pull your throttles, and how to hit your point every time. I sound like an infomercial. But I'm serious, it's that easy. All you got to do is follow this. Those are your 1,000-footers. You got 1 centerline stripe, 2 centerline stripe, 3 centerline stripe. So all of this is under the establishment that you're coming in at 70 knots. That is where the airplane has enough energy that if you need to draw it out just a little bit, you have that energy to draw it off and hold it off for a little bit. But if you're ready to put it down, you can just stop flaring, and the weight of the aircraft will very gently bring it down to the ground. That's another big difference between the Archer. The Seminole's heavier. If you just stop flaring, the plane will quickly run out of energy and gravity will take over and it will settle itself down to the ground. It's not going to get picked up by a big gust of wind and continue floating like the Archer or the Cessna. Right? So 2 is your aiming point. This is where you want to aim to round out. And in parentheses, I'm going to put low. You want to round out low to the runway. It's going to be intimidating. You're going to feel like you're in a much bigger plane because you got 2 engines and it's heavier. But you could go on the ramp right now. The Seminoles don't sit any higher off the ground than the Archers do. So you can round them out at the exact same distance over the ground that the Archers. You don't have to feel like you're some enormous elephant and round out 60 feet over the runway. Good? Low round out is key because it gives you precision of where you either add more flare to allow it to keep floating or stop flaring to allow the weight to vary over that short distance, come down and gently touch down. If you have a high round out, and you decide I need to put the plane down, either one, you can run out of energy and that weight is going to accelerate and make a very aggressive landing, which I'll yell at you for, or two, that's usually just what happens. Not really a two. Anyways, three, this is going to be where you pull power. And one, flaring doesn't have the, one is going to be where you stop flaring. So we'll treat this table here kind of like a pseudo runway and mock up what we have. One eraser, two eraser. These are our 1,000-footers. Oh, we could even use the airplane. It's funny because this is how I teach it in the FBO. But I usually use packets of sugar or salt or whatever they have there, or toothpicks. Center line, center line, center line. Can you guys see that? Yeah. Okay. So this two, that two, that's where we're aiming for. Right, we're in this slow flight, nice and draggy. We're just plowing through the air on a trajectory towards this point, right? That's where we're aiming for. 70 knots, all assumed. As we cross over this third line, this is where we're going to pull power very smoothly to idle. We'll pitch the nose over to get that sluggish attitude out and just continue to a nice low round out over this point. At which point you're going to flare ever so slightly just to get the nose gear off. And when you're over that first center line stripe, you just stop doing anything. No forward yoke movement, no backwards yoke movement, just stop. The weight of the airplane will take over and set you down on your 1,000-footers every single time. The two things that are important to this, 70 knots on the approach. Totally lost my train of thought. 70 knots on the approach and a low round out. If you're too high, you're going to extend too far because there's too much distance for the weight of the plane to fall over. It's both going to be long and an aggressive drop when you run out of energy. If you round out low, you can flare as much as you need to extend it, or you can stop as soon as you need to drop it there, right there. So important thing, one more time. You're configured in slow flight. Trimmed out 75, approaching 70. Over the third, you've cut your power to idle. You pitch the nose down. You round out over the two, nice and low. You flare ever so gently. You stop, thousands every time. Second consideration here. I very, very highly recommend you go out to the ramp and look at a Seminole that's sitting right next to an Archer. You see the Archer? The nose is up. It has a natural stance that it's strutting around with its nose up high. If you're just taxiing around, the plane itself usually has a 5 to 7.5 degree pitch up attitude, right? The Seminole sits on the ground, nose low, has pretty much a neutral pitch attitude. So take that into consideration of what your sight picture is going to be like in the Seminole. A lot of these guys that are transitioning Cessna or Archer, they're under the impression that they're flying the Archer still. And you need 12 degrees of pitch up attitude just to keep your nose gear from hitting the ground because the plane naturally sits in such a nose high strut. The Seminole doesn't need any of that. If your cowling is covering the runway, you're probably flaring too high. You really don't need that much at all. And you can just hold that flare attitude, whatever it is, 5 degrees, maybe even 7 in an extreme point. The weight of the plane will nicely take over and set you down wherever you are. So do not over flare. It's going to feel like you're going to nose strike, but it's not going to be that case at all. The sight picture is way, way more shallow. Any questions on all that, Jess?
When you say stop over one, do you mean release pressure or just like?
No, do not release pressure because that's going to cause the nose to fall over. What I mean is stop that continuous flare. Because in the Archer and the Cessna, you get to that point and you're progressively adding more. All of you guys have this primacy to progressively add more and more flare and hold it off, hold it off, hold it off, because you need extreme pitch up attitudes to soft field land an Archer or a Cessna. And the Seminole, I'm just saying, only add a little bit when you're over that second line so that the nose comes up and you land mains nose first. And as soon as that's assured, you don't need to increase your flare attitude anymore. So just maintain that pressure and then the weight will take over and settle you down nice and gently.
You're just arresting it at that point.
Yeah, you're arresting your flare attitude. And then you're flying by your butt. And your butt will tell you how quickly or slowly you're accelerating into the ground. If you've rounded out really high, I would suggest maintaining some flare to arrest your descent because you're going to have a long distance to accelerate. But that's the importance of the low flare. If you flare really, really low, as soon as you want to land, you just arrest your pitch up attitude, the weight will take over and it'll kiss you down nice and soft. So low, round out, very important. Or maybe not low, but same as the archer, not high, so that gets scary. The other thing too is, if you're coming in any lower than like 67 knots, it's probably best to just go around at that point. So the plane's heavy and you'll experience it. Like 67 knots, if you get really slow and if you've rounded out a little too high, the plane just does not have enough energy to float you out and you will crater that thing. So it drops like a rock when it runs out of energy. So 70 knots gives you just that sweet spot where you can extend it a little if you need to, or you can arrest your flare and it'll come down if you need to. Yeah, you follow that procedure, you'll get it every single time. If you try to fly it like a Archer and a Cessna and you just pitch down into ground effect here and try to float it out all the way, you're going to be so inconsistent. You'll never get it by the time you get to your EOC. You only get 3 flights to practice it. So it's in your best interest to follow this. It's tried and it's true, and it's very simple once you get it the first time. The other thing too, the ACS specifies minimized float. So it's 1, silly to do it in an Archer. It's 2 times silly to do it in a Seminole. That crosses off everything on the list.
That wraps up day 2 and our multi-engine course training. If you guys are still watching, kudos to you for watching the whole video. It was very long. That being said, make sure to like, comment, and subscribe, and thank you for watching.